Hi, this course is the Variable Frequency Drives course. This course was written by Vincent Woods-Weblick. I've been messing with variable frequency drives for many years. For a long time I was an instructor at one company that taught variable frequency drives. The material used to put this course together was taken from the internet, Wikipedia, Siemens, Toshiba, ABB, any website that was available on the internet and didn't have a copyright information. I went ahead and used some of this information. What we'll cover in this course: first we have to cover AC induction motors. Then we'll talk about motor efficiency and motor assessment. Next we'll talk about controlling motors or motor controllers. Then we'll move into variable frequency drives, and then we'll talk about harmonics, and then last we'll talk about application considerations. This particular motor is from Baldor. It's an AC motor. Basically converts AC electrical energy to mechanical energy. You'll find out later here in a minute that the mechanical energy can actually spin faster than the motor, and it can actually reverse that process. So this induction motor can become an induction generator. This here is a large induction machine made by Siemens. The top portion of it is a housing, and then the bottom inside the housing or enclosure is the actual motor. These are used for large industrial applications, usually three-phase induction motors, 4,000 or 5,000 horsepower motors. These are very large machines. The bearings in front of this Siemens machine is actually a Babbitt bearing. So this is a little symbology here. So here you have, on the left you have your electrical system. You have E as voltage and I as current, and you have your electrical machine in the middle. And then the idea is that you would have mechanical systems tied to the output of it. So you'd have torque and speed. T is torque, N is speed. So if the direction of the flow if the flow is from the electrical system to the mechanical system, it's a motor, or it's said to be motoring. If the flow is from the mechanical system to the electrical system, and the energy flows in that direction back towards the electrical system, then it is said to be a generator. So an electrical machine is the link between an electrical system and a mechanical system. Conversion from mechanical to electrical, again that's mechanical to electrical, is the generator, and the conversion from electrical to mechanical is a motor, which is normal. We don't really talk a lot about single-phase induction motors here because primarily the VFD is a motor or a drive that drives a three-phase motor. So even if you had a single-phase source, you would buy a three-phase VFD and connect it to a three-phase motor. You'd plug in single-phase to the input of the VFD, and you'd have to derate it. But other than that, I'll just kind of point out a few things here about single-phase motors. Typically, they need a capacitor to start them. So once the capacitor allows the motor to start, then it disconnects the capacitor after the motor picks up speed. There's a centrifugal type clutch that allows this electrical disconnect, or that allows it to start up and allow the capacitor to be in the circuit, and then when it comes up to speed, it disengages the capacitor and the motor's allowed to run. Because of that electrical clutch, these motors cannot be used for Class 1 Div 2 areas unless they are in an XP type enclosure, an explosion proof enclosure. If you wanted to have a motor that's more energy, uses less energy, then you would add a capacitor, a run capacitor to it. So you'd have the start capacitor after it started up and came up to full speed, then the run capacitor would be allowed to be put into the circuit. This keeps the capacitor connected during the operation of the motor in order to keep the electrical power consumption low. And then you can actually have dual, where you have a capacitor start run, uses two capacitors, one for starting and one for running, and this further improves power consumption. You can always tell a single-phase motor because it has a little hump on it, right? And you'll see a little can on top of it, and that indicates that there's a capacitor in there. So here we have the motor construction, or the stator. The stator forms a hollow cylinder with coils of insulated wire. These are inserted into the slots of the stator core. The coils plus the steel core form an electromagnet. What they do is starting on the far left of this illustration, you see these plates. These are very small, thin plates, lamination plates. They're stacked. A bunch of them are stacked all the way up until they make the stator core. The reason they have laminated plates is because that core would get super hot because it would be because of eddy currents is what happened. So what they discovered, and they do this in transformers as well, is they stack these lamination plates and insulate them between each other, and that prevents these rotating eddy currents. And then next they take and lay these insulated wire coils in there, and then they interconnect them all. And then after that, they dip this into a resin tank full of resin, hot resin, and they pull a vacuum on it, and that's what they call vacuum pressure impregnation, where they pull all the air out of all these connections. Then we have the motor construction, the actual rotor. There are two types of motor rotors, the wound rotor and the squirrel cage. The wound rotor has coils of wire wound in the slots of the rotor, similar to generator coils. The squirrel cage consists of bars of copper or aluminum, electrically connected at each end with conducting rings. As the rotor rotates inside the magnetic field, it receives electromagnetic induction. Then current flows and form the rotor electromagnet. So basically what happens is, as the stator injects a rotating magnetic field into the rotor and causes the rotor to turn, it in turn has that magnetic field going across these conductor bars, which if you have a current flowing through a conductor bar or through a conductor, it creates its own magnetic field opposite of the other magnetic field, and it reverses it. It's a counter electromotive force, which will be important later on as we work through this course. There are different types of motor enclosures. You have the ODP, which is the open drip proof motor. You have the TENV, totally enclosed non-ventilated motor. The TEFC, totally enclosed fan cooled. And then the XP, the explosion proof motor. The most common here is the TEFC, totally enclosed fan cooled motor. And primarily they'll use these in refineries and petrochemical locations because they're inherently class 1 div 2. They are totally enclosed, and the fan is on the outside of it, so that it doesn't create any arcing and sparking contacts or devices, and it can be put into a class 1 div 2 area. If you don't understand what class 1 div 2 area is, watch the area classification DVD that's in this package. So the types of motor enclosures, you have the open drip proof. It allows air to flow, flows through the motor. The fan blades help flow. Used environments free from contaminants. You don't really see these very often. You can see right below the vent is the connection part where you actually connect the conductors. An electrician would call that a peckerhead. It's always some funny words in electrical engineering, but one of them is the peckerhead on an electric motor, and it's really what they call it. So next we have the TENV, the totally enclosed non-ventilated fan, or ventilated machine. And so here you have the protects motor from corrosion and harmful elements, and the frame fins help dissipate the heat. So there really is no internal fan inside this motor. It just the heat builds up inside of it to a point where it just transfers the heat to the outer body of the motor, and then natural conduction occurs at that point. This motor can get pretty hot, but certainly they oversize it so that it can run in this duty. This is actually the most popular motor. It's the TEFC, totally enclosed fan cooled motor. It can be used in a class 1 div 2 location. It has that fan on the back end of it, which actually pulls air across those outer fins. It's actually sealed right there. You can see in that peckerhead They've got the red and the green and the black wire that are coming out of it, and that's actually sealed to the environment. So it's a very well built motor. You can see the cutaway here, the blue, and then you've got the yellow cutaway, so you can see the actual stator inside there with the stator coils, and then inside you can see the actual rotor. And then this is actually a bearing. When you look at this, it's actually a roller bearing as opposed to an oil Babbitt type bearing. This is an XP explosion-proof motor. An XP explosion-proof motor is similar to a TEFC, but enclosures are cast iron. Can be used in a Class 1 Div 1 location, whereas the TEFC can only be used in a Class 1 Div 2 location. If you don't understand what Class 1 Div 1 or Div 2 is, watch the area classification DVD 1 and 2 that I've provided in this package. Three-phase AC motors. It has three pairs of electromagnets connected to one of the three phases of the power supply. It provides a lot higher power than what a single-phase motor can deliver. And that's primarily why we use three phases. It's because you can get a lot more power in a smaller package. A lot of people ask that question, well, why don't we just use DC or single-phase? Three-phase is more condensed, and it just provides a lot more power for the physical size. Certainly you could bump up the phases. You could go 6-phase or whatever, and you'd get even better performance. But the induction motors, I think probably 70% of the market actually uses induction motors, three-phase induction motors. Here's another induction motor machine breakdown. It's the actual construction, another good cutaway. You can see the rotor cage in iron. You can see the stator windings. You can see the terminal box or pecker head, and then you can see the shafts pointed out. On the AC motor data plate, each motor has a plate mounted on its frame with electrical and mechanical information. It's critical that you record all of this information when you go out there and investigate either a motor changeout or an electrical study. What's on this is your motor manufacturer's ID number. Sometimes you might have to go back to the manufacturer with the ID number to get all the relevant data and also some better curves. You'll have your horsepower, you'll have your synchronous speed, your RPMs, that's rotations per minute. You'll have your duty cycle, minutes out of an hour motor can be operated. You'll have your insulation class, which is tells you how hot the insulation can get before it burns up. You'll have the type of winding insulation, be it class H, F, or whatever it is. Ambient temperature rise, that's the actual air outside. If it's designed for 40 degrees C, it'll say 40 degrees C here. 40 degrees C is about 102 degrees F, so that's not uncommon, especially in southern states like Texas or something. If you ship it into Arizona, you might see 50 degrees C requirements, and certainly in Saudi Arabia or something, you'd see 50, 55 degrees C as well. Then you have your Nema design letter code classification, and the design code is actually allows you to understand the characteristics of this motor, such as the torque curves and things like that, and we'll discuss those later here in a little bit. Next, you have your Nema code. This allows you to calculate your locked rotor current. When the rotor is initially sitting still, then what happens is the locked rotor current is the highest, right? When the contactor closes, the rotor is not turning, but at that point in time, you have the highest current, the locked rotor current, and you can calculate what that locked rotor current is by the Nema code, and I'll show you that in a little bit as well. You have your frequency of the electric supply. Usually that's 50 or 60 hertz, HZ, hertz. Then you have your service factor, how much the motor can be overloaded. So typically a service factor is 1.0 or 1.10 or 1.15. In this presentation we actually see 1.25, but I've never actually seen an induction motor that was rated 1.25 of its service factor. And what that means is, let's say that if you had a 50 horsepower motor and you had a service factor of 1.25, then you would actually take 50 horsepower times 1.25, and that would be the actual horsepower you could run that motor Not that you'd want to do that, but it is actually rated to do it continuously. Number of supply phases, you either have single phase or three phase being the most common. And then you've got the type of enclosure, which we just talked about, the ODP, the TENV, and the TEFC, and then the XP. Next you have your frame type. The frame type actually will be talked later. That's part of Nema MG1. And using the frame type, you can actually understand all the physical mechanical dimensions of the motor, and we'll show you that shortly as well. And then obviously you need the current used under full load conditions. That's your full load amps, FLA, and that corresponds to the actual horsepower and the voltage. And then you've got your three-phase line-to-line voltage. So if it's a 480 volt motor or 480 volt service, typically that voltage will be 460. It's always a little less than the actual line-to-line voltage. Next we have some motor I/O relationships or input-output relationships. If you want to solve for the kVA, that's kilovolt amps in, you would take the square root of 3, which is 1.732, times the line-to-line voltage, so it could be 460, times the full load amps, I is the current, divided by 1,000. That equation, the kVA in, equals the kilowatt in divided by power factor. So if you were able to solve for kVA and you know your horsepower, because the horsepower is, let's just say hypothetically it's 1 horsepower motor, then that would correspond to 0.746 kilowatts. So 1 horsepower always equals 746 watts or 0.746 kilowatts. So then you could actually solve for your power factor using that, just the nameplate data. kWn is the square root of 3 times volts line to line times the current times power factor divided by 1,000. So that's the square root of 3 is 1.732 times volts line to line on the nameplate would be 460 times the current. If it's a 10 horsepower motor, it might be 14.3 amps or so, times the power factor. Usually you don't know the power factor. It's not given on the machine. And the reason it's not on the machine is because it is a function of the loading of the machine divided by 1,000. So that kilowatt in equals the horsepower out times 0.746. Remember I was telling you that the nameplate horsepower can be converted to kilowatt in if you know, if you multiply it times 0.746 divided by the efficiency, the actual efficiency of the machine. Efficiency you rarely see as well on the nameplate. So here you have a little motor nameplate data, and you've got all this information coming in. You've got the current, and you've got the line-to-line voltage, and then out you have the horsepower out. Horsepower out can be converted to torque, which equals torque in foot-pounds times the RPMs, how fast it rotates, divided by 5250. So that equals kilowatt in times efficiency divided by 0.746. So those are just some nice motor I/O relationships you can use to calculate some different things. This is a slide that was taken from Article 430. That's the National Electrical Code. NFPA 70 is the National Fire Protection Association Article 70, which is the National Electrical Code. In there is an article called 430, which is strictly for motors. And so if you were to look down this you see the middle part here, you see the supply, and then you've got the motor feeder. So if you were trying to size the motor feeder, you would go to Article 430.25. If you wanted to size the motor feeder short circuit and ground fault protection, you'd go to Part 5 of this code. If we could slide all the way down to the actual motor overloads, you would go to Part 3. And pretty much it has everything you need to know about sizing the feeders and the controls for that motor in the National Electrical Code. So we'll look into a little bit of this National Electrical Code and look at some of the tables that you might use. Here you have table 430.7b, which is your locked rotor indicating code letter. So remember on the nameplate, if we saw a code letter B, then you can see that's in that column that's 3.15 to 3.54. You always go to the highest value, 3.54. So that would equate to kilovolt amperes per horsepower with locked rotor. So if you want to know what the kilovolt amperes per horsepower is, you would take the full load amps times the 3.54, and or actually you take the 3.54 times the horsepower, and you would get your kilovolt amperes, and then from there you could solve for the current, the locked rotor current, and we'll do that here in a little bit. Table 430.52 is the maximum rating or setting of the motor branch circuit, short circuit, and ground fault protective devices. So if you have a, let's just use the squirrel cage motor. Well, let's use Design B energy efficient. It's the, let's see, 1, 2, 3 down. Design B energy efficient. If you have a non-time delay fuse, then you want that to be 300% or 3 times the full load amps. That would be the proper size, and then you just round up to the next larger size. If you used a percent of full load current, the dual element time delay fuse, then you would use the 1.75 or 175% of the full load amps. And if you used an instantaneous trip breaker, you could go all the way up to 11 times or 1100% of it, of the full load amps. And then inverse time breakers is 250% or 2.5 times the full load amps. Here we have the motor controller enclosure selection. We kind of talked a little bit about this, but when we talked about the actual motor itself, what if it's a TEFC, stuff like that, or you know, it's rated for outdoor use or something. But when the actual motor controller, what's actually starting and stopping the motor, that enclosure needs to be rated as well. So if the enclosure is going to be outdoors, and you'd probably want a Nema 4 enclosure. If it's a highly corrosive environment, like a lot of salt, if it's up near the beach or something, then you'd want a 4X, right? So that's a 4X enclosure would be like stainless steel, like a 304 stainless steel or a 316 stainless steel. Could be even fiberglass or a plastic, different types of plastics. Those are all 4X, Nema 4X rated. If you have it indoors, then you could also have a Nema 4X application. And the best way I can describe a Nema 4X enclosure is if you were to put it in the back of your pickup and took it to the car wash, you could hit it with that jet spray in every different direction and it wouldn't get inside that enclosure. Your electrical equipment would still be dry. So everything that connects to that Nema 4X box, so if you connect conductors to it like cables or conduits, everything has to be rated for this Nema 4X rating. Otherwise, you're going to break down the integrity of the box just because you put the wrong lamp or the wrong cable gland on it or something like that. Next, we have the conversion table for the three-phase or polyphase Design B, C, and D maximum locked rotor currents for selecting disconnecting means. So you can see if I have a 20 horsepower motor and I slide over to 460 volts for a Design B, C, or D, then I know my amps is 145 amps. So these are nice tables in the NEC, and you can grab these right off the internet. You'll find tables and stuff like that. This is a Nema table 11. It's the characteristics or applications for fixed frequency small and medium AC squirrel cage induction motors. Again, the Design B is the most common. You'll find out that the locked rotor torque is between 70 and 275% of the normal rating of that motor. The pull-up torque is 65 to 190%. The breakdown torque is 175 to 300%. The locked rotor current is 600 to 700%. So if you were just to guess at what the locked rotor current would be, you usually use about 6 to 7 times the full load amps, and you're usually pretty close. Electrical motors or induction motors don't actually run at synchronous speed. So if you've got a 4-pole machine running at 60 hertz, the synchronous speed for that machine is 1800 RPMs. But because of the slip, the rotor is not in phase with that synchronous speed, that rotating magnetic field in the stator. So it lags, and that lag is real important. It's called the slip. That's what actually creates torque. So it can be anywhere from 0.5 to 5% of sync speed. That's why your RPMs is always something like, for a 4-pole machine, it would be 1764 RPMs on an 1800 synchronous speed machine. So just give you a little indication there. Typical applications are fans, blowers, centrifugal pumps, compressors, motor generator sets, where starting torque requirements are relatively low. Relative efficiency is medium or high. So that's primarily the most common motor there is the induction 3-phase motor design B. If you recall, we talked about the frame dimensions on the actual motor nameplate. So if you were to slide down here, you'd see, let's say the first thing is frame 42. So D is from the bottom of the motor mounting foot to the center of the shaft. It's in the third diagram over. So that gives you the height of the shaft, the actual center line of the shaft. So you can see it's 2 5/8 inch height. E is from the actual mounting hole on the left-hand side or the right-hand side to the center of the shaft is 1 3/4 inch. So using these frame sizes on the nameplate, you know all the physical dimensions of the motor, and you don't have to be stuck with one manufacturer's motor. You can actually use multiple manufacturers such as Baldor, Siemens, Toshiba, etc. Going back to the Nema motor enclosure types, what we talked about before, the TEFC, the totally enclosed, the TEXP, totally enclosed, explosion proof. These are extremely wet, dirty, and dusty environments. But you can clearly see that, what we were talking, we overgeneralized before by saying ODP, open drip proof. Really, there's 4 different types of open drip proofs, and there's, I don't know, you can count all the totally closed different ones. There's quite a few. And the weather protected, there's 2 of them. And then you've got your IEC. IEC type motors are like IPs 22, 44, 54, or 55. A 56 or 55 is equivalent. They say it's almost equivalent to a Nema 4X or a Nema 4. But the problem is you can never convert an IEC motor to a Nema motor. Or a Nema enclosure to an IEC type enclosure. It just doesn't quite work. Even though manufacturers would lead you to believe that it is an equivalent, it's not. This is a nice chart. This chart actually breaks down the entire, remember we were looking at the article 430, right? And it broke every little article down. So this thing actually gives you the entire breakdown. It's got motor horsepower. You could find that in the National Electrical Code 430.250 table. Here they have a 20 horsepower motor. So for a 20 horsepower motor, if you were to look it up, you'd see the full load amps is 27 amps. Sometimes that's less when you actually get the motor. It's just because every motor is different. You could build 10 motors at the same time and you'd have 10 slightly different results. You got your lock letter code or kVA per horsepower. And here we have an F motor, and so if you were to look up what an F is, you'd see it's 5.59 times the full load amp. So that would give you that. We'll go into that later as well. You can calculate your locked rotor amp rating there as well. So if you were to calculate it, you'd say that 112 kVA. So 112 times 1,000 is 112,000 divided by the square root of 3 times the line-to-line voltage. So that would be 112,000 divided by 1.732 times 460, which is 141 amps. So that was what your actual locked rotor current would be. And you can go through the rest of this as well. You'll find out that when they size that transformer, if you look at the very top, it says power requirements is 3-phase 7200 line to neutral voltage. Well, 7,200 line to neutral is 12,470 line to line. So you can see item 30 at the bottom. Is it 30 or 29. It's a delta primary transformer, so the line-to-line voltage is 12,470 volts, and the secondary volts is a Y transformer, so it's a delta Y transformer, and so it's 480 volt line-to-line, 277 line to neutral. But that just gives you a nice little breakdown, and I think you can, if you were to search on the internet, you could find where I found this, and you could dig through these different codes. You can see the item number 21, the motor frame is a 256T, so you can actually run off of that and figure out all kinds of things here. You got your motor sync speed is item 19. So your motor sync speed is a function of the poles, so you have 120 times the frequency is 60 hertz divided by the number of poles, 4, so it's 1800 RPMs. That's kind of a neat little chart. We'll do a little quiz here. Which of the following is least likely to be found on an induction motor nameplate? The frequency, the motor weight, the full load current, or the RPMs? And I gave you the answer at the bottom right there. It's actually the motor weight is not something you're going to see on that nameplate. Which of the following is least likely to be found on an induction motor nameplate? Full load power factor, design code, frequency, or full load current? And remember I said the power factor is a function of the loading, how much you load it up, so they rarely put the full load power factor, although you can back into that calculation with some of those calculations I gave you earlier, or you can just pull the data from the manufacturer and they'll give you the full load power factor. A 60 hertz AC motor is running at 1,178 RPMs at half load. The motor has how many poles? And so, again, it's 120 times the frequency divided by the speed at which the machine's running. So we have 120 times 60 is 7,200 divided by 1178 RPMs equals 6.11. Therefore, the poles are a number of 6 poles. And that would be answer number C. Which of the following is least likely to be found on an induction motor nameplate? Again, it's full load RPM, full load horsepower, full load current, or full load torque. And the answer is D, full load torque. And you would find your full load torque value by looking at the actual code of the motor, so the Nema code rating. So, and we'll talk about that later here in a little bit, how the torque is actually built. Motor nameplate indicates the following: it has a horsepower of 50, service factor of 1.25, that's SF, voltage 460 line to line, current 53 amps, RPMs is 1145, code letter is a B, phases equals 3, the design letter is a B. So you have a code letter and a design letter. The temperature rise is 25 degrees F, and the frequency is 60 hertz. This motor has how many poles? So they gave you a lot of information in this question, but really they're after the same question. So it's 120 times 60 divided by 1145 in this example, so you get a 6-pole machine. And that's answer is B. Same data, but this time we have a different question. The question is, the maximum horsepower is what? Well, it's a 50 horsepower motor, but remember the service factor. The service factor in this case is 1.25, which is abnormally high. You don't usually see that. So you'd have 50 times 1.25 is 62.5 horsepower. That would be the maximum horsepower you'd want to run that motor. Otherwise, you'd cut the life in half if you ran it over 10% of its rating for an extended period of time. And the answer is B, 62.5. A motor nameplate indicates the following: horsepower 50, same data, service factor 1.25, voltage 460, current 53, RPMs 1145, code letter B, phases 3, design letter B, temperature rise 25 degrees F, frequency 60 hertz. That's an odd temperature rise, but whatever. Starting current at rated service factor is most nearly what? So what you would do is you'd find the code letter B, and you'd go look up in that article 430, and you'd find that a code letter B is 3.54 kVA per horsepower. So your horsepower is 50. So you take the 3.54 times the 50 horsepower, gives you a starting kVA of 177 kVA. If you take that kVA divided by the square root of 3 times 460, you'd find out your current is 222.4 amps. That is your locked rotor current. And it won't last very long until the motor comes up to speed, but that's the value when it's initially energized. So the answer that is most nearly 222.4 would be C, 225. The following illustration shows the allowable temperature rise for motors operating at a 1.0 service factor. Before we had that 1.25 service factor. This is at altitudes no higher than 3,300 feet. Each installation class has a margin allowed to compensate for motor's hot spots, a point at the center of the motor's windings where the temperature is higher. What they do is they find the hottest spot that they can in the motor, and they use that to as the worst case scenario. It's called the hot spot. For motors with a service factor of 1.15, you just add 10 degrees C to the allowed temperature rise for each motor insulation class. So you can see that here we have a class F insulation, so it has a 105 degrees C rise over ambient. And then if you have a 1.15 service factor, you can add that 10 degrees C hotspot. So the motor insulation class F and a service factor of 1.515. This means that its winding temperature is allowed to rise to 155 degrees C with an additional 10 degrees C hotspot allowance. Motor life versus temperature. Most insulating materials have a negative temperature coefficient. That is, their resistance decreases as the temperature increases. And you can kind of think about that. If you have a conductor and you're running a lot of current through it, the insulation, the actual insulation material gets soft, right? And it's easy. It's not as it becomes real pliable and easy to cut. And so that tells you that it's heating up, right? So therefore, electrical stresses are more likely to cause insulation failure at elevated temperatures. So if you run a motor above its horsepower rating, above its service factor rating, then the insulation will get real soft and it'll break down real easy. So you want to be real careful not to do that. Motor life versus temperature. Insulation aging may be attributable after years of service to thermal weakening, even at rated nameplate temperatures. So this process is greatly accelerated by operation at higher than normal current ratings because the heating increases as the square of the current. Continued operation at elevated temperatures produces embrittlement and mechanical deterioration of insulation. Hence, current nameplate values are exceeded at the expense of decreased insulation life. So if you run above that full load amps, you're going to destroy your machine. Insulation degradation is a chemical reaction or action, and higher temperatures accelerate this process. So here we have an equation from IEEE C57.91, and it's the life in hours equals this equation A plus B divided by T. T being the temperature in kelvins. A and B are typical constants that are related to a certain insulation system. Each insulation system has unique constants. So here it is. T is the absolute temperature in degrees Kelvin. So you take your Celsius degrees plus 273 gives you Kelvin, using the temperature at the hottest spot in the winding. And then A and B are constants that vary with type insulation systems. Typical values for a Class A insulation, which is really not very normal. You usually see a Class F insulation or Class H, but for an A would be negative 11.968 plus NB would be 6,328.8. So you can actually go back to that IEEE C57 and figure this out. I think it was C57. Although the above gives a general feel for life expectancy due to temperature changes, other variables such as vibration, moisture, switching surges must be factored in determining the actual life. So if your temperature is just fine, you can still have motor failures if you have high vibration, high moisture. You've spec'd the wrong motor for this application. You know, maybe it's too close to the ocean or something. You might have switching surges, which would cause spikes in the voltage, which could penetrate a hole in the insulation system. So this is really kind of a hard thing to gauge. Nema motor designs, we talked about the letters, the the letters used, the A, B, C, and D to identify the motor designs based on torque characteristics. The motor is a design B motor is the most common type, as we've talked about, A being the least most common. The characteristics of motors designs B, C, and D are discussed in this course. Speed torque curve for a Nema B motor. Because motor torque varies with speed, the relationship between speed and torque is often shown in a graph. This graph is called a speed torque curve. This curve shows the motor's torque as a percentage of the full load torque over the motor's full range speed range, shown as a percentage of its synchronous speed. And we'll get into more graphs and stuff. I think you'll understand this pretty well once you go through the graphs. When we're talking about a torque and a magnetic field, torque, a moment or moment of force, is the tendency of a force to rotate an object about an axis, fulcrum, or pivot. So just as the force is a push or pulling, a torque can be thought of as a twisting motion, right? It's twisting the shaft. It's a mathematical torque is defined as a cross product of the lever arm distance and force, which tends to produce rotation. Easiest way to think about this is maybe breaking a bolt loose or something. So if you have a very long torque, a wrench, a lug nut wrench on your tire, and the handle's very long, you're going to increase your torque. It'll be easier to break that nut loose. If you have a very short wrench, it's very hard to do that. So loosely speaking, torque is a measure of the turning force on the object, such as a bolt or a flywheel. For example, pushing and pulling the handle of a wrench connected to a nut or bolt produces torque, turning force, that loosens or tightens the nut. So if you add an extender or a pipe on that wrench, you can increase your torque, right? It's easier to turn that bolt. You might even break it if you're not careful. The symbol for torque is typically tau, T, that Greek letter tau. When it is called moment, it is commonly denoted as M. The magnitude of torque depends on three quantities: the force applied, the length of the lever arm connected to the axis to the point of force application, and the angle between the force vector and the lever arm in symbols. So here we have a torque is the basic specification of an engine. So for your car, for example, the power output of an engine is expressed as its torque multiplied by its rotational speed of the axes. Internal combustion engines produce useful torque over a limited range of rotational speeds, typically from about 1,000 to 6,000 RPMs for a small car. The varying torque output over that range can be measured with a device that will actually measure that torque, a dynamometer, and shown as a torque curve. This graph will actually help explain kind of how this torque works. So here you have a wheel or a shaft that's 6 inches in diameter. And we have a 100-pound weight hanging there. So we take half that diameter, which is the radius, 3 inches. So our torque equals the force times the radius, the lever arm. So T equals F times R. So if we had 100 pounds and the radius is 3 inches, then we have 300 inch-pounds of torque. For a motor, the torque in inch-pounds is 63,025 times the horsepower divided by the RPM. So if you wanted to measure it in foot-pounds, it'd be 52 times horsepower divided by RPMs. And to kind of show you the relationship between the horsepower and the speed, if the speed is increased or decreased, it changes the torque. So here we have a 1 horsepower motor at 1750 RPMs. T equals 63,025 times the horsepower divided by the RPMs. So we've got 63,025 times 1 divided by 1750. So the torque at that RPMs is 36 inch-pounds. If we decrease that speed, we cut it in half, then we have 875 RPMs, which is 72 foot-pounds. or inch-pounds rather. So when the speed is cut in half, the torque value increases by the same ratio, or 2 to 1. That's kind of interesting. Using that, they used to create, or they still do, gearboxes. The torque multiplier is a gearbox with reduction ratios greater than 1. The given torque at the input gets multiplied as per the reduction ratio and transmitted to the output, thereby achieving greater torque, but with reduced rotational speed. Here's an actual curve. This is a speed torque curve for the most common motor, the Nema B motor. The Nema B motors are general purpose single speed motors suitable for applications that require normal starting and running torques, such as fans, pumps, lightly loaded conveyors, and machine tools. The bottom, you've got your percent synchronous speed, and then you've got your percent load torque. So initially you have 150% full load torque, and that would, you could actually back into that and figure out your locked rotor current from that value. And then as the speed increases, it dips and then it rises and then it falls into a stalled condition. So if you go over synchronous speed, you can actually stall a motor. It'll come to a screeching halt. Using a 30 horsepower 1765 RPM Nema B motor as an example, full load torque can be calculated by transposing the formula for the horsepower. So here we have the horsepower is known, it's 30 horsepower, and we're solving for foot-pounds, so we're going to use 5252 divided by the RPM, so we have 30 times 5252 divided by 1765 RPMs is 89.3 foot-pounds. So how does this torque curve, how does it actually made, or what are significant values along the way? The first value is your starting torque, also referred to as the locked rotor torque. It's when the motor is actually not started yet. This is the torque that the motor develops each time it is started at rated voltage and frequency. When the voltage is initially applied to the motor stator, there's an instant where the motor turns, before the motor turns, and at that instant, a Nema B motor develops a torque approximately equal to 150% of the full load torque. The full load torque being here 89.3 foot-pounds, or pounds per foot. For a 30 horsepower 1765 RPM motor, in this example, that equates to 134 pounds of torque. So, yeah, so that would be your starting torque would be 134 foot-pounds, and your full load torque, as we just previously calculated, is 89.3 foot-pounds. Next, as the motor picks up speed, the torque decreases slightly until a point B, which is called your pull-up torque. This torque available is at the point is called the pull-up torque. For a Nema B motor, this is slightly lower than starting torque, but greater than full load torque. So again, during this whole starting process, as the motor is coming up to speed, you're always above your full load torque. So the motor is going to get real hot while it's starting. You don't want to start a motor too many times in a row. And certainly large motors have to be very carefully monitored, otherwise you'll really overheat that rotor. As the speed continues to increase from point B to point C, the torque increases up to its maximum value at approximately 200% of the full load torque. This maximum value of torque is referred to as the breakdown torque. The 30 horsepower motor in our example has a breakdown torque of approximately 178.6 foot-pounds. So that's your breakout torque. So you can slowly see this curve being created from A, B to C. And then finally you get to your full load torque. Torque decreases rapidly as speed increases beyond breakdown torque until it reaches full load torque at speed slightly less than 100% of the synchronous speed. Remember I said there's a slip, right? And that's why we have that slip. So it's not quite at synchronous speed, but it's, in this example, 1.9% slip. The full load torque is developed with a motor operating at rated voltage, frequency, and load. The motor in this example has a synchronous speed of 1800 RPMs and a full load speed of 1765 RPMs. Therefore, the slip is 1.9%. So that actually gives you a lot of good information on how that torque curve is created. There's different types of torques. There's a variable torque or a constant torque, and we'll kind of talk a little bit more about those as well. Speed torque curves are useful for understanding the motor performance under load. The following speed torque curve shows 4 load examples. This motor is approximately sized for a constant torque load 1. So here you could have a constant torque load. You can actually have a variable frequency set for a constant torque load. And from 0% speed all the way up to maximum, it will stay at that constant load torque. So that's kind of cool. This motor is appropriately sized for constant torque 1 and variable torque 1. In each case, the motor will accelerate to its rated speed with constant torque 2. You can see at the top there at 175. The motor does not have sufficient starting torque to turn the rotor with variable torque load 2. So you can see if you had a variable torque load 2, it wouldn't work. With variable load torque 2, the motor cannot reach rated speed. In these two examples, the motor will most likely overheat until its load relay trips. So you want to make sure that you understand the load, the characteristics of the actual load you're connecting to the motor before you actually do it. A lot of times this is outside of the electrical engineer's expertise area. Typically a mechanical engineer would size the load and the horsepower required for that load, and then you wouldn't have a problem with this. But if you ever ran into a situation where you were overheating your motor, it might be a mismatch of the load. Starting current, also referred to as locked rotor current, is the current supplied to the motor when the rated voltage is initially applied with the rotor at rest. So it's sitting still, and then you hit it, you close the contactor, and you get this starting current, this locked rotor current. Full load current is the current supplied to the motor with the rated voltage, frequency, and load applied to the rotor up to speed. For a Nema B motor, starting current is typically 6 to 6.5 times the full load current, or 600 to 650% times full load current. Knowledge of the current requirements for a motor is critical for proper application of overcurrent protective devices. If you do not know what the starting current is, you could trip on an instantaneous situation when you're trying to start the motor and never even get it started. So you've got to make sure you set the instantaneous settings of the fuses or the breakers high enough so that they allow starting current, but then the long time values so that they protect the motor in an overload condition. Nema A motors are the least common design. We talked about that. A Nema A motor have a speed torque curve similar to a Nema B motor, but typically have higher starting currents. As a result, overcurrent protection devices must be sized to handle the increased current. Nema A motors are typically used in the same types of applications as Nema B motors. A Nema C motors are designed for applications that require a high starting torque for hard to start loads, such as heavily loaded conveyors, crushing and mixings, large flywheels, things like that. Despite the high starting torque, these motors have relatively low starting current. Slip and low torque, or full load torque, are about the same as the Nema B motors. Nema C motors are typically single speed motors which range in size from approximately 5 horsepower to 200 horsepower. Here we have a Nema C torque curve. So you have the following speed torque curve is for a 30 horsepower Nema C motor with a full load speed of 1765 RPMs and a full load torque of 89.3 foot-pounds. In this example, the motor has a starting torque of 214.3 foot-pounds, or 240% of the full load torque, and the breakdown torque of the breakdown torque here is actually 174 foot-pounds. So you can see your point A is much higher on a Nema C motor, but because of that, you have a larger inrush current, starting current or locked rotor current, but you can also start a very, very heavy load. The starting torque of a Nema D design motor is approximately 280% of the motor's full load torque. This makes it appropriate for very hard to start applications, such as a punch press or an oil well pumps. Nema D motors have no true breakdown torque, after starting, torque decreases until full load torque is reached. Slip for Nema D motors ranges from 5 to 13%, which is really kind of odd. So I don't, I guess whether they use them for punch presses or oil well pumps. And I guess an oil well pump would be like a jack, one of those big jack pumps. You can see those oil wells going up and down, up and down, up and down. So here you have the following speed torque curves is for a 30 horsepower Nema D motor with a full load speed of 1656 RPMs and a full load torque of 95.1 foot-pounds. This motor develops approximately 266.3 foot-pounds of starting torque. So this is the actual Nema D, so it just falls off. And again, that's for a oil well jacking pump type application. You don't really see them very often. A small variation in supply voltage can have a dramatic effect on motor performance. In the following chart, for example, when voltage is 10% below its rated voltage of the motor has 20% less starting torque. This reduced voltage may prevent the motor from getting its load started or keeping it running at rated speed, so it could stall. A 10% increase in supply voltage, on the other hand, increases the starting torque by 20%. This increased torque may cause damage during startup. A conveyor, for example, may lurch forward at startup, which would, whatever is on that conveyor, bottles or whatever, might all fall over. A conveyor, for example, a voltage variation also causes similar changes in the motor's starting and full load currents and temperature rise. So you want to watch to make sure your voltage is not abnormally high or abnormally low. A variation in frequency at which the motor operates causes changes primarily in speed and torque characteristics. A 5% increase in frequency, for example, causes a 5% increase in full load speed and a 10% decrease in torque. Remember, as the speed increases, the torque decreases. If the speed decreases, the torque increases. So they give you that chart here. Plus 5% variation in frequency gives you a percent change full load speed of 5% and decreases your starting torque. Standard motors are designed to operate below 3,300 feet. Air is thinner and heat is not dissipated as quickly above 3,300 feet. Most motors must be derated for altitudes above 3,300 feet. The following chart shows typical horsepower derating factors, but the derating factor should be checked for each motor. A 50 horsepower motor operating at 6,000 feet, for example, would be derated to 47 horsepower, right? So if it's 6,000 feet, you'd multiply it times 0.94. Providing the 40 degrees C ambient rating is still required. Obviously, if you go higher, your temperature is going to decrease. So here they have a 50 horsepower times 0.94 is 47 horsepower. The ambient temperature also have to be considered. The ambient temperature requirements may be reduced from 40 degrees C to 30 degrees C at 6,600 feet on many motors. However, a motor with a higher insulation class may not require derating in these conditions. So if you have an ambient of 30, you might be able to get away with 6,600 feet. If you have an ambient temperature of 40, you don't want to install that motor any higher than 3,300 feet. Open enclosures. We talked about open enclosures. They permit that cooling air to flow through the motor. One type of open enclosures, that drip-proof type, the open drip-proof, ODP. This enclosure has vents that allow air to flow through it. The fan blades attached to the rotor move air through the motor when the motor is turned. The vents are positioned so that the liquids and solids falling from different angles, as long as they're not greater than 15 degrees. So it's actually got a little angle on that vent from vertical, cannot enter the interior of the motor when the motor is mounted on a horizontal surface. When the motor is mounted on a vertical surface, such as a wall or panel, a special cover may be needed for these ODP enclosures. Should be used in environments free from contaminants. So if you've got this, a dusty environment, or a situation where you've got some maybe threads in a textile area, you certainly don't want to use an ODP because it'll suck in all the threads or the dust from sawmills and clog it up until it overheats and catches on fire. In some applications, the air surrounding the motors contains corrosive or harmful environment or elements which can damage the internal parts of the motor. So here you'd use a TENV. And we pretty much talked about this and how it works and how the motor is actually, the heat actually goes to the outer enclosure and then the heat is dissipated through those heatsink fins. That TEFC motor again, obviously it's the most common motor. It's used in Class 1 Div 2 locations. You can look that up in the NEC. That's Article 500. I think it's, I don't remember what it is. It's 501 or something. The motor is similar to a TENV motor, but it has an external fan mounted opposite the drive end of the motor. The fan blows air over the motor's exterior for additional cooling. The fan is covered by a shroud to prevent anyone from touching it. TEFC motors can be used in dirty, moist, or mildly corrosive environments. There's a problem associated with this. Let's say you've got a variable frequency drive and you're going to run it at 50% of its rating for an extended period of time. Well, if that motor is running at 50%, that means that fan is turning half speed. If it's turning half speed, you got to make sure that that motor doesn't overheat. Sometimes you have to have external fans blowing on these motors if you're running motors for extended periods below their rated speed. Hazardous duty, the XP. The hazardous duty applications are commonly found in chemical processing, mining, foundries, pulp and paper, waste management, and petrochemical industries, refineries. In these applications, motors have to comply with the strictest safety environment standards for the protection of life, machines, and the environment. This often requires the use of explosion-proof XP motors. An XP motor is similar in appearance to a TEFC motor. However, most XP motors enclosures are cast iron. In the United States, the application motors in hazardous locations is subject to the NEC and standards set by underwriters, the UL, Underwriters Laboratory, and various regulatory agencies such as API 500. But again, if you don't understand hazardous duty ratings, I suggest you watch the two DVDs. I have the DVD number 1 and the DVD number 2 that cover the NEC 500 and area classification issues. Okay, so next we'll cover the motor efficiency and motor assessment. After you've done the AC induction motors portion of this class and then you've worked on the motor efficiency and motor assessment, you'll have a very good understanding of how a motor operates, and when you understand how a motor operates, you can actually determine a lot of things about how the variable frequency drive works as well. So that's why we go through this trouble of making sure you're introduced to AC induction motors first. So here we'll talk about efficiency gains. In this little picture off to the right, you have some production unit and you have a warehouse. So you have a fixed speed motor. So really what they're saying here is this system may be viewed as very inefficient because we are locked into whatever efficiencies the motor can provide, given a somewhat variable amount of loading. So you can't really change the efficiency of this application. If the motor happened to be an alternating current AC motor, typically the following would be true. The more load on the motor, the more efficient the motor is. So as you load it up, it becomes more efficient. The higher the motor's horsepower rating, the higher the efficiency. So if you have a 200 horsepower motor, it's much more efficient than a 50 horsepower motor, and a 50 horsepower is much more efficient than a 5 horsepower motor. The higher the operating speed, the more efficient the motor. So if you try to operate this motor at a very low speed, it's not going to be very efficient. So we'll kind of look at that graph here in just a second. And here you can see at the very top you have starting at 25% of the rated load all the way up to 125% of rated load. The very top graph is your 200 horsepower motor. So it starts at 25%, you're at about 90, and then you ease on up to about 95%, and it's flatlined all the way through. So that's a fairly efficient machine. A lot of people try to say that these AC induction motors have efficiencies of 98% or higher, but they don't. Now, granted, an AC induction motor is extremely efficient when compared to like a natural gas engine or a diesel engine. You know, those aren't nearly as efficient. But if you look at the bottom part of this graph here, you see a 1 horsepower motor. So if you have a 1 horsepower motor, you're looking at 70% efficiency, and it curves, right? You can see it curves. Starts out at 25% at about 55% efficiency, and then when it hits that about 65%, it becomes 70%, and that's about as high as it can get, is about 70% efficient. It's possible you can get some really high efficiency motors. One of the first pictures that you saw when we started AC induction motors was that gold Super E Baldor motor. So Super E means super efficient. So this graph talks about constant and variable torques. So if you have a variable torque load or a variable torque drive, you can see at the very top, it's very efficient all the way throughout, even on a 2 horsepower motor. Relative to the bottom, which is motor speed. So as you increase from 0 to 100%, if you have a variable torque load, it's very efficient all the way through it. If you have a constant torque system, it's not that efficient. So you can see a constant torque system would be like, I guess the thing that comes to me is the centrifugal pump is a constant torque system. So it has more of that curve, and that's why, if you've heard that variable frequency drives offer a lot of efficiency or money that you can get back by running it at about 70% load, you can see that here. You know, 60 to 70% of the load, you're getting a lot of performance out of that machine, and you might not need it to go any higher. And that's why, if you run at about 60 to 70% on a constant torque load, you can actually get some return on investment that way. So, and then you've got the dotted line there is just a drive and motor efficiency. So it's a very straight line there. So as you increase your rated speed, your efficiency goes up linearly. 3 types of motor loads. You've got your constant torque loads. Output power varies, but torque is constant. Examples are conveyors, rotary kilns, constant displacement pumps. Oh, I apologize. I just said that before. So centrifugal pump is a variable torque load, not a constant torque load. A variable torque load is a torque varies with square of operational speed. And then your centrifugal pumps and your fans. And the variable torque load is exactly the one that you actually see some payback on it, infinity laws or affinity laws. You won't see a payback on a constant torque load or a constant power loads. Constant power loads are torque changes inversely with speed, and you see this on large machine tools like big lathes and stuff like that. And there's different types of electrical motors, and here's a classification of these motors. So you have an AC motor on the left and a DC motor on the right. We don't really see a lot of DC motors anymore. When I first started, there was a lot of them out there, big 100 or 1,000 horsepower DC motors. Powered by 750 volts. If you rectified 480, you'd get about 700 and some odd volts DC. That's why they use that voltage. You can have separately excited systems where you have a separate excitation system and you can control it, or you can have self-excited systems, and a lot of times that's what we use, is self-excited. You can have a series motor, a compound motor, or a shunt motor, or some combination of those. Alternating current motors, AC motors, you have either a synchronous motor or an induction motor. In the induction motors, you have 3-phase and single phase. So primarily what you'll run into on variable frequency drive applications are induction 3-phase motors. Synchronous motors are used in special applications, believe it or not, where you have super high speed. So if you have a 2-pole machine, which would be 3,200 RPM synchronous in sync speed, those machines, if they're designed properly, they can go way really high, like 6,000 RPMs, and they can be like 10,000 horsepower. You see that the reason they're able to do that is because
they control the excitation system. So by increasing the excitation system, you can actually, and increasing the frequency of the variable frequency drive, you can overspeed a synchronous motor, where you can't do that to an induction motor. An induction motor would slip at some point in time. So you start to see a lot of these large synchronous motors, 10,000 horsepower and higher, where they actually overspeed them and replace large turbines. Here's a DC motor components. You have basically the field pole, the north pole and the south pole, and it receives electricity to form a magnetic field. The way I kind of think of a DC motor is it's a inside out, right? It's like a synchronous motor, but it's reverse. So the poles are actually on the stator part of it, and the armature is kind of on the rotor part of it. And if you think about it like that, you can actually kind of get the feel for it. It's kind of reverse of each other. And you also have like commutating, you have commutators and these carbon brushes and things like that. And because of this, you really don't want to put this in a class 1 div 2 area, because the brushes, the carbon brushes that run on those commutator bars actually arc and spark. So the nice thing about DC motors is they are very, very easy to control the speed. All you have to do is increase and decrease the DC voltage on the armature, and it will increase and decrease its speed. The armature is a cylinder between the poles. So again, see, it's the cylinder between the poles. So the field poles are the stator portion of this, and the armature is actually the rotor. So it's a cylinder between the poles. Electromagnet, when current goes through, linked to the drive shaft to drive the load. So to get to the armature on this motor, you actually have to get to the shaft through those commutator rings. We'll show that in a little bit. So yeah, you have the commutator, which overturns the current direct into the armature. So basically, you have these carbon brushes riding on the commutator, and there's usually 2 of them. Might be multiple, depending on the actual current load. And you can increase and decrease the DC voltage on the commutators, which in turn drives that armature, which causes that motor to rotate. And if you increase the voltage, the motor will go faster. If you decrease the motor will go slower. Years ago, they used to use these exclusively on paper mills and steel mills, because they could put a line of DC motors together and accurately control that conveyor or that process. Now, of course, with the VFDs and the advancements in them, they've replaced them all. So on your DC motor, you have speed control without impact of power supply quality, changing armature voltage and changing the field. So by adjusting the armature voltage and changing the field current, you can actually increase and decrease the speed of that motor. Restricted use, few low to medium speed applications. They have to be clean areas, and they have to be non-hazardous areas. So, like I said, the non-hazardous is because that carbon brush arcs and sparks, and so you'll create an arc and spark and blow up a class 1 div 2 area or a class 1 div 1 area. They're very expensive compared to AC motors, but in their heyday, they were the way to go. You might see these in traction type trains and stuff like that, or traction. Here's a DC motor construction. So again, you see the poles, and then you see the rotor winding, which is the armature, and then you see the commutator, and then you see the brushes off to the left, and then finally you see the bearings and a fan. So as this motor increases and decreases in speed, that fan changes its speed as well. If you're running it at a low speed, then typically what you want to do is you want to supply it with a separate source of air so that it can stay running. And you'll see that a lot on larger motors. They'll actually have a big blower on top of them, run with a AC 3-phase induction motor, just to keep the machine from cooling, to cool it properly. So here you have typical AC motors. Here you have electric current reverses direction. 2 parts, stator and rotor. We talked about that. You have a stationary electrical component. Your rotor rotates the motor shaft. Speed difficult to control. It's not that much. It's not as difficult anymore because you have the variable frequency drives. There's two types, the synchronous motor and the induction motor, and you can see that that picture right there has a DC component to it. So you would see a DC component excitation system on a large synchronous machine. Basically what you do is you inject the DC current into there and into the rotor, and the rotor in turn creates a magnetic field. We'll talk a little bit about that later, but those work really well for large applications. So if you hook this up as a generator, you would start your large diesel engine or your natural gas engine driving the shaft. Once you came up close to operating speed, you would start increasing your excitation current, increasing the DC into the rotor. As you increase the DC into the rotor, the voltage would increase. If for some reason you tied this to utility, tied it to the actual grid, what you would do is you'd first pull it in sync with the 60 hertz by increasing and decreasing the speed of the machine. You would actually do that by, like a gas pedal. If you stepped on the gas, you'd increase the speed of that machine. If you decrease the gas, you would decrease the speed of the machine. And obviously the speed is directly related to the frequency of that generator, if this was a generator application. So what you would do is you would use a governor, a load governor, and it would actually sync to utility. Once it got into close to utility or slightly slower, then you would go ahead and close the breaker into it, and then once you locked into utility, utility would take over. And basically, if you increase the excitation at that point, you cannot change the speed anymore because the engine is not big enough and strong enough to control the speed. But if you increase the excitation system, you're changing VARs, right? So you can actually change how much VARs go out of this machine or how much VARs come into this machine. And if you in turn increase the speed of the rotor, you're actually changing the kilowatts, how much kilowatts is being exported from this machine. So if the engine, governor, or load increases, or the governor increases the speed of this machine, and it maintains its excitation circuit, then you will deliver kW. If you decrease the speed of this machine, then you're actually receiving VARs at that point. You're no longer delivering kW, and you can actually go into a reverse power condition, which would be an IEEE function on relaying a 32 function, which is reverse power, and you can destroy that machine. So we don't really talk in this course. I didn't talk about relay programming and relays, just understanding of like 5051s and stuff like that. But it's possible that I will do a course like that. Here you got your AC motors, synchronous motors, constant speed fixed by system frequency. So if that synchronous motor is tied directly to utility, then utility sets the speed of the machine, right? So the DC excitation system is a low starting torque suitable for load applications, can improve power factor. So if the synchronous machine is linked to utility and it's a motor, right, so it's driving a load like a big compressor, you can increase the excitation current on that synchronous machine, and you will go into more leading power factor. You'll actually add capacitance to the system. This is equivalent to a capacitive type, like a capacitor on a utility pole. Years ago, this was the most common use or way that they control power factor because it was the most robust system. Nowadays, capacitors have come up the curve and they can withstand these jolts in the system, so they just add capacitors instead of large synchronous machines. However, you will see, like if you go into a refinery, if they've got a large compressor and a large synchronous motor, they'll actually increase and decrease that power factor by increasing and decreasing this excitation current. So here again you have synchronous speed, Ns. So Ns equals 120 times the frequency divided by the number of poles. And we've seen that before, and we worked with that equation. The only difference is an asynchronous machine doesn't have slip like an induction motor. So AC motors, most commonly used in the industry, I think there was something like 70% of them are used in the industry. Advantages, they're simple design, they're very inexpensive, they have a high power to weight ratio, They're easy to maintain, and the direct connection to the AC power source. So you don't have to go into an armature or into brushes or commutators or something like that. You go directly into that stator of that AC machine, and it's easy to connect right to the pecker head. A single-phase induction motor, it has one stator winding. It uses single-phase power. It has a squirrel cage motor, requires device to start the motor. That device, obviously, we talked about that. That is a compressor, right? So, I mean, a capacitor. And you'd have a start capacitor, and then once it comes up to speed, the start capacitor would come out of the circuit. And you may or may not have a run capacitor, and sometimes you can have actually both the run and start capacitor. Usually these motors are very small, 3 to 4 horsepower applications. You see these a lot in your house, your household appliances, such as fans, washing machines, and dryers. If for some reason you have a fan that just sits there and hums when you try to start it, if you were to stick a pencil in there and spin it up to speed, it would actually start. If you saw that and you saw that little hump on the motor indicating that it has a capacitor and it comes up to speed and stays there, then it just needs a new capacitor. Here's a 3-phase induction motor. 3-phase supply produces magnetic field. That 3-phase supply actually rotates at synchronous speed. That's why you don't need that starting capacitor for a 3-phase induction motor. Also, I wanted to tell you that a capacitor and a switch are the most common things to fail in an electrical application. So be that switch a little relay type switch or a circuit breaker or something like that, switches fail, and so do capacitors. They fail. So by removing the clutch, the capacitor clutch, where they spin it up on an induction motor, by removing that and the capacitor, they've actually made the 3-phase inductions much more robust. Squirrel cage or wound rotor design, and we talked about that before. Self-starting, you don't need any special capacitors or ability to start this thing. High power capabilities, you can, for a 480 volt system, you don't want to go any higher than about 200 horsepower. But if you go over 480, like 4160, a medium voltage machine, well, you can certainly go even higher, right? Much, much higher. 4,000 horsepower induction machines, not uncommon. If you want to go into the 10,000 range, maybe you'd go to 13.8 kV or 12470. These motors, there's a third to hundreds of horsepower applications, literally thousands and thousands. Yeah, I don't know how many motors there are out there. Pumps, conveyors, compressors, grinders, and again, it's 70% of the motors in the industry. So it's a huge, huge impact. If you just increased the efficiency on these motors somehow, and you actively went after that market, you could make a big impact on somebody's, bottom line, on their return on investment, because you can increase the efficiency. And a lot of these old industries and these refineries, they actually rewind those motors as opposed to buying a new high efficiency motor. So if the voltage doesn't change, you might consider just buying a brand new high efficiency motor with the same frame size. You'll actually have a better payback on that. You'll actually see a positive payback in 18 months or so. You'll actually start getting a return on investment. I'm going to go ahead and talk a little bit about a slip ring. The only types of motors induction motors that have a slip ring are like the wound rotor inductions. And the slip ring is an electromechanical device that allows the transmission of power and electrical signals from a stationary to a rotating structure. A slip ring can be used in any electromechanical system that requires unrestrained, intermittent, or continuous rotation while transmitting power and or data. It can improve mechanical performance, simplify system operations, and eliminate damage prone to wires dangling from movable joints. That's just basically a slip ring, right? And you'd see that with carbon brushes. Certainly on a DC motor you would see this. On a large AC synchronous machine, sometimes you see carbon brushes, but not as often. Usually what we do when we make large AC synchronous machines is we wire that to a permanent magnet generator type thing, or just to a device where you can transmit it without actually having to hookup brushes, but every once in a while you do see some of these with brushes. I've seen some large 4100 or 4500 horsepower synchronous machines with large brushes, and they have to check them from time to time and stuff like that. But at the time, that's probably the best way to do it. So AC motors, induction motors, they have slip and speed and slip. Obviously, in an AC induction motor, the motor never runs at synchronous speed, but at a lower base speed. The difference is called the slip. Install slip rings to avoid this. You can actually install a slip ring and decrease the amount of slip. So you can calculate your percent slip equals NS, which is your synchronous speed in RPMs. So if you had a 4-pole machine, you would see 1800 RPMs. If your base speed in RPMs, let's say hypothetically it was 1764, then you would subtract those two numbers, divided by 1800, your synchronous speed, multiply that times 100, and you would know your percent slip. We've gone over a few equations like that, but that'll help you understand how to get that percent slip if you need it. Efficiency of electric motors. Motors lose energy when serving a load. This is a neat little graph right here because everything electrical falls into this. If you were to treat that motor like a black box, every electrical device falls into this. You have some input power and you have some output power. Input power is always higher than output power because you have losses. And the losses are translated into heat typically, right? So here you have different losses in an AC induction motor. You have fixed losses, you have rotor losses, you have stator losses, you have friction and rewinding losses, and then you have stray load losses. So you can actually calculate all these different losses and solve them or fix them or compensate for them. Certainly the rewinding is the easiest thing to fix because rather than go back to a rewound motor if it ever fails again, just go ahead and replace it with a brand new high efficiency induction motor and you save a lot of money. So factors that influence efficiency: the age of the equipment, capacity of the equipment, the speed of the machine, the type, the temperature, the rewinding, and the load. And we talked about that before, you know. As you're increasing the speed of the machine, it changes how your efficiency is. Motor part load efficiency designed for 50 to 100%. So if you're running a motor and you've got this percent full load, you don't want to buy a 10 horsepower motor and only run it at 3 horsepower. That would be a very inefficient thing to do. You can do it, it's just wasting energy, and a lot of people do it just because they want to standardize on a certain size motor, but it's a very inefficient when you do that. Most efficient at 75% load, and then rapid drop below 50%. So if you're running a motor below 50%, you are losing money. I mean, it's just a big waste of money. It might last forever, but it's not the most optimum area to run it. And you can see in this graph, it says, acceptable short period load ranges from 20% to 120%. Certainly on the low end, you don't want to do it because you're just wasting energy. Certainly you don't want to run on the high end of it because you'll start losing life, right? Because if you overload that machine, it'll burn up. Your acceptable operating ranges are anywhere from 50% to 100%. And then optimum would be 60 to 80%. And that's where you would run a fan or a centrifugal pump, is between that 60 and 80% loading. Motor load is an indicator of efficiency. So if you wanted to try and figure out what that efficiency was, you could actually determine it with this equation. So here you have load equals the three-phase power in kilowatt, the PI, times the motor operating efficiency in percent, times the horsepower, the nameplate rating of that machine, and that equals the actual output power as a percent of rated power of power, the load. So you can actually back into it. You could reverse this equation around, right? And if you had like a meter, you can measure the kilowatts, and then by measuring the kilowatts, you could actually look at you could calculate the efficiency of this machine. You could back into that efficiency calculation. which is not a bad idea, especially if you're walking around as an electrician and you're just trying to figure out if there are any improvements in efficiency that can be made. You can use this equation to do it. Three methods for individual loads. This is motor loads. You can do an input power measurement, the ratio input power and rate power at 100% loading. You can take the line current measurement, compare measured amperage with rated amperage. And then you can use a slip method, compare a slip at operation with slip at full load. So these are different methods of determining the motor load. We'll go over a few of these. So here you have your input power measurement, 3 steps for 3-phase motors. So what we're trying to do is figure out our kW. So we know the volts, we measure the volts, we look at the current, we look at the power factor, then we multiply times the square root of 3 divided by 1000 gives us the actual kW. So you can measure that. Determine the input power. Again, the same thing, you can actually back into this. There's a lot of things like a fluke kilowatt meter that can quickly measure this. Then you've got input power measured. So here you've got your horsepower times your 0.457 divided by NR, which is your efficiency at full rated load. So then you've also got your load equals PI divided by PR, where PR is the input power at full rated load in kilowatts, and then you multiply it times 100%. Input power measurement, determine the rated power. So here we have the horsepower times 0.7457 divided by the efficiency at full load. Here we have input power measurement, determine the rated power. This is step 2. So you can determine the rated power. Then you determine the percentage of the load. You can mark through that. And the result is if you have significantly oversized and underloaded. So let's say you have a machine that has a 20 horsepower machine, it's rated 20 horsepower, but you're only running 7.5 horsepower. The way to really solve this problem is to replace with a more efficient, properly sized motor. So you'd probably want to go to, if you're 7.5 horsepower, you'd probably want to go to a 10 horsepower motor, and while you're doing that, go ahead and replace it with a high efficiency motor, and you would save a lot of money that way. Moderately oversized and underloaded, replace with more efficient, properly sized models when they fail. So you don't have to really act on this real quick. It's not a big game changer, but if you have a result where you're moderately oversized and you're underloaded, when it fails, don't rewind it. Go ahead and replace it with a more efficient, properly sized motor. Properly sized but standard efficiency. Replace most of these when energy efficient models when they fail. So this would be your game plan for your facility, right? You just go through, you understand all these different loads, how those machines are loaded up, and then you put it in your budget to say, we know this motor fails, every 10 years or 20 years or whatever, so we're going to go ahead and plan on that we're going to replace that one with a high efficiency motor then. Energy efficiency opportunities. Obviously use energy efficient motors. Siemens sells a lot of them, Baldor, just about every manufacturer, Reliance, they all sell them. Reduce underloading and avoid oversized motors. And again, a lot of people used oversized motors just because they wanted to have a standard motor on the shelf, and so they would actually maybe use a slightly oversized motor just so they didn't have to carry multiple motors in stock, which is not a bad idea. And maybe the cost of carrying motors in stock is a bad idea, and it'll drive cost up. Size to variable loads, improve the power quality. And what we mean here is if you have an imbalance in current or an imbalance in voltage, you can actually decrease your energy efficiency that way. So you want to improve your power quality. Rewinding, you don't really want to do rewinding. I know a lot of people do it because it's cheaper, but obviously it's a better idea if you don't and just move to an energy efficient motor. Power factor correction by capacitors. That's a good idea. Just make sure that if you do add power factor correction capacitors, that you realize that the incoming current will drop, right? Because if you're running at a power factor of, let's say hypothetically it's 0.8 power factor, and you add enough capacitance to increase that power factor to unity or slightly below unity, which is more of a maybe 0.95 or 0.98 power factor lagging, what you'll notice is the input current drops, right? The kilowatt never changed, so there's really no savings in kilowatts, but the input current drops. And so you have to adjust your overload settings and your current protection downstream. Don't change your wire size. You must always size your wire size for the full load amps of that motor. Don't just adjust it because you've added power factors, because I pointed out capacitors fail, right? So when they do fail, you don't want to have a overheated situation in your conductors. So what will happen is when they fail, you might get into a situation where you trip your contactor, your overloads, and then you can go double check those capacitors. You want to improve your maintenance. You want to make sure these motors are clean, that they're not sucking in dirt, that everything's rotating properly, that you properly grease the bearings, because you'll have friction losses in the bearings, so you want to make sure they're properly greased on the proper rotation. And then you can do speed control of induction motors. And this is the speed control of an induction motor. Obviously, if you do that, you can save some money only on the centrifugal pumps and the fans. Any other load, you won't save money that way if you change the speed of the motor. You might have to control the speed of the motor for process reasons. That's a whole other story. Use energy efficient motors, reduces intrinsic motor losses. Efficiency is 3 to 7% higher. 7% of a large motor like a 200 horsepower motor is a significant savings, and you will get a rapid payback on that. Wide range of ratings, more expensive but rapid payback. So they cost a little bit more to manufacture and to buy, but the payback is so high that it's worth it. So you can see motor rating kW. If you have a let's just grab an easy one of 5 kW, you're at 80%, a little over 80% efficient. But when you move up into a high efficiency motor, you're more like 87% efficient. So you might see a 5% increase there. Best to replace when existing motors fail. So don't just arbitrarily go out there and start replacing motors if they're not failing. When they fail, have a system and plan to replace them with higher efficiency motors. And these talk about the power loss area. So your first fixed loss is iron. What they'll do on an energy efficient motor is they'll use that thinner gauge iron. Lower loss core steel reduces eddy current losses, and we talked about that. When they stack that stator, they actually use thin gauge metal and laminations, and they're insulated from each other, and they stack them. So you'll lose, if you don't do that and you use thicker plates, you'll actually have higher core steel losses, and that's due to those eddy current losses. Longer core adds more steel to the design, which reduces losses due to lower operating flux densities. So if you have a short, compact machine, it's not going to be as efficient as a very, if you're 65% longer or, something like that. Stator I squared R losses. This is your standard, you've got X current flowing through the line. You have a fixed resistance. So power equals I squared R, right? I raised to the power of 2 times R. And that's where you would have a lot of losses. So it uses more copper and larger conductors, increases cross-sectional area of stator windings. This lower resistance R of the windings and reduces losses due to current flow. You can do the same thing by oversizing your conductors feeding the motors, right? So you can reduce a little bit of your I squared R losses. Rotor losses, your I squared R rotor losses, use a large rotor conductor bars, increases size of conductor sections, lowers the conductor resistance and losses due to current flow. So they actually increase the diameter of those conductor bars that create that squirrel cage in the rotor. Friction and winding, use of low loss fan designs reduces losses due to air movement. So believe it or not, there's a lot of losses in friction and winding. So if the design has a big, heavy old fan, you could actually have some drag. And then you've got your stray load losses. Use optimized design and strict quality control procedures. Minimizes stray load losses. Reduce underloading. Reasons for underloading are large safety factor when selecting motors, underutilization of equipment, maintain output at desired levels even at low input voltages, and then higher starting torque is required. So you want to reduce underloading, right? So you don't want to have a larger machine on a smaller load, and these are some of the reasons for underloading. Reasons for underloading, large safety factor when selecting motors. Again, a lot of people just say, you know what, I'm not sure if that load's 8 horsepower or if it's 10.5 horsepower. I think I feel comfortable going with a 15 horsepower motor. Well, you do that and you are going to have a large safety factor. However, you're going to have very inefficient design. Underutilization of the equipment. Obviously, you will underutilize that equipment if you oversize it. Maintain outputs at desired level, even at low input voltages. High starting torque is required. Consequences of underloading: increased motor losses, reduces motor efficiency, reduced power factor. So these are all the things that happen. Replace with a smaller motor. If motor operates at less than 50%, then yes, you want to replace it with a smaller motor. Not if the motor operates at 60 to 70%. 60 to 70% is, or that 60 to 80% is that optimum range. So you don't want to change it out. But what you don't want to do in a situation like that is whenever it fails, you just replace it with a high efficiency motor. You can operate in a star mode. What that means is you have a delta. You've got these, I didn't really talk about how these windings work, but you can go into a triangle type shape where you would connect in a delta mode, and then you can go into a Y mode. So you can operate in a star mode. If motor consistently operates at less than 40%, inexpensive and effective way to do it. Motor electrically downsized by wire reconfiguration. Motor speed and voltage reduction, but unchanged performance. So I guess the best way to describe this is a delta to Y starter, right? Or a Y to delta starter. If you run the motor in a delta mode, it will have more voltage across each winding, so it'll have more current flowing through it, which means you'll have higher flux, right? So you're running at full speed as fast as that motor can run. If you switch to a Y mode, then it's going to be running at about, I don't know, maybe 50% of its speed. So you could actually do that and actually reduce the, it would actually run not 50%. Yeah, it's actually it reduces the current that you're able to operate at that point. So that's a common method of doing a reduced voltage starter is to go star to delta. So if you just ran it star, you might be able to get away with it. Sizing to variable loads, motor selection based on the highest capacity load, expensive and risk of underloading. Don't do that. Yes, slightly lower than highest load, occasional overloading for short periods. So that's where you want to be. If you're dealing with variable loads, you want to do slightly lower than the highest load, occasional overloading for a short period. So you allow it to go into overloading as long as it doesn't happen very often. Sizing for variable loads again. You want to avoid the risk of overheating due to extreme load changes, frequent long periods of overloading, and inability of the motor to cool down. So you want to be cognizant of that and make sure you don't run into those situations. And that's exactly why people get, they're like, you know what, I just don't want even to risk this. I'm just going to oversize that motor significantly. So they do it, so they'll actually oversize it. Improve your power quality. And we talked about this before, but you don't want to have a voltage imbalance or unbalance or a current imbalance. And if you do have those issues, you'll have major problems. Motor performance affected by poor power quality, too high fluctuations in voltage and frequency. Sometimes you'll see in remote areas where you have a factory, when those factories turn off, the voltages start to rise because these factories are no longer running. And so you can actually have poor performance on an AC induction motor in those conditions. a voltage unbalance, unequal voltages to three-phase motors. So if you have line to ground or line to, phase A to neutral is less than phase B and C to neutral, then there's a problem with that. So here we have an example. We have an unbalanced percent of 30% in example 1. Example 2 is 2.3%. I'm sorry, it's unbalanced is 0.3%, and the example 2 is 2.3%. And in example 3, you have 5.4% imbalance, and you have an unbalanced in current percent of 0.4 in example 1, 17.7% in example 2, and 40.0% in example 3. So you would have a temperature increase in degrees C. Of example 1, you have no impact, no temperature increase. But example 2 and 3, you have 30 and 40% temperature increases in that machine. If that exists, you will overload that machine. You'll overheat it, and you'll decrease its life by half at least or more. You'll have motors failing all the time. Another problem with imbalanced voltages or currents is you can have circulating currents. What will happen is if phase A, B, and C are not balanced in and about the same, you'll actually all of a sudden have these stray currents flowing through the system, and you could have premature bearing failures, and we'll talk about that later as well. But that's a good thing to know. One of the drawbacks about a VFD is the pulse width modulation on the output of that VFD. It's inherently going to have a voltage and current imbalance all the time. Although it's not a big imbalance, it will have a imbalance. When that happens, you do have stray bearing currents, and you can actually pit your bearings and destroy them prematurely. We'll talk about that later. Improve your power quality. Keep your voltage unbalanced within 1%. Balance single-phase loads equally along 3 phases. So when you have a single-phase panel, you want to make sure, or even a 480-volt system, you want to try and balance those loads so that you don't have this unbalanced condition in your facility. You want to segregate your single-phase loads and feed them with a separate line to line/transformer. So if you separate all your single-phase loads and then you go with a separate transformer, you can actually isolate those from your 3-phase systems and not have problems. Rewinding, sometimes 50% of the motors out there are rewound. You see it all the time. The reason they can reduce motor efficiency is because these rewinders, they don't really design it. They don't know how to design it exactly the same way. Maybe there's no drawings on the original motor design, and so they do their best job at rewinding them. Granted, they might work like a champ. They just have different operating characteristics. To maintain your efficiency after rewinding, make sure you use a qualified certified firm. Maintain the original motor design, which can be a challenge if there's no documentation on that motor. Replace 40 horsepower and greater 15-year-old motors instead of rewinding. So if it's greater than, if it's 40 horsepower or higher or older than 15 years, just don't rewind it. Go ahead and replace it with a high efficiency motor. Buy new motors if costs are less than 50 to 65% of rewinding costs. So there is a big factor here. You need to take that in consideration. So you want to look at the rewinding costs, and then you want to look at your cost efficiency gains, your savings. And if you don't have a return on investment within less than probably 3 years, you certainly want to go ahead and use a rewound motor. But it's a shame, but it is what it is, right? You gotta watch the dollars return on investment. Improve your power factor. Use capacitors for induction motors. Obviously, we talked a little bit about that. You're going to reduce your input current. You're going to change your VARs, right? And you want to make sure you adjust your overcurrents when you do that. And you always want to size your feeders for worst case conditions, which would be the full load amps of the motor. Benefits of improving power factor: you reduced your kVA, reduced losses, obviously the I2R losses. Improved voltage regulation because your voltage is now raised because of the capacitors. It actually increases the voltage. Increased efficiency of plant electrical system.
Capacitor size not greater than 90% of no load kVAR of the motor. So you don't want to oversize those capacitors where you go into a situation where you're going to a leading power factor. You want to shoot for just slightly less than unity. You don't want to go into a leading power factor. 80% lagging is no better than 80% leading. You still have losses, right? So what you want to do is you want to shoot for like 98% or 95% lagging power factor. Maintenance. Checklist to maintain motor efficiency. Inspect motors regularly for wear, dust, dirt, things like that. You want to check the motor loads for under or overloading. You want to lubricate the bearings properly. You want to check for alignment of the motor and the equipment. You can, if you go out of misalignment, you can have high vibration issues and cause that machine to prematurely fail. You want to ensure supply wiring and terminal boxes are properly sized and installed. And then you want to provide adequate ventilation. So that's a well-maintained machine. And, you know, in a refinery, you could literally have a thousand motors, and what you need to do is just carefully step through and create a spreadsheet of some sort and you know, a load list and monitor all these loads and make sure that you're maintaining them on the proper intervals. Probably once a year would be optimal, that you could take a motor and make sure that it's operating properly. But you could also do a monthly walkthrough to make sure nothing's changed on them. Speed control of induction motors. You can do multi-speed motors, limited speed control, 2 to 4 fixed speeds. On wound rotor motors, drives, a specifically constructed motor has a variable resistance to control the torque performance, and typically that's less than 300 horsepower, most common. Speed control of induction motors, and that's the heart of this course, is variable speed drives or adjustable speed drives, also called inverters. Several kW to 750 kilowatts. Change speed of the induction motor can be installed in existing systems. Reduces electricity by 50% in fans and pumps. This may or may not be true, and I'll show you later, because sometimes pumps don't quite get the results that you would expect. But we can go over that. Convert 50 hertz incoming power to variable frequency and voltage, and change the speed. So if that's for overseas, obviously if you're in the United States, you would convert that 60 hertz incoming power to variable frequency and voltage, and you can modify the speed. You can actually ramp it up. And there are 3 different types of VFDs. Here you have a speed control of an induction motor. You can have a direct current drives. Oldest form of electrical speed control consists of DC motor, field windings, and armature. Controller regulates the DC voltage to the armature that controls the motor speed. Tach generator gives feedback to the controller. So this was the way they used to do these, is they'd have these direct drive current drives, and they'd have a feedback mechanism where they have a tach generator, and it would give them the exact speed of the machine. And so they could increase and decrease the field windings voltage and also the armature voltage, and they could accurately control that speed very, very accurately. It was phenomenal how well they could control this, and easily you could control, you know, a conveyor of 100 DC motors all simultaneously and be just spot on. Nowadays, variable frequency drives do this with a variety of different methods, which we'll talk about later. Something we didn't really elaborate on too much was synchronous machine construction. So here you see a large synchronous machine. What you see is the actual rotor of that machine. You can see that there's poles, individual wound poles. So here, I'm just going to count a few of them here. You got 1, 2, 3, 4, 5, 6. That could be a 10-pole machine. It's a very large machine. And off to the left there, what you have is brushes, commutator brushes. So you can actually increase and decrease the DC flux going into that rotor, and you'd want to do that. First, to get this motor started, what you would do is you would clamp that field to 0, right? You would short all the rotor windings. Sometimes they do this with a SCR type crowbar circuit. Other times they just flat out short it out with a mechanism. And then once it starts, it actually starts like a large synchronous, large induction machine.
Once it comes up to speed, you release that that short, and then you apply your field, and then you can control the armature voltage, the voltage going to your client. AC rotating machines, you have synchronous generators, the primary source of electrical energy throughout the United States. Synchronous motors used as motors, as well as power factor compensators or synchronous condensers, and we talked about that. These large 4,500 horsepower synchronous motors driving compressors in refineries, you can increase and decrease the excitation current on that synchronous motor, and you can change the power factor. It becomes more capacitive. An asynchronous motor is an induction machine. Induction motors most widely used in electrical motors, both domestic and industrial applications. And you can use an induction generator due to the lack of a separate field excitation. These machines are rarely used as generators. Years ago, there was a company called Power Strategies, and I worked for Waukesha Pierce Industries building natural gas machines connected to synchronous generators, or natural gas machines connected to large aerial compressors. One of the designs by that Power Strategies was an induction generator. It was an induction motor, actually. And what we did was we connected it directly to utility, and the gas source was waste gas off of landfills. So what we did was we allowed the generator to start, or the motor to start, by closing it on utility, and it was like a 25 to 50 horsepower motor. It would spin up the Waukesha engine up to rated synchronous speed. Once it did that, and the Waukesha engine had gas available, it would start. It would actually start. So you'd use the induction generator motor as the starting device to start the actual synchronous machine, or the Waukesha machine. Once it started, the gas supplied it, and then it oversped just slightly over in sync speed. So it was a 4-pole machine. What you want to do is run it at no higher than 62 hertz, certainly about 61 to 61.5 hertz. And then by doing that, you could actually export kilowatts, right? You could actually run the gas engine slightly faster than synchronous speed. However, you can see here that it does not have that separate field excitation system. So you need to supply VARs, right, to this model. And the way you do that is connect a delta connected capacitor situation, and what that'll do is it'll supply the VARs and excite that induction generator and allow it to operate properly. So that's a pretty neat design. Synchronous machines, unlike induction machines, the rotating air gap field and the rotor rotate at the same speed, called synchronous speed. So again, that outer field, the actual stator, rotates at synchronous speed, right? That magnetic field, and the rotor actually is locked into, it's in sync with that synchronous speed. If for some reason it falls out of sync, the current rises radically, power factor changes, and you need to get off the line if that happens. Synchronous machines are used primarily as generators of electrical power, called synchronous generators or alternators. You can see, well, you'll see in the next slide, there's a large generator used for a, probably, utility of a city's utility. There are usually large machines operating, generating electric power at hydro, nuclear, and thermal power stations. In Texas, you see a lot of these switched over to natural gas because we have an abundance of natural gas. So natural gas burns real clean. You can't even tell hardly that it's even running. Very quiet machines, very efficient machines, and they don't pollute the environment. I would say that probably, this is 2013. By 2023, you're going to see almost every one of cogeneration units throughout the United States being run off natural gas, because there is such an abundance of natural gas in the United States because of all this fracking. So applications as motors, you can have pumps and generating stations, electric clocks, timers, and so forth, where a constant speed is desired. Synchronous machine, here you have a large picture of a 2-pole round rotor generator and exciter. So here you have a
Very, very large machine. I don't even know how large that machine is, but you can tell it's very large. Um, and it has a separate excitation system. So a two-pole machine would rotate at 3,200 RPMs. If it was 60 hertz, it would rotate at 3,000 RPMs if it was 50 hertz. Synchronous machine, here you have an example of the actual diagram. So if you look here, the stator is the ring-shaped laminated iron core with slots. So the stator with laminated core, so you can see A phase, B phase, C phase, A phase, B phase, C phase. And C phase is green, B phase is blue, and A phase is red. And these windings actually fall into these slots, right? They snap into these slots. And designing these three-phase machines and just synchronous or just any kind of transformer or induction motor or a synchronous machine is more of an art than it is a electrical feat. It is, you see a lot of mechanical engineers that design these. I used to work for a large generator testing facility, one of my first jobs when I came out of the Navy. And I really was excited, and I thought there'd be a lot of electrical aspects to this, but there really wasn't. The only thing you could really do is maybe do some testing. You could certainly do some of these calculations, but most of that was already done. It was cookie cutter, and it wasn't as fun as building like a large UPS or something like that. So you have three-phase windings are placed in the slots of the stator. The round solid iron rotor with a slot. So the rotor here actually has slots as well. So you snap them into the slots as well. And a single winding is placed in the slots. The DC current is supplied through the slip rings. So the DC current is B, right? And well, let's see, that's A. No, that's the actual AC waveform. I don't see where that DC slots are, but you get the idea. Round rotor machine. That's a very long machine, but you can see that extended length, and this is probably a two-pole machine or so. Big, big machines, right? Maybe a four-pole. Looks like could be a four-pole. I can't tell. Synchronous machine, you have your rotor in the middle, so you have a north and a south pole. That's what it creates. You can have multiple poles, right? But here you have a two-pole machine. A two-pole machine would have a north and a south. The stator has a laminated iron core with slots and three-phase windings placed in the slots. The rotor has a salient poles excited by the DC current, and the DC current is supplied to the rotor through slip rings and brushes. So that's a typical synchronous machine. Here's a good picture of the rotor machine. So that smaller one on the top left, you see that's 1, 2, 3, 4, 5, 6-pole machine. And if you have a 6-pole machine, you can calculate the RPMs. I think that equates to 1,200 RPMs on a 60 hertz system. Synchronous generator principle of operation. From an external source, the field winding is supplied with a DC current. So basically, as you increase the DC current, your flux on that rotor increases and decreases. The rotor field winding is mechanically turned, rotated at synchronous machine. So the prime mover, be it a water wheel, gas turbine, or steam turbine, turns the rotator at synchronous speed. The rotating magnetic field produced by the field current induces a voltage into the armature or stator windings. The frequency of this voltage is in synchronism with the rotor speed. So you can actually, this would be like a generator, right? And so you have A, B, and C, which are 120 degrees displaced from each other. Parallel operation of synchronous generators. Generators are rarely used in isolated situations. Most commonly, generators are used in parallel, often massively in parallel, such as in a power grid. The following steps must be adhered to when paralleling a generator to a grid. When adding a generator to an existing power grid, the RMS line voltage of the two generators must be the same. So you match the line voltages. The phase sequences must be the same. What that is A, B, C, or C, B, A. If you're tying generator 1 and generator 2 together, you want to make sure they all have the same phase sequence. Usually it's A, B, C. but it could be reverse of that. One of the things I wanted to mention here is on an AC induction motor, if the motor rotates in one direction and it happens to be the wrong direction, then you can just swap any two phases, swap B and C or swap A and B, just any two of them, and that motor will rotate the opposite direction. Phase angle of the corresponding phases must be the same. So you want to make sure that these machines are actually in phase or slightly really close, and the frequency must be the same. You want to make sure they're both at 60 hertz if it's a 60 hertz system. You sometimes want to have one slightly lower than the other if you're paralleling it, and then once you actually close in that generator, it'll pull itself right into synchronous speed. Again, synchronous speed is calculated by NS is the synchronous speed in rotations per minute. F is the frequency in hertz, so it'd be 60 or 50 hertz. So it's 120 times 60 divided by the total number of poles, and we've talked about that. We talked about slip and slip speed. The slip S of an induction motor is the difference between the synchronous speed and the rotor speed, expressed as a percent per unit of the synchronous speed. The per unit slip is given by the equation S is the slip, the NS is your synchronous speed, the NR is your actual rotor speed divided by your synchronous speed. A little recap on that. We're almost done with these motors, and then we'll finally move into motor controllers. Voltage and frequency induced in the rotor. The voltage and frequency induced in the rotor both depend on the slip. They are given by the following equation. F2 is the frequency of the voltage and current in the rotor. S is the slip, and F is the frequency of the source connected to the stator, usually 60 hertz. E2 is the voltage induced in the rotor at slip S, and EOC is the open circuit voltage induced in the rotor when at rest. So that's your relationship, your equation relationship between the voltage and frequency induced into the rotor. Active power of an induction machine. Again, we kind of alluded to this, but this is a better picture. It also kind of goes into some metric equations here in a second. But you can see your active power is actually connected to the stator, to the actual three-phase connections there. You do have stator copper losses. You do have stator iron losses. That active power is magnetically coupled to that rotor, which causes it to spin, right? The rotor spins. The rotor has copper losses. Certainly you can decrease the rotor losses by increasing the diameter of those copper squirrel cage conductors. You have mechanical losses such as bearing losses and windage and frequency losses. And then you have your windage and frequency losses, and then you finally have your shaft power, so P out. So your efficiency output will never be higher than your input. So the input, it's always got to be higher than the output. If you didn't have that, then you would have some type of a perpetual motion machine, which we all know doesn't exist, which is a darn shame. And maybe somebody will figure that out one day, but I don't think that's possible because everything has to add up. So motor torque. So here's a metric conversion for a motor torque. We talk primarily about the American version of it, right? The ANSI version. But this is metric. So you have 9.55 times your PM divided by your N, and you can actually step through this, and you can calculate your torque. I squared losses in the rotor. There's your formula for that. You have your slip. You have your power transmitted in the rotor, watts, and then you have your rotor I squared R losses in watts. And then your mechanical power is your PM equals PR minus PJR, the I squared losses, and you can calculate that if you ever wanted to. Can't imagine that you would go through that unless you're manufacturing synchronous machines or manufacturing AC induction machines, but you could do it. Calculate the synchronous speed of a three-phase induction motor having 20 poles when it is connected to 50 hertz. So a 20-pole machine, that's pretty wild. It doesn't rotate very fast, but they could have them like on a large hydro plant. The one thing I wanted to point out here is the faster that machine rotates, the smaller it is. The slower it rotates, the larger it is. So a 0.5 horsepower, half horsepower, 6-pole induction motor is excited by a three-phase 60 hertz source. If the full load is 1140 RPMs, calculate the slip. And again, we've kind of beat this one to death. We've talked about it multiple times, so it shouldn't come to any surprise to you what the calculation is. We have source frequency 60 hertz, number of poles is 6, full load rotor speed is 1140 RPMs. So again, you use the same formula, 120 divided times frequency divided by P. So you have 1200 RPM machine for a 6-pole unit. Slip speed NS minus N equals 1200 minus 1140, which is what we were trying to calculate is the slip. So you have 60 rotation or RPM. So 60 divided by 1200 is 5% slip. So that's how you figure that out. This is kind of an interesting chart. I hope you can read it. I'll kind of go slow. Starting at the top, you have the effect of voltage and frequency variations on induction motors. So if you have a voltage variation of 120%, your starting and your max running torque increased by 44%. Your synchronous speed is unchanged. It's only a voltage variation. The only time you can change your speed is to change your frequency, right? You have a decrease by 30% in slip. You have full load speed increases by 1.5%. Synchronous speed doesn't change, but full load speed changes. You have full load efficiency of a 6% decrease. You have a full load power factor decrease of 5 to 15 points. You have your full load current increases by 12%. Your starting current increases by 20%. You have an increase in your temperature rise at full load to 5 to 6%. And you have a max overload capacity increase of 44%. Magnetic noise, no load in particular, is noticeable and increases as if this condition continues. So you can see if you have an increase in voltage, there's a lot of things that happen here. But you can pretty much go through it. You have 110% voltage. You can actually search for this. I think it's the Engineer's Digest, September 1969. Somebody produced this chart, and it's a pretty good chart. If you have a problem reading it and you really want it, just send me an email and I'll send you a better copy of it. I think what I'll do actually is I'll put this PowerPoint presentation in the DVD so you can kind of follow along if you can't read this on your screen or something. Measurement of the motor output is based on the principle that slip RPM is linear from 10% of the load to 110% of the load. So this is a typical Nema design B induction motor curve. So you can follow this. You can see your efficiency curve. You can see your power factor. You can see your current. You can see your slip. And then you can see your percent speed as you load up the motor. Kind of an interesting overall curve. So here we have an example. If a 4-pole, 10 horsepower motor with a full load slip at 80 RPMs was found to be running at 1770 RPMs, what is the approximate output at that time? So if you're able to measure the slip, the actual speed of the machine, what it's running at, you can actually calculate the output load, the actual horsepower. That's kind of cool because that allows an operator or a maintenance technician to go out there and measure. If you had a handheld device where you could measure the speed of these machines, you could quickly calculate their output load. And you could also determine if you're in a situation where you should change out that motor next, right? So again, you have full load slip equals 1800 minus 1720. That's the actual machine there. It's 80 RPM. So you have at 100% load, you have a difference of 80 RPMs. Your running slip is 1800 minus 1770. How fast it's running? You got a 30 RPMs. So your running load is running slip divided by full load slip. So at full load, you should see 80 RPMs. At whatever load you're at right now, you're only seeing 30 RPMs difference. So you take 30 divided by 80 is 0.375. So your output load, this happens to be a 10 horsepower motor, is 10 times 0.375. You're actually running at 3.75 horsepower. Pretty cool. That's a neat equation, neat problem, because a lot of times you can't measure, you can't get into these things for reasons such as arc flash issues. They don't want you messing with the electrical connections. But if you were actually able to measure the speed of these machines, you can put a little reflective tape on that shaft at some point in time when it's shut down, and you can measure it. Or there's different ways you can actually measure the speed of that machine. You can actually calculate its output load. This measurement or method of estimating motor loads assumes nameplate voltage is applied to the unit, so you need to make sure you understand that you are at your 460 volt AC or whatever, not increased or decreased. And as shown in Table 4, a motor's slip will vary inversely proportional to the square of the voltage. So if for some reason you have an abnormal slip, it could be due to an abnormally high voltage. Unless the nameplate voltage is applied to the unit, a significant error can be made in estimating the motor loads based upon only on slip. Note that below about 60% of full load amperes, the motor current is not valid measurement of motor load. Due to the increase in motor power factor, more and more of the apparent current is reactive amperes as the motor load decreases. So that's an interesting thing. You know, one of the things that we do at my current job is we go through and replace old motor starter buckets with some nicer Schweitzer or ABB or GE intelligent devices where they can actually give you all this data and you can capture it. You can look at all kinds of things like event data, all kinds of things. Certainly for smaller motors, they have a smaller version of it. You can sell it to your group because it's arc flash mitigation. It has a little arc flash optical sensor on the motor's protective relay, and it snaps right in there, and you can replace a lot of things, and then you can interconnect all these things later and get a lot of data from it. We talked about the torque. The torque equals force times the radius. So again, your radius is 3 inches, and so you have 100 pounds times that 3 inches is 300 pounds per inch. We talked about this equation, which is torque in inch pounds and torque in foot pounds, which is 5252 times the horsepower times the RPM. So we understand torque and we understand its relationship. And now we're fixing to move into variable frequency drives after we talk a few other items. So here we have pole action causes turning. So if you have a magnet on a string extended out by that little rod there, and you're holding a magnet in your hand, obviously likes repel each other, and opposites attract each other. So if you were to put the North Pole in your hand to the north of the magnet, it would cause that to rotate. And that's exactly how a machine operates. It actually has a magnet on the rotor, and as you have the stator magnetic field rotates, it also tries to catch up with it. So that's how this actually functions, and that's how a motor works. If you were to allow that end to stay, then the S would just stop at the end in your hand, so it would actually hug it, right? Because they attract each other. So the idea is that this magnetic field has to be rotating at all times to keep the rotation occurring on the rotor. Here's an actual rotor, and if you had a two-pole machine, you'd have a north magnet at the top and a south magnet at the bottom. You could have multiple machine poles, and they'd all be north on the one side and the reverse on the other side, and as long as that the stator armature windings are changing in frequency, it should cause that rotor to rotate. An electrical current creates the magnetic field proportional to the current. What this means is if you have a coil of wire, by applying a current to it, it creates a magnetic field. This magnetic field increases as the current increases. So this magnetic field gets larger and larger and larger, which is why these motors function the way they do. If you have a conductor passing through a magnetic field, you induce a current into that conductor. And there's a force that's created on that wire which causes that conductor to be pushed outside of that magnetic field. It's hard to actually keep it inside that magnetic field. And so that's why on the rotor, those squirrel cage conductors, actually get a current flowing through them. Granted that they're all shorted out on both sides of the rotor, but they do have a current flowing through them. That current flowing through them in turn generates a magnetic field opposite the other magnetic field, so it actually is a counter EMF, whereas the magnetic field generated by the armature is generated by the EMF, the electromotive force. So here you have another picture of this. Because of the direction of the flux lines that circle the conductor, the flux lines between the magnetic poles tend to accumulate on the side where all the flux lines are going in the same direction. This produces a strong field of lines that are closely spaced and curved. The lines tend to straighten and become more widely spaced, and in doing so push the conductor away at right angles to the flux lines in the direction of the weak magnetic field. And that's what causes the torque, right? It causes that device to rotate through there. So here again you have the direction of the current is facing down. The direction of the motion is actually going to the right. It's going to the weak side of the magnetic field. The stronger side of the magnetic field actually pushes that conductor through. So if that conductor is held on a axis, on a shaft, it'll actually rotate, right? Here's another example, just a different view of this, how you have the force on the wires going up. The stronger magnetic field on the bottom is causing it to push up. The weaker magnetic field on the top is actually, it's a weaker field, so it allows the conductor to move in that direction. If the current was reversed, it would obviously go the other direction. So if you have a rotor cage, you'll know that on one side the current's going in one direction, and then it's turned around and going the opposite direction the other way. So both cages, or the wire cages, actually cause the proper rotation. So one side is going through or into the motor, where the other side is coming out of the motor, so it actually rotates faster. I've never used the left-hand rule, but I'll go ahead and talk about it. If you actually wrap your hand or curl your fingers around the conductor, your thumb shows the direction of the electric current flow, and the fingers wrapped around it show the magnetic field. So this is what they call the left-hand rule. The right-hand rule, if you put your thumb up, your index finger straight out, and your middle finger to the left, you'll actually see the resulting motion of the conductor as your thumb. The magnetic field would be your index finger, and your electric current flow would be your middle finger. Again, if for some reason you had a magnetic field or a conductor not connected right, you might want to think like this to sort it out. But this is just kind of a visual. And then we kind of alluded to this, right? I was talking about as the copper wire goes through it, it's shorted on that one end and it comes back out. So the torque is a twisting or turning force exerted on that loop that causes it to rotate around its axis. The direction of current going away from you is shown as an X. The current actually flowing to you is shown as a dot, right? So you have an X and then you have a dot. It's kind of like an arrow, right? The back side of the arrow is the fins of the arrow, and it's going into the page. If it's coming at you, you would just see the dot, the sharp point of the arrow. So that's a good way to think about it. And instead of the straight wire conductor, a loop is put into the magnetic field, and the current passes through it. The newly created magnetic field interacts with the existing field to produce torque. So that's exactly why that rotor actually turns, or that magnetic field turns. And that's also why on an induction machine you don't want to have it exactly at in sync speed. You want to have the slight slip, and because you have that slip, that angle slip, you actually produce torque. If you didn't have that difference, you would have no torque. When the plane of a loop becomes perpendicular to the field, the armature is in a neutral plane. It could get stuck there. If it's stuck in a neutral plane, it won't really move. With the armature in the neutral plane, magnetic interaction is at equilibrium and no torque is developed. If power were applied to an armature at rest in the neutral plane, no torque would be developed, and the armature would just not run or not turn. So you need a, obviously, you don't want to have a two-pole machine like this, a little magnetic DC field where it would get stuck. But if the weight of the rotor is large enough, it'll actually keep rotating through it. And here you have your commutator brushes and your commutator. So you have your slip ring, and you can see as it would slip. So in figure A, your torque is going to the counterclockwise. So the current through the loop creates a torque. So it actually rotates. At this neutral position, there's no torque created, but the inertia carries the loop forward. When it does that, the current actually reverses because of the slip rings, and it'll actually rotate through it. So the inertia has to carry it through the neutral plane. Once it carries it through the neutral plane, then the commutator brushes, or the commutator is actually seeing a reverse current and causes it to rotate it again. So as the loop continues around, the commutator reverses the current direction, so the magnetic field interacts with the loop to produce a torque that keeps the loop turning in the same direction. At this point, inertia carries the loop toward position A, and the cycle is repeated over and over and over. So that's why you have to have a commutator in the carbon brushes on a DC machine to make it work. This is an interesting experiment by Faraday. He uses the Oersted principle to build a world's first electric motor. This would be a kind of a neat application for somebody to build. It used the interaction of the magnetic fields of the current carrying wire and the permanent magnet to achieve continuous rotation of the wire conductor. So you can see the actual wire conductor has current flowing through it, and it just sits there and spins. So you have a pool of mercury, a cork stopper, right? And of course mercury is magnetic, right? So the platinum wire conductor is actually sitting in the top of the mercury pool of mercury, and the other conductor is in the bottom of that mercury pool, and the cork stoppers keep it all from leaking out the mercury. The top of the electric motor is connected to a cork through that other conductor, and as the current the current flows through this device, it actually causes that that little wire to rotate, and you'll have continuous rotation. Obviously, mercury is very dangerous. You don't want to leave it around kids or anything. And certainly, there's an active, everybody wants to get rid of their mercury in these facilities, such as lead. They want to get rid of lead, mercury, and asbestos. So you don't want to introduce mercury into a design in a refinery. We talked about EMF, and we talked about counter EMF. And so your EMF is actually the voltage applied to the stator, and the counter EMF is a result of the rotor turning, and as it's turning, it has a magnetic field induced into it. The current then travels in the opposite direction, which creates its own magnetic field, which is counter to the EMF. So the counter EMF acts as a load for the DC supply, a power supply, feeding the motor, so that the low resistance motor windings do not draw excessive amounts of current. If we jammed the armature, we actually locked it so that it could never turn, there would be no counter EMF was produced, and eventually the motor would just heat up and burn up, right? So it relies on that rotor turning at the proper speed to counter that EMF. Otherwise, you would be stuck in a locked rotor current condition. And obviously, on a 10 horsepower motor, you don't want to exceed about 14 amps. You certainly don't want to go into 6 times 14 amps for an extended period of time. And the only way that can be reduced is for that rotor to turn and create a counter EMF. It subtracts the voltage from the EMF, and that's where you get the lower current. Here we have we have your EMF. Your EMF is induced into this wire, and it creates a current that the generator action in the motor. So basically what happens is the motor is driven, but it also creates a opposite generator action, which becomes the counter EMF, and these subtract. The counter EMF and the EMF subtract, and you have the motion, the actual wire goes through. So here it shows you the EMF is going in one direction, but the counter EMF is going the opposite direction, and you have rotation. So when the motor is used as a generator, the left-hand rule for the generator states that the current flow in the armature is the reverse of the current flow in the motor for the same direction of rotation. This means that the EMF induced in the armature of the operating motor by generator action opposes the EMF applied to the motor armature. For this reason, it is called counter electromotive force, or CEMF. If for some reason the motor, years ago they used to have these VFDs and they didn't know that they had to change the armature voltage at the same time that they changed the frequency, and they didn't have that volts per hertz relationship linear. So when they did that, they were burning up these designs, these motors, because the motor saw full voltage at a reduced speed, and if it has a full voltage at a reduced speed, the counter EMF is not high enough because it's not rotating fast enough to counter that EMF, which causes overheating. So that was one of the original problems when they started first designing VFDs. This will help you understand it a little better. This is a simplified version. This same concept can be used for different ideas, like for induction machines as well. So here you have a 250 volt machine. Your full load amps on the nameplate is 5 amps, and the resistance is 10 ohms. And then therefore, solving Ohm's law, you have 250 divided by 10. We would see 25 amps. But if we saw 25 amps, that's equivalent to, in this example, locked rotor current, 5 times the full load amps of 5 amps. Somehow that 25 amps has to drop back down to that 5 amp full load. And the way that happens is because you have that counter EMF. So if Ohm's law is true, then E equals I times R, which equals 5 times 10 equals 50 volts. So by Ohm's law, we know that we only have 50 volts across the resistor being REQ, 50 volts. So where is the rest of the voltage coming from? And of course, we know that it has to be the counter EMF. It has to be reverse polarity. You can see the voltage applied, 250 volts, the positive is at the top. But the counter volts, the counter CEMF, is the positive is at the top. So it has to have a voltage of 200 volts, which would subtract that 250 and leave 50 volts across that REQ, 10 ohms, and allow you to run this motor at 5 amps. If for some reason you're not at full speed, you won't see this. So if you could actually run this test, right? It's a nice way to understand it, and it's a very simplified way to understand it. Again, we talked about the frequency at the bottom and the voltage at the top, and as the current, or as the frequency is increased, the voltage has to be proportional as well. Like I said, it used to be that they used to leave that voltage at the top at 100%, and they'd run this thing at 10 hertz up to 20 hertz, 30 hertz, 40 hertz, 60 hertz, then 60 hertz, and it would overheat that motor because it didn't have any counter EMF, or the proper counter EMF. So it has to be a very clear rise, and volts per hertz has to match. Once they figured that out, then VFDs kind of took off. So we need to talk about inductive reactance, the amount of opposition to current flow offered by an inductor. X of L equals 2 pi times the frequency times the inductance, which equals the volts divided by current. So there's a lot of interesting things about reactance or inductive reactance. Usually you say 2 pi F is omega, which is a small w. So if you were to take 2 times pi times 60, that would roughly be 377. And then you just multiply that times the inductor in henries, and that solves for X of L. Using that relationship there, if the frequency is increased, the resistance to that frequency increases, right? So later on, when we talk about harmonics, there's multiple frequencies above fundamental frequency, which is 60 hertz. So if you have a third harmonic would be 3 times 60 hertz. So a third harmonic would be 2 pi times 180 times the original inductance, which would say that if you increase the impedance or the inductance of the system, you could actually decrease that ability for that 180 hertz or that third harmonic to get back to the utility system, and indeed that is how it works. So here we have a chart. It's a variation of X of L versus F for a 1.59 Henry inductor, and it's no different than omega L, right? So here, if you have 100 hertz, you'd have 2 pi times 100, and that would be your, and then times the 1.59 henries would give you 1,000 X of L, and that is 1,000 ohms. X of L is measured in ohms. The load and motor speed regulation, the greater the load, the less the speed. The less the speed, that means the less the counter EMF, and the greater the EMF to raise the speed. So that's a good relationship. And as we were talking about those efficiency things, this comes into play a lot, right? So if you decrease your load, you'll increase your speed, which will increase the counter EMF, which will decrease the need for a higher EMF. These are different field arrangements for DC motors. The first one is a shunt DC motor, and you have your field and your armature and your actual applied voltage. So the power and motor elements are in parallel. You can have a series motor where you put that field in series with the armature, and there's certain reasons you would do that. You can also have the compound motor, which is a separate field in series with the series field, and then you could have a power and motor elements in a series parallel combination. And there's certain reasons why you would want to do this for different characteristics, but we really don't get into DC motors as much anymore. I just wanted to point it out that is that relationship, because we had talked about it earlier in an earlier slide. One thing about a DC motor, if it's lightly loaded and for some reason you lose that field current, it disconnects that field, that rotor will actually go into an overspeed condition. It'll actually go into an avalanche and destroy itself. And most people are really leery of this. I have actually seen it operate. Years ago, when I came out of the Navy, I worked for a company, and they had a large 800 horsepower motor. It was just sitting on the end of it, and this was kind of before safety was a big issue, right? And I was designing these little electronic boards, or actually fixing them for this company. And what happened was I increased the speed of the machine too quick, and because it wasn't bolted down, it fell over. It spun and fell over. When it fell over, it pulled the field windings off, and because it was just sitting there spinning the shaft, it was totally unloaded. It was a lightly loaded machine, and when that field broke up loose, that motor just took off, and it would have just destroyed itself had I not run over there and killed the power. Lesson learned was, one, you don't want to run a big DC motor like that without securely fastening it to a frame or a mount, or in this case I took a chain and wrapped it up against an I-beam just to keep it from moving around. And two is you pretty much don't want to run one of those motors unloaded like that, because you risk the chance of having that field disconnect for some reason and that motor overspeeding. So you constantly have to watch it. It was a lesson learned for me. I learned it in school, but seeing it do it standing right in front of me was a whole other thing, and I'll never forget. So here you have a DC motor, and you can actually adjust the field with a rheostat, right? It's a variable resistor, and you can decrease the current flowing through the motor to speed it up. So you decrease the field current, just like we were talking about before. If you decrease the field current, you'll actually speed that motor up. If you increase the voltage across that armature, you can also speed it up as well. So if you decrease the armature current flow, slows the motor down. So you can actually adjust the armature rheostat as well. But these are large motors, and you don't always want to do this. But these are different ways of varying the speed of a DC motor. Here you have a shunt motor. The residual magnetic field maintains a weak field. And certainly if you um, have that field current go to zero, you certainly don't want to have a lightly loaded motor, or it'll run away from you, right? So you want to be careful of that. Here we have the counter EMF and the EMF explained again. We have the CEMF. The counter EMF is produced when the armature current cuts through the flux lines of the pole pieces. When field strength is increased, there are more flux lines and the counter EMF increases. So you can actually increase your counter EMF by increasing your field current, which is kind of cool. You don't have to rely just strictly on the speed of the machine. They all kind of interact with each other, so you want to be cognizant of that. Here you have a three-phase machine. You have phase A, B, and C. You can see that they're 120 degrees displaced on that top, the output voltage. The actual stator also has phase A, B, and C, and they are exactly 120 degrees displaced of each other. If you had slip rings in this situation and a north-south pole, and you applied your voltage to the slip rings, you could cause that motor to rotate. So, but usually you don't see them like this. Here's the actual winding connections. This is actually a Y connection. If you see it, you can see phase 1 comes around and phase 1 comes out, and then it connects to a common point, that common connection point. Phase 2 is displaced by exactly 100 degrees. It comes out, goes to the opposite side. It connects to that common connection point. And then phase 3, which is phase C, it also goes through, around, and connects to the opposite point. So when you're interconnecting all of these stator armature windings, you need to make sure you connect them the right way, and you need to make sure that they are wound or laid in there the proper way, because you don't want to have opposite current windings in the wrong direction, or you'll counter this and you'll have problems and have to rebuild that motor. Rotating magnetic field produced by a three-phase current flowing in the stator of a three-phase motor. Starting out at the top on 1, you see your north-south, and then as you move to 2, it rotates. 3 rotates again. So these fields are at the stator fields are actually rotating because of that magnetic field, which causes the rotor to rotate, and you can step all the way through it as it rotates through there. Here's a breakdown of the current flowing in the rotor bars at 98% RPM. You can see how these rotor bars are actually shorted out by that end ring on both sides. They need to be shorted out. And the bars are located at 90 degrees from the stator pole centers at the center of the rotor poles. And so you can kind of get the idea. You've got your stator pole 1 and your stator pole 2, and then you've got your center of your stator pole, the lines of force, the center of the pole formed at the rotor, the current flowing in the end rings. You actually have current flowing through those end rings, so they need to be properly sized, right? Because current flows in one direction. You can see at the top it says current flowing right to left on the rotor bars, but if you look on the bottom, opposite of them, the current flowing is from left to right in those rotor bars, right? We saw that before, which causes the rotation. So then you have your lines of your force, and then you got your center of your stator poles, and the center of the poles formed in the rotor at the top, and then the current flowing in the ends. So this kind of gives you an overall magnetic field and the current flowing through these rotors, that relationship. We talked about a Y connection and a delta connection, and if you recall, the delta connection is shaped like a triangle, right? And so the best way to figure this out is if you start on that winding 1 and you say the top of winding 1 is T1, and then the top of winding 3 is T2, and the top of winding 1 is T1, the bottom right hand side of winding 3 is T2, and the top of winding 2 on the far left hand is T3. Then winding 1, the bottom side, would be T4, and the far left-hand side of winding 3 would be T5, and the did I say that right? So T1 is the top of winding 1, T2 is the far right-hand side of winding 3, and T3 is the bottom of winding 2. I think I said that wrong. And then the T4 would be the bottom of winding 1, T5 would be the far left-hand side of winding 3, and then T6 would be the top of winding 2. So you can actually interconnect these motors. You'll see if they have that 6 leads coming out, that's what they mean. So you would connect on the T1 to T6, and then T4 to T2, and then on the far left-hand side you would connect, let's see, 1, 2, 3, 4, 5 to 3. So that's how you would make a winding, a delta connection. And the delta connections, the end of winding 1 is connected to the beginning of winding 2. The end of 2 is it's the beginning of 3, and the end of 3 is the beginning of 1. The three-phase windings form a closed circuit. Leads are brought from the 3 junctions of the windings for connection to the load. Any 2 of the 3 wires takes the voltage phase across 1 coil. If you have a delta Y starter, you would first start it in a Y, and then you'd switch to a delta. So it would rotate faster in a delta configuration. And you would just basically have a reduced voltage starter in this situation. In a Y connection, you actually connect it in a Y, so you can see that you tie all these windings together at the bottom of it, and you create a Y condition. So that concludes AC induction motors, motor efficiency, and motor assessment. The next topic we move into is motor controllers, and then finally we'll move into variable frequency drives, harmonics, and application considerations. I think we're at 2 hours 45 minutes already in this course, so it's a fairly long course, but hopefully by the end of it you will have a very good understanding of variable frequency drives, because you'll understand your induction motors and harmonics and some of the application considerations you need to make sure you're aware of. Okay, now the next topic is the control of the electric motor. So here we have a picture of a variable frequency drive, but what we're first going to talk about is contactors and motor starters, then we'll talk about solid state starters, and then we'll talk about programmable type starters, and then we'll move into variable frequency drives. So again, there's types of motor controllers. You'll have magnetic units, contactors, and motor starters, and then you have solid state starters, and then you have programmable starters and variable frequency drives, VFDs. VFDs are now called adjustable speed drives now, AESDs, but I still call them VFDs. Here's a typical pump panel. On the far right-hand side of that panel, you have a circuit breaker. That circuit breaker is out of the bottom of it, you've got those large black wires, and those go to a power block, a power distribution block. And then you're coupled to a, looks like some type of well, actually that looks like a soft start type device, or a variable frequency drive with some separate little relays, and then ultimately it goes to the load, the motor load. So that's really not a across the line starter, or at least I don't see it across the line starter in there, but that's a typical design for a pump panel. And when you close it, you've got that little handle on the right hand side. That's your disconnect panel, right? Or disconnect switch, where you would open and close it, and then you can start and stop the pump at the bottom and get some feedback as well. Magnetic controllers that are universally used, made up of components such as relays and contactors, magnetic coils, electromagnets, and moving armatures, contacts and arcing horns, spring-loaded components such as push buttons, fuses, timers, interlocks, switches, main operation. They basically open and close the electrical circuit by means of a contact. A motor starter basically is made up of a contactor, special relays containing coils, contacts, pressure spring, arcing horn, and armatures. You have overload protection, and you can also have an undervoltage release or protection. The difference between a contactor and a motor starter is the added overload protection, or undervoltage release protection, in the motor starter. So you certainly understand now why you want to have overload protection. You don't want that machine to have a locked rotor and leave that on for a continuous time, or you'll overheat that motor, burn something up. So you want to trip that contactor in an overload condition. In an under voltage condition, if the voltage is low, you can have some problems as well, as if it's extra high. Overload protection implements when overheating occurs. Overheating causes a stalled rotor, so the rotor's not turning. Abnormally low voltage, low frequency in the case of an AC motor, and then unbalanced voltages could be a cause of that overheating. Thermal relay consists of heater elements connected in series with a motor. There are some old-fashioned bimetallic elements that we used to use, and we call them heaters, right? They're deflected by high heater temperature. When that heater element or that bimetallic element heats up, it snaps open, right? And then it shuts down. Contacts open when bimetallic elements deflect, and then you have a manual reset button where you can actually reset that device. And then you can also have time characteristics of thermal overload relays. I'm not really going to get in too much into protecting a motor, but there's another course that you could go into, a protective relaying type course, where you would talk about protecting motors, especially medium voltage motors. Under voltage release and under voltage protection implements when loss of power or loss of a low voltage occurs. Under voltage release allows for the voltage to be restored automatically. Under voltage protection prevents automatic restarting when the voltage is restored. How that would work. And then here's a connection wiring diagram of a small little motor starter. It shows a physical layout. It shows the wire connector numbers. The darker wires depict the power circuits. And then you've got a little schematic off to the right. So this is a solid state type starter. The one on the left actually is not a solid state starter. That's actually magnetic relays. So let's do elementary wiring of a ladder diagram. It shows the power on the vertical lines called rails. It shows the components on a horizontal lines called rungs. So if you studied the PLC training, you would understand what rails and rungs are in ladder logic diagrams. You have two sections in this motor starter. You have a power circuit and a control logic circuit. So starting at the top left, this is actually a garage door. So you have your 208 volt AC coming in three-phase. Goes through the first contactor, OC. If it closes, that motor goes through an overload there. So those are bimetallic overloads. So if OC closes, the motor rotates one direction. And if CC closes, it reverses two phases. You can see the reverse of those two phases. If you look at the top, A connects to A, B connects to B, and C connects to C. So the tops are connected the same. But the bottoms, the A is connected to the C. You see that? And the B is connected to the B, and the C is connected to the A phase. So whenever CC is connected, it reverses, in this case, A and C phases, which causes the motor to rotate the opposite direction. On the right-hand side, you have your transformer, your control power transformer. It's a single-phase transformer. It steps at 208 down to 120 volts. You have X1 and X2. On your X2, you always want to have that grounded per UL 508A. And then you go through a fuse. You go through your overload. So it's actually a contact 9 and 10 off of the actual motor overloads. And you have a stop push button, right? So if the overload opens or the stop push button is depressed, this circuit should stop. Then you've got open and closed circuits, right? So if everything is okay, that 120 volts it'll feed right between the open and closed circuit breaker. So if I press the open circuit breaker, the first thing that's going to happen is you have limit switch open and a closed coil, right? That CC is not energized. So if limit switch is not open and the closed coil is not open, and I press the open button, OC will energize. OC contacts locks in. It's sealed in around that open push button by 9 and 10 contacts. And what happens there is the garage door starts to open, right? It actually opens until it hits its limit switch open and it stops, right? Then you have on the right hand side the close push button. If you press the close push button, if the limit switch close is not activated and the OC motor starter is not running, then the CC contact will close, and again that reverses A and C phase, which causes the motor to rotate the other direction and the garage door to close. And then you've got your SS selector switch, and then not on the other selector switch. So I'm not sure what the SS is. Let's see if we can figure it out. I don't see where it is in the schematic, but if SS closes, it's mechanically interlinked or interconnected. That's what that little dashed line means to the not SS. So if for some reason it was activated, then the open would energize, and if it's not, if it's de-energized, then they close. I'm not sure what SS is. It must be some type of a safety system or something. Hard to say. Anyway, the stop button, at any time, if you wanted to stop this, you would just press that stop button and release that over OC latch, right? So it would just stop in midstream. There's different symbols here. You have the far left is a disconnect switch. Then you have a circuit interrupter, which is circuit breaker. Then you can have a circuit breaker with a thermal overload is the next symbol. Circuit breaker with a magnetic overload is the next one. So these are the different symbols. You see the limit switches, they look like little sails. You have a normally open limit switch or normally closed. You have a foot switch. You can see that symbol right there on the far left below the disconnect switch. Normally closed, pressure or vacuum switches. Temperature switches have that little metallic, a little element on the bottom of them, and they'll open and close. You can also have liquid level switches to control these motors, flow switches, etc. I go over a lot of this in that PLC training class, so if you don't have that, you might want to order it. That selector switch, SS selector switch, maybe that's what that SS is on that other diagram, but you can actually have a selector switch 2 position, 3 position, and they can mean different things, right? And then pilot lights are your actual lights. I like using the push to test lights because you can walk up to it and press the light itself, and it'll light up, and that'll tell you if it functions or not. On the right hand side, you've got different push buttons. You got normally open and normally closed. So the normally open would be your start, the normally closed would be your stop. You've got a double circuit, normally open, normally closed. You got a mushroom head, which would be like a emergency stop push button that would more than likely latch in. You got a wobble stick there, two single circuits for maintain contacts. You've got illuminators. You've got different contacts here for instant operating, time contacts. You can have timers in there. You can have overload relays. You've got coils, different symbols for coils. You've got your iron cores, the different symbols for the iron cores. So these are nice overview of the different diagrams. Here's some more symbols. A single phase motor or a 3-phase motor is just a circle with 3 lines coming off of it. You want to make sure you ground that outer case of that motor as well. And then you have a wound rotor motor, which you don't really see that very often, but that would be a wound rotor, and you would connect a field to the other 3 phases. On a DC motor, you could have an armature, the shunt fields, the series fields. On the far left, you got schematic symbols. If you have 2 wires that cross each other and they don't have a dot in them, that means they're not connected. Usually what I like to do is actually draw a little hump over them so that they're not, so you can clearly see they're not connected. But if they are connected, you have a dot. Power is usually a thicker wire, control is a thinner wire. If you have a battery, you just have the 2 cells, the positive and negative, where the positive plate is always larger. We'll talk about diodes here in a little bit. You have a half-wave rectifier diode there. On the right, you have a full-wave rectifier, which converts the AC to DC. Different type fuses and symbols, an annunciator, bells, buzzers, voltmeters and amp meters, and I think that's pretty much all we need to go through now. Make sure you understand your grounds and you ground everything per the National Electrical Code. Next, we'll talk about a silicon-controlled rectifier, an SCR. The semiconductor device is a member of the family of control devices known as thyristors. These were developed in 1970. They're the workhorse of the industry, industrial control industry. Its evolution over the years has yielded a device that is less expensive, more reliable, and smaller in size than ever before. Typical applications would be DC motor control, generator field regulation, variable frequency drives. You don't see SCRs that often on variable frequency drives anymore. Now what you would see is a IGBT insulated gate bipolar transistor. Lighting systems, you see a back-to-back SCR, which is called a static switch, or a THIRAC, or a THIRAC, I think it's called. TRIAC, it's a TRIAC. And so it's just two back-to-back SCRs, and you'd see that in a lighting condition, like a single-phase lighting application. This silicon-controlled rectifier, the bottom part of it that actually screws in at that stud, is the anode of that device. The cathode is on the top, and then you actually have gate leads. So your auxiliary cathode lead red extends the cathode potential to the control circuit. So if you were to touch that red cathode lead, it would be the same potential as the cathode lead, so you want to be very careful with that. The gate lead is a small voltage that's created from your pulsing transformer when you gate this transformer. We'll talk a little bit more. Here you have a silicon-controlled rectifier, a 3-lead device with an anode and a cathode. As a standard, it's like a standard diode, but it has that third lead, that gate. As the name implies, it is a rectifier that can be controlled, or more correctly, one that can be triggered on into an on state, applying a small positive voltage to the gate lead. So if you go from the gate lead to the cathode and you apply a small voltage, positive voltage on the gate lead, if the device has more positive on the anode side with respect to the cathode side, it'll turn on. If it's not, then it won't turn on. So once the gate is on, the trigger signal may be removed, and the SCR will remain conducting as long as the current flows through the device. The load to be controlled by the SCR is normally placed in the anode circuit. You can see the little picture below. So we can talk a little bit about this. So in here we have an AC source, and we have a resistor, and we have the SCR. So if we were to wait until we saw the positive portion of that AC waveform, you know how it goes positive and it goes negative. If we looked at the AC positive portion and we gated at that time, then it would actually turn on and allow only half that current to flow through it, the positive waveform. The minute the current reversed, because it would go back through the zero crossing of that sine wave, and then it would go negative, that SCR would naturally turn off. It would naturally commutate off, regardless if the gate signal is on or off. Typically what you do is you fire that gate like a car fires a spark plug, but not near as high a voltage, and then you get off of it. So you fire it at the right time, and then you get off of it, and you allow it to turn on at the right time. So here you have a gate turn-off device, the old GTO. You don't really see the GTO anymore. It's another member of the thyristor family. It's a gate turn-off device. So the neat thing about the GTO is, unlike the SCR, where you had to wait for it to be reverse biased before it would turn off. So if that AC voltage was a DC voltage on the previous diagram, that SCR would never turn off, regardless of the gate signal. You would have to interrupt that current. So the GTO, on the other hand, is like the SCR, but it can turn off. So while this component has been around for many years, it has just recently evolved to the point where it is capable of carrying high currents required for motor control circuitry. This is an extremely old slide. We don't use GTOs anymore. We use IGBTs. Unlike the SCR, the GTO can be turned on and off with a signal applied to the gate. So regardless of where you are on that signal, you can actually turn that device off. The turn on signal is a positive voltage. The turn off signal is a negative current pulse. It is now finding applications in the output stage of medium voltage, high powered, variable frequency drives. So, I bet if you dug into this, you would find out on some really high voltage applications where IGBTs cannot handle the high voltage or the high current applications. There might be some manufacturers out there still using these old GTOs. There is a cutoff where these frequency, the power is too high for an IGBT, and you just have to use a GTO. The triac we talked about is a triode for alternating current. You can see it's two back-to-back SERs. It's a bidirectional SER. It represents the SERs connected back-to-back. AC motor control utilizes triacs instead of SERs for control, especially single-phase AC motors. So you can actually control the voltage going across it. Kind of a neat little device. You also see these in light switches as well, right? A circuit using the SER. Here we have an SER controlling a load in a DC circuit. The DC motor starts and stops the control circuit. So you have this motor, and this motor is fairly small because you've got some push buttons that are in series with it, and you've got your SER under test. So if you, and you can see your battery on the left is a positive and negative. So the positive is on the motor, and the negative is on the bottom side of the SER. So it's set up to have a forward bias, right? So if you press the on button, you'll apply that positive voltage to the gate of the SER, and because the off button is held closed, that current will flow, and the SER is now allowing that current to flow, and the motor will run. If at some point in time you press the off button, you have broke the current, right? So you've actually disconnected the power to that SER, and that's the only way you can actually turn that SER off, is to either reverse the voltage on it or to cause the current to go to zero. Once that's done, the motor will sit there in an idle state, even when the off button is closed again, and you'd have to press the on button again. So that's a good little circuit to test an SER. You just want to be careful that how much power you're flowing through those contacts, and also because it is DC, the contacts, the on and off push buttons, have to be rated for that DC, or you will have a large arcing, an arc across those. We talked briefly about a crowbar. A crowbar can be used in different applications. In this particular application, it's over voltage protection. So here you have it consists of an SER placed in parallel with the output of a DC power supply for the purposes of placing the direct short circuit in the output of that supply to prevent excessive voltage from reaching the load. Damage to the SER and power supply is prevented by the judicious placement of the fuse or substantial series reactance ahead of the SER to limit short circuit current. So you don't, obviously you don't want to short it out and trip the fuse or something like that. You want to put some reactance in there, and so they have a little filter there as well. So you could also put a series resistance in series with that crowbar as well to protect that load. So here you have your AC source. Goes the secondary side of that transformer is your rectifier. That's a full bridge rectifier. Then you have a T filter, so it filters that output out. Goes through a fuse for primary protection, and then finally to the load. If for some reason there's an overvoltage situation, they left out the triggering circuit, but it would look at the actual AC voltage or DC voltage. If it sees a high voltage, it would energize the crowbar, which would cause that all the voltage to be shorted on the outside, on the output of that fuse, and it would protect the load. AC motor control. Here we have a SER and an AC motor. The circuit will allow you to control the speed of the AC motor, for example, an electric drill. The bridge rectifier produces DC voltage from the 120 volts AC. So you can see the plug is on the far right hand side. S1 is your little switch, so you apply your AC power to that full bridge rectifier. The full bridge rectifier converts the AC to DC power, and then a portion of the current is passed through that 10K resistor, which is a potentiometer, right? The circuit comprises a 10K potentiometer, the two 100 ohm resistors, and a 50 microfarad capacitor delivers gate drive of the SER circuit. So they've created a little gate triggering circuit. So by adjusting the 10K resistor up and down and having those two resistors in series with the 50 microfarad capacitors, they've reduced the overall current and voltage to the SER's gate. And you can see the bottom part of their little circuit there is connected to the cathode of the SCR, right? It always has to be connected to the cathode. So the negative side of those 50 microfarad capacitors are connected to the SCR. So the diode D1 protects the circuit from reverse voltage spikes, and the rating of the bridge rectifier in the SCR should be 25 amps in this case, with a peak inverse voltage of 600 volts. What does that mean? What that means is if that SCR is reverse biased and has a large reverse bias voltage on it, if it exceeds 600 volts, that will break that SCR down and cause it to fail. So they have a peak inverse voltage, PIV, of 600 volts. The diode D1 should be rated for 2 amps with a peak inverse voltage of 600 volts as well. The circuit can handle a load up to 10 amps. The SCR should be very well heat sinked. What that means is that SCR doesn't have the ability to dissipate its heat, and so you have to attach it to a heat sink, which allows the heat to transmit itself into something like a aluminum heat sink with fins. So again, we can go through this operation here. We have our little rectifier there, and we have some DC voltage. That DC voltage is significantly lower than 120 volts AC. I think it's 0.45 times the 120 volt RMS voltage. Let's see if it would be pi divided by 2, or 2 divided by pi, which would be 0.866, I believe, times the voltage. We're not really going to get into that too much here. I did do a rectifier class where I covered all the different bridge configurations. It's not a class that a lot of people like to go over anymore because we don't use a lot of them. But anyway, so the voltage is sitting there on the anode of the SCR, the opposite of the arrow, and the other side of the voltage is at the bottom of D1. So you've got your AC socket. You plug your drill into the AC socket. When somebody activates that SCR, whenever it goes positive, it'll fire that SCR and it will cause it to rotate. So you can adjust that 10K pot up and down and vary actually control the drill. You could use PLCs to control motors. We do it a lot, and that's what we kind of talked about. So here we have a ladder logic to control the system shown. When the push button 1 is on and push button 2 is off, the blue light turns on. As long as the button 2 is on, the red light turns on, independently of push button 1 is on or off. If both push buttons are off, then the lights are off, or the lights turn on. Neither light turns on. Really doesn't help you here. It's just a black box, if you will. But again, if you don't understand PLCs, I highly encourage you to watch the PLC training courses that I offer. You'll understand this much better. Here's an example of a typical motor starter. This is a 20 horsepower motor. At the top you have a diverter valve, which actually is for a well pump, a water well pump. We'll start off on the left-hand side. I apologize you can't see this, but I will give you PDF documents of all these slides so that you can see these slides real clearly and follow along. On the far left-hand side, you've got a circuit breaker. Then you've got a surge arrestor below that. It's a SA1 at the bottom of it. And so what that surge arrestor is a capacitive type circuit that anytime the voltage spikes high, it'll actually smooth it out, right? Or sometimes you put a metal oxide resistor, MOV, in there, and it'll clamp it to 0. On the top, you have a small little circuit breaker, 15 amp circuit breaker that feeds a diverter valve. So here what they do is they open up the diverter valve, and then they start the motor and allow the water to flush that line. And once you're done with that, you close the diverter valve and you continue to run that well pump. Whenever that M contact, the M main contactors are closed, the motor will start. Here you have CTs, so this is a fairly, you have a CT design where you actually have the overload short circuit condition there, and then you have at the bottom to the left of those overload short circuit CTs, you have the PMR, which is a phase monitor rotation device. It's protected by fuses. To the left of those fuses, a phase monitor rotation device actually looks at over voltage, under voltage, Phase reversal, if for some reason somebody rotated your phases, it would not allow this pump to run. If you single phase this motor, you'll destroy it on a single phase motor, so that PMR detects against single phasing as well. And it also detects on over-under frequency. So that's a very powerful time mark device. I think Time Mark Relay sells it, probably Omnicon or whoever else sells it as well. But it'll actually protect that motor. You have on the left a CPT, a control power transformer. It is taking that 480 and stepping it down to 120. Remember I said on X2 you must ground it per UL, and then on the hot side of that transformer CPT, the 120 volts, you'd have a fuse. Goes to a contact PMR, which is your phase monitor rotation. So if for some reason you don't have the correct phase rotation, or your voltage or frequencies out of whack, then the PMR will open. That contact will open and you'll never be able to start the motor. The first line, the rung line number, I think it says 1 there, goes to a limit switch, and as long as the valve is open, if somebody actually walks over there and presses the diverter valve, then it'll allow you, there's a vibration switch right there, it's a VBS, so they're looking at the vibration of that motor, and as long as that motor's not vibrating real bad, that switch will be closed. Next you have a stop push button, and if all these things are true, right, your diverter valve is open and your vibration switch is closed and your stop push button is closed, what will happen is that power will rotate to the bottom there, and it feeds a vegetable oil drip system that drips oil onto the solenoid. It also energizes that timer, a 300-second timer. So that allows that diverter valve to stay open for 300 seconds. Actually, it's just telling the operator, hey, leave the diverter valve open for 5 minutes, 300 seconds. Once it times out, it'll say pump is ready to start. So you can see at the bottom right there, it says TR1. It says pump is ready to start, and that light lights, and that tells the operator to go ahead and close the, well, you can leave it open first, and once it says it's ready, that TR1 will energize, and then the M contact on the very top, that main contactor, will energize, which will latch in that start button whenever he presses start. So when the timer is done and the operator presses start, the TR1 is true, the M contact, the motor starts, right? And as long as it doesn't have an overload, it stays running. It seals itself in around the start button, and the elapsed time hour meter starts to turn on. And then you can walk away from the motor at this point. It's encouraged at this point, you also want to close your diverter valve, right? Because once the well pump motor is running, you want to go ahead and press the close button on the diverter valve. The open and close push buttons are not shown on this schematic, but this gives you a good overall understanding of how a typical control scheme would work for a motor. So now the next topic, finally, is variable frequency drives. We've covered AC induction motors, we've covered motor efficiency, we've covered motor assessment, we've covered motor controllers. Now we're going to finally cover the variable frequency drives, and then after we've done that, we'll talk about harmonics and then application considerations. Okay, so here we have a block diagram of a basic variable frequency drive. It doesn't even have to be a variable frequency drive. It could be or a VFD IGBT type drive. It could be anything. But here we'll just kind of go over this. First, you have your controller, generates and sends a reference to the drive that could be to ramp it up or to ramp it down or to do different variations to it. The drive itself controls the speed, the torque, and the direction of the motor. So the IGBT drives can actually increase and decrease the speed of the motor, which we all know that. They can also change the torque, so you can set it to constant torque or a variable torque, or however you want to set it up. Sometimes, like for a conveyor system, you'd have like an S-shaped pattern, right? Where you would start out slow, then you would go to a certain speed, and then go to the full speed. And that makes sense because you want to start out slow. You don't want to knock all the bottles off on this conveyor belt. And then you have a separate power supply. Sometimes the power is actually created inside the drive from the AC source, which is usually the case. You have the motor. It changes from one form of energy to rotating energy, right? So it's electrical to mechanical energy. You have some type of a coupling that connects the motor to the machine. And then the machine is actually the device that performs the work. It could be a pump or a fan or things like that. So that's an overall diagram, simplified diagram of all the different pieces. Um, Here we have an old-fashioned device where you have a constant speed motor and it's coupled to a variable diameter pulley system. So the diameter of this pulley increases and decreases, which causes the output to increase and decrease. So you're actually like changing the speed on your bicycle, right? You're adjusting the diameter of the sprockets, and you can go faster or slower, or it'll spin real fast, or however you want it to go. That's the same concept here. It's limited on how much you can vary it, but you can have a constant speed AC motor with this variable diameter pulley. Just an example. Here is a constant speed AC motor coupled to a pump, coupled to a control valve, and then you've got some type of a hydraulic motor, and you've got a fluid reservoir. So this is another type of a variable frequency drive, or variable speed drive rather, not frequency drive, but you have that constant AC motor running. It's driving a pump, which causes the liquid, the hydraulic oil, to circulate in this system. And by opening and closing that control valve, you can control how fast that hydraulic pump or that motor moves. Therefore, you can actually change the speed of the motor. So you could bump into one of these at some point in time in your life. They're kind of phasing out, but every once in a while you do run into them. So I just wanted to point it out that is a type of variable speed drive. It's a hydraulic type motor. Here's another type of motor. It's a constant speed AC motor coupled to a what we called an eddy current drive, right? So you have this input drum, and then you have your assembly, coupling assembly inside. And the idea is you would change your excitation, your DC voltage on that coupling field. What that does is it magnetically attracts that coupling assembly, right? And so if you magnetically couple it real tight, it turns on and off, right? And what happens is as you turn on and off, the constant speed motor, the shaft's always turning, and the input drum is always turning. So as you increase the magnetic field on the coupling field, you're actually causing that coupling assembly to spin. So if you put it on full blast, it would rotate at the constant speed of the AC motor, so they'd be directly coupled together magnetically. And this is what they call an eddy current brake or an eddy current device. And then you can have that shaft rotate at variable speed. So if you let off that field, it'll slow down. If you engage it, it'll turn on, and you can be fairly precise with this device. It will get pretty hot, but that is another example of a variable speed output. Not very efficient, but it's an example. Here's another type of variable speed drive. Here you have a constant speed AC motor coupled to a DC generator. So you're spinning that DC generator, and you're making DC voltage, right? And so by increasing and decreasing the generator field coil's voltage, you can actually increase and decrease the output voltage on that DC generator. And of course, if you have full DC voltage out, generator voltage out, the motor will run at max speed. If you decrease the field coil, the field current on the field excitation system, the voltage will decrease, and then the DC motor will decrease as well. You can also have, which we've discovered, is if you adjust the motor field excitation system, if you decrease the excitation system on the motor, that motor will speed up. If you increase the motor excitation field, that motor will slow down. So in combination with these two items, you can actually increase and decrease the motor speed. You might want to set that generator speed at a certain reference and leave it, and then you might want to adjust that DC motor speed reference if you want. But you can do them in combination and control it. So that's another example In all these examples, they're not very efficient, but I do want to point them out because there's different types of variable speed drives. This particular design right here is extremely controllable. It's very, very smooth. If you had like a crane or something, you'd probably want to use a DC motor. I don't know if VFDs are the common drive type VFDs have come up to speed and they're smooth enough for a crane operation, but a lot of those old cranes, and I'm talking about on a big barge, right, where they have these big old cranes and these moving around and lifting things and stuff like that, those are usually driven by a DC generator coupled to a DC motor. And finally, we have a DC drive. Where we used to use these is the old drilling wells. We had what was called a thyristor house, or I think Ross and Saldo Ross Hill made them as well. They had a version of this. Maybe Robocon made it as well. So you have three-phase input. It's just a 6-pulse SCR drive, rectifier output, and that's coupled to a DC motor. So by changing where you fire into these AC waveforms, you can vary that DC voltage output, and you can change the output of the DC drive, the voltage, and control the DC motor. In conjunction with that, you can actually adjust the field as well. So that's actually a different type of DC drive. Used to be in the 80s, DC drives ruled. The Thyrig, the Thyristor, what do they call them? The Thyrig 1, Thyrig 3 systems pretty much dominated the system. Then Ansaldo Ross Hill got involved and they dominated the systems for a while. And then ultimately this all phased out to where VFDs kind of caught up to the technology and were able to control it. And these are slowly phasing out of these rigs. And this is a standard AC drive that you would see today, right? For an induction motor, you have your three-phase power goes into a rectifier. It goes into the diode, has a fixed DC voltage output on the, and then the AC portion here, they actually drew a transistor. So that's a bipolar transistor. But more than not, you see those as IGBTs, insulated gate bipolar transistors. And then you vary the voltage and the frequency on that AC motor in a linear fashion, and you can control the speed of that AC motor. And you can sit there and adjust the pot. And then, of course, you could tie these things back. Like you could get an encoder off that AC motor or a tack, and you could feed it back and get direct feedback to that drive and be very precise on how you're able to control that device. Again, there's your VFD. We saw this picture before. You have a run, start, stop. There's a lot of functions you can do. You can see it's running at 60 hertz, and it has a nice little display there. This is inside that particular VFD. Years ago, you don't see it, but behind this, you see that aluminum plate, a big old metal-looking aluminum plate, and there's a black little device bolted to it on the far left-hand side. That is your isolated power module. And that might be your IGBT or transistor or whatever this design is. The capacitors are used for the DC bus, and basically years ago those capacitors were just regular old electrolytic capacitors, and they found out that they needed to be a special low resistance capacitor, so that kind of evolved as well. These pictures are pictures of different drives from Toshiba International. If you live in Houston, Texas, or if you ever get a chance to come to Houston, Texas, go to Little York and Little York and 290, and you'll find Toshiba America. And what they have there, and I just grabbed these off the internet, but the G9 drive is a very nice drive. You can actually go to a marketing class there. They have a phenomenal, great marketing class. And they'll go over that drive. That drive by far is extremely robust, capable of withstanding a lot of harsh duty. Then you have a larger P9, which is more like for HVAC control. It goes up to higher voltages. You can go directly to their website and look at all this information. And then you have some medium voltage drives. Well, I think on the left-hand side is not a medium voltage, but that large, yeah, I think they both are actually. But they can actually take these up to 4160. And the way they did it is they stacked some of these IGBT modules so they could raise the voltage. And then you've got an outdoors duty type VFD on the bottom right-hand side. So these These IGBTs, I think, were originally designed or invented by Toshiba, and certainly the IGBT module, that power module, was. A lot of people use them, like the Mitsubishi. Some people nameplate these drives, but by far, Toshiba was the leader in the IGBT technology, and certainly the leader in the medium voltage design. Just to kind of go over some of this, I know we kind of talked about this, but DC voltage, it rises and it stays at a constant value. Typically, that's what it would be, like a battery, right? It's not cyclic in nature. It doesn't change, right? As opposed to an AC waveform, you would have a positive portion of that waveform, and then it would go negative, and that would be called one cycle, right? One cycle is 1/60th of a second, right? Which is 16.47 milliseconds. And if you had a three-phase, that's a single-phase power source there, but if you had a three-phase power source, you'd have three AC waveforms all displaced by 120 degrees. By the way, that DC voltage output right there on the far left is very, very smooth. The output of a rectifier, a three-phase rectifier or single-phase rectifier, would have an AC component ripple on top of that, and we can show you that later as well. Some of the things we need to talk about is voltage and current. This particular waveform that you're looking here is, you've got your voltage is the dark line and the current is that dashed line, and you can see how they start and stop at the same time. That's what we say that is in phase, right? The current is in phase with the voltage. That phase relationship is measured in theta, a degree angle. If you took cosine theta, you would find out that that equals the power factor, right? So I think it's inverse cosine theta is the power factor. So this power factor in this case is 1. It's said to be unity power factor. If the voltage or the current leads or lags each other, then you have a leading or lagging power factor, and then of course you can you would need some type of correction device there. Again, this is a AC sine wave, a single phase AC sine wave, and the horizontal line is in seconds, right? So one cycle is the frequency inverted, so it's 1 over 60 hertz would be 60. It's 16.67 milliseconds. So one cycle is 16.67 milliseconds. Here we have a three-phase circuit. So again, you got your phase A starts first, and then you got phase B starts second, and you got phase C starts next, and they're all 120 degrees displaced of each other. So the one phase is 360 cycles, or one cycle. So 1/3 of that cycle is where you would start your next phase. Here we have a DC voltage, and what happens when we have a capacitor in the DC voltage? Initially, when you apply voltage to that to that capacitor, it's a dead short, right? And then it charges up. So that's what you see is when they applied voltage, it was at 0, and it's actually a dead short, and then it slowly charges up. With DC, the charge remains on the capacitor. So even if you removed that voltage, that capacitor would still be charged. And eventually it would bleed off, but it could hold that charge for a fairly long time. In an AC voltage, the AC, the capacitor is constantly charging and discharging. So on the DC circuit, you'd want to have an electrolytic capacitor, and that's polarity sensitive, so you have the positive and the negative. On the AC voltage, you do not want an electrolytic capacitor because you'll blow it up. So you want a non-polarized cap, and you can see it would charge and discharge that capacitor. So if you were to look at this happens to be a single phase rectifier, right? And so what you see is the output of this rectifier. Every time it goes positive, you see the positive pulse. Then when it sees the negative, you don't see anything. It's flatline. Then it goes positive again, then it goes flatline, then positive again. So if you put in a 10 microfarad capacitor on this, what would happen is the DC voltage would go to peak, that positive peak right there, and then it would start to discharge, right? Because there's nothing charging it. But then the next pulse would pop up, and then it would slowly discharge. So your power would be somewhat rippled. If you had a higher capacitance, 50 microhertz, let's say, then you can see the different change in the waveform. That waveform looks suspect to me because if you increase your capacitance, it's going to hold the DC voltage higher. So I think the waveforms might be reversed there, but I don't know where I got this picture. When you energize a coil with a DC voltage, you have an expanded magnetic field. Okay? When you de-energize that voltage, that magnetic field collapses. And something I want you to know is if you have a switch here and you close in that DC voltage, that magnetic field energizes, right? And then the top, the north to south, that north would be positive, that south would be negative. If you open that switch and you have no voltage, as that field collapses, that voltage reverses. And the south side of that coil becomes positive and the north side becomes negative. It actually reverses the voltage. It's called an inductive kickback voltage, and it can get up to 10 times the source voltage. So if you have a 24 volt DC battery and you connect it to a large coil and you energize it and then you de-energize it and you captured it on an oscilloscope, you would see a spike, a negative minus 240 volt spike goes negative because of that collapsing field. It's not a big, wide spike. It's just a real narrow spike, right? It's the inductive kickback of it, but it's enough to destroy things. So it can cause all kinds of havoc in your design, especially with electrons. Here we have an AC voltage across a 1 millihenry inductor. And if you recall, on the AC voltage or the inductor, it is omega L, right? So omega is 2 pi times the frequency, and L is constant. So L here would be 1 millihenry. So if this was an AC waveform, a 60 hertz waveform, and you had 2 pi times 60 is 377, then you're times the 1 millihenry. So you would have so much inductive reactance. So you can see that the inductive reactance opposes any change in current in this AC waveform. So the current would be a certain value. If you increase that millihenry value, increase the inductance by 25, 1 to 25, the current would be further reduced, right? Because omega didn't change, 2 pi times F didn't change, but L changed, it increased. So therefore your resistance increased, right? And so just like Ohm's law, E equals E divided by the X of L equals I. So X of L increased, right? So the voltage did not change, and therefore your current decreased. And that's what they're showing you here. And we talked a little bit about this. We said that an in-phase voltage and current generated by the utility. So the load is what sets this relationship, right? If it's a resistive load, a heater or an incandescent lamp, it will be unity power factor. If it is a like a motor or a current or a capacitive load, then you'll have a out of phase relationship, right? And usually you have something like 0.8 power factor for a system. So you're said to be out of phase. The phase voltage and current are caused by use of inductors. So here we have the actual voltage and the current. The picture doesn't show you really well because it kind of looks like the voltage is the dashed one and the current's the dashed one. But you can see the dark line is the voltage and the current is the dashed line. So the current is leading the voltage, right? So, or lagging, the voltage is lagging the current. Which one comes first, I guess you would say, right? So here again, we talked about the power factor. And if you have a resistive circuit, like an incandescent light or a heater, then you would have a power factor of 1, right? If you have an inductive circuit, you have some phase angle displacement, and so if you calculate that, let's say if you knew what that angle difference was there, you could actually calculate by using cosine inverse that angle, and you could calculate the power factor. In this case, you've got 0.5 or 50% power factor, which is extremely low. So you have, and this could be in an induction machine. Certainly on a 2 horsepower induction machine, you saw the power factors were very low and the efficiencies were very low. Here's a typical drive. You've got a reactor in the front of the DC drive. And why would we have the reactors in front? That's a good question, right? Well, I'll tell you why. And the reason is you have a rectifier. That DC drive module is nothing more than a rectifier, and it's got some fuses in front of it. And so this rectifier has a lot of harmonics that we haven't really talked about yet, but we will talk about it. And those reactors actually have different resistances for all the different frequencies that the harmonics generate. And that reduces the harmonics reflected back to utility. It also has it opposes any change in current, so it's a smoothing effect. It's a smoothing effect for that DC motor as well. You could also have a reactor on the output of that drive as well if you wanted it. These are different types of relays. So here we have a 24 volt DC coil, and then we have another device on the output. We've got an MOV around it, and a metal oxide varistor. A metal oxide varistor, what it does is whenever it sees a spike or a voltage change, it protects that load. So if you had a 130 volt MOV, anytime that it goes over 130 volts, it would clamp it to 0 for a very, very short period of time. And when it did that, it would protect that load from that spike in voltage. And the next one, instead of a metal oxide varistor, you could use an RC snubber network. And an RC snubber network is a resistor and a capacitor put in series, and it also has the same effect. If it sees a real high pulsing voltage, it'll actually smooth it out. It'll snubber it and protect the load. Here we have a 120 volt control coil, 1M, and on the output we have our armature to the DC motor, and then we have the DC module drive. So if 1M is pulled in, if the AC power comes in, it energizes 1M, and then that AC power is rectified, and then 1M contact pulls in, and the DC motor runs. So whenever the AC voltage drops out, the 1M contactor would drop out as well. Here we have a transformer. We have the primary AC input, and we have the secondary AC output on a common core, right? So that's how a transformer works. And it's just a simple relationship. If it's a 4-to-1 ratio, and you have 480 volts on the primary side, you'll have 120 on the secondary side. Transformers are measured in kVA or VA, and you can calculate the current. A transformer is somewhat dumb, and the reason I say that is because you can sit there and overload it, and then there's nothing really that'll stop it from burning itself up. So you have to put a lot of protection around this, either fuses or some type of a relay device if it's a real large transformer, but you want to fuse both the primary and the secondary side. Per the NEC 450, one of the tables in there says you don't have to do that. You could just do the primary side. I always like to do the primary side and the secondary side. So, and that's the symbol for it if you're doing a schematic. You can also create feedback to drives for diagnostic purposes or for control. So here they have, let's say we have an AC drive with diagnostics. So you have a motor at the top, and you've got your 3-phase input at the bottom. You see those CTs? Those CTs are current transformers. So what they are is toroids, and as the current increases on that AC waveform, the output of the CT actually increases, and usually the CT secondaries are 5 amps for USA and 1 amp for European applications. You never want to open that CT under any conditions. You always want to keep it shorted. On the PT, you never want to short it. You always want to keep it open. But if you were to open that CT under load, that CT would blow up, or it would create such a high spark or a high voltage spike that it would could hurt somebody. I've actually seen, I didn't actually see it. I had my back turned to it, but
one of the technicians actually cut the CT wire on a large medium voltage switchgear, and it knocked him off the ladder. And this guy was a big guy. And fortunately, one of our techs was there and caught him, so he didn't really get hurt. But it's kind of scary. You never want to short those out. So in this case right here, these CTs are actually used to provide current feedback into the AC drive. And so the AC drive can predict what the input current is. If it sees an overload condition, it'll shut itself off and protect itself and isolate it from power. So that's kind of a cool situation. You see a lot of these VFDs have this advanced protective capability, so you don't have to add a lot of additional items. The output of an IGBT is what we call a sinusoidal wave, a pulse width modulation control. And so here we have an AC waveform is superimposed on the voltage pulse waveform for illustration purposes. You can see that this is one cycle, and the AC waveform is perfect sinusoidal waveform. But the IGBTs or the transistors or the GTOs on the output of that VFD, they can only turn on and off, right? And if you recall, well, I haven't really shown you yet, but on the DC bus voltage that feeds the IGBT inverter portion of those VFDs, what they'll do is they'll turn it on and allow that positive voltage to come on and then turn it off real quick, right? And then they'll turn it on again and leave it on a little bit more, and then they'll turn it off again. Then they'll turn it on and leave it on a little bit longer and then turn it off. And so if you took calculus or something and you did the integration of these square waves, you would find out that the RMS value of that integration, the sum of that integration, is equivalent to the RMS value of that sine wave, and that's why it works the way it does. The motor is actually a large inductor, and because it's an inductor, it actually has a smoothing effect on the output of that waveform. So the motor's actually taking the brunt of this. Something that I also wanted to mention is that when you have a three-phase power, you remember you're shifted by 120 degrees. So the difference between phase A and phase B, there's always a difference, right? Because you're going positive, and then you're going positive again, and then you're going positive again, and you're going to have a difference for a very short period of time between A, B, and C at all times, an imbalance, a current imbalance. And that current imbalance causes a circulating current in the bearings, so you got to be real careful with that. Now you can see on the negative side of that waveform, what we're doing is we're turning on and off the the IGBTs so that we go negative on the output. And so again, it's the same thing. So that's what they mean by pulse width modulation. They're actually increasing and decreasing the width of the pulses to come up with the equivalent RMS value if you were to integrate it, right? So that's how that works. There are some drives that have a standard square wave. So here you have your sine wave, and you've got your pulse width modulation voltage waveform superimposed on that AC waveform. You don't really see these too often because it's technically not the same, right, as the smaller pulses on the left. You know, at the beginning of it, you don't need these. You want them all different widths, right? So you don't want to just arbitrarily turn it on and off. But that's pretty much what they used to do a long time ago. Here's a block diagram of a basic sinusoidal pulse width modulation drive. On the top you have your rectifier, which is and you have your input voltage. It's three-phase input voltage, 460 volts or 230 three-phase. You could put a single-phase power voltage right there, and it would still rectify it to DC output voltage. You've got your filter, which is a capacitor, and then you've got your inverter. So here they've drawn it's not an IGBT, it looks more like a transistor. Well, you know, whatever. It could be an IGBT, and then they've got that little diode that goes around it, and we'll explain how that works here in a little bit. Then you've got your base drive circuit, which actually fires the IGBTs or SCRs at the proper time so that you create that pulse width modulation circuit. That is a transistor, an old transistor circuit, and then the output of the motor would actually run from 3 to 60 hertz and 460 volt AC depending on the output. You have on the far left-hand bottom side of that, you have a reference signal, and then you can accelerate or decelerate depending on that reference signal. And then so you want to accelerate and decelerate for 1 to 5 horsepower from 1 to 20 seconds. So the nice thing about these VFDs is you don't have that big locked rotor current. You don't have that big inrush current. So if you were to model a VFD in like SKM or ETAP, you would just treat it like a static load because it really doesn't have any inrush. The only time you would include inrush on a VFD application is if it had a bypass device that went around that VFD circuit, the power circuit at the top, and allowed it to start across the line. Next thing you have is a volts per frequency hertz or volts per hertz control. And remember I said that needed to be linear, so for 7.5 to 100 horsepower, you want that to ramp up at 6 to 60 seconds. So, and then you have your sinusoidal pulse width modulation control, which drives the base drive board, which drives the transistors in this case. So that's a basic block diagram of a sinusoidal pulse width modulation drive. This is a little nicer because it kind of gives you the actual power diagram of the rectifier. So on you got your AC input on the left, the input, and then that is a 6-pulse Gantz bridge, three-phase full-wave bridge, and the output of it charges that DC bus, right? And so when that DC bus is charged, it charges that capacitor. And if you recall, I said initially when you apply the power to a capacitor, it's a dead short. And then it allows itself to charge up. So sometimes they put resistors and stuff in series with that, depending on the size of that capacitor, so you don't see a large inrush current due to the capacitor charging. And then you've got your outputs, your transistor outputs, and then you've got, you see the rectifier is repeated on a smaller scale across each transistor. And there's a couple of reasons why they would do that. One reason is if for some reason the output of that rectifier, or the motor, right, if it became a generator, it would actually increase the DC voltage, right, or the AC voltage. It would generate power back. That rectifier right there actually takes that the output generated a motor, it's becoming a generator, and it rectifies it and charges up that capacitor. You could, in this case, go into a DC over voltage. In fact, that's what happens on a DC over voltage condition. If you've got a large load that's driving that motor, when it's accelerated too fast coming down, it can actually turn into a generator and do a DC over voltage. Later on, you'll find out that they add like DC brakes and things like that. So if we look at that pulse width modulation transistorized sinusoidal type diagram at the bottom, you can see in order to turn, this is volts A to neutral, right? If you were to look at that. So you want to make that go positive, right? So how would you make that go positive? The first thing you would do probably is fire that top left SER, and then you would also fire the bottom right transistor, right? So you'd have a path between A and C, right? And you'd also have a path between A and B. So you could, if I labeled these 1, 2, 3 at the top, 4, 5, 6 on the bottom, I'd see 1 and 4 turned on, and then later I'd see 1 and 5 turned on, right? And then you would just alternate between these, and you would generate these different output waveforms. I think that's all we'll cover. Here we have our volts per hertz waveform, and remember when I said that you don't want to increase your motor voltage to max, right? You want to actually allow your frequency to increase as you increase your voltage, right, on your motor. And if you don't do this, what happens is you don't have that counter EMF at lower frequencies, right, at lower speeds. And if you don't have the counter EMF, you have to compensate that for that. Otherwise, you'll overheat that motor. So if you're at 50% of the motor voltage and 50% of the speed, 30 hertz in this case, you want to make sure that your voltage is half of what it ordinarily would be. Because if it was at 100%, your EMF would be much higher than your counter EMF, and you'd have an overheated condition. So that's why they created this this volts per hertz curve. And they learned this the hard way, because the first VFDs that came out didn't do this, and they applied max voltage and just changed the frequency. And they found out that as they adjusted the frequency lower, it actually started overheating these motors. Here's a picture of a a typical starter. I think I pulled this right off of Toshiba. They've got some manuals and stuff you can actually download. We'll go over it. You got RST. RST is ABC, but in Japan or European terms. Sometimes they use UVW. So your input AC is three-phase, comes into RST, that's ABC. You have a MS1 coil. So whenever it sees the proper voltage, it energizes. MS1 energizes. And then what it does is initially what happens is you see that R1 around that MS1 contact on the output of the full wave rectifier. What happens there is it allows to charge that capacitor. Remember I was telling you that you want to allow that capacitor to charge, so you apply power, you allow that rectifier to rectify that voltage to a DC value. It goes through R1, charges up that capacitor back through FU1, and when it comes up to a certain point, then MS1 pulls in and shorts out R1, and then you're able to run it. So that way you don't have that large inrush current due to the capacitor charging. Next you have a MCT, a Hall effect current transformer. So you're looking at the DC voltage, the DC current flowing to the three-phase transistor bridge right there. So you want to make sure you don't go in an overcurrent condition. You're also looking at the voltage of the DC voltage. So you can see it goes to an under voltage below that LED in that capacitor. You'll see under voltage, over voltage, over current detection. So if the LED lights OV/UV, you know you have an over voltage or under voltage. If the LED lights and it's an OC, you know you have an over current. So this this circuit, or this electronic circuit, is actually designed to protect that motor and the drive. So, and again, if that motor goes into a regenerative state where it becomes more of a generator, it'll backfeed that that DC bus, overcharge the capacitor, and if it does, it could you know, damage the capacitor. Rather than that, you go over voltage and trip it offline. Or you can go at the top where you see that regenerative power discharge unit option. What they do is they actually have a resistor up there, or they have a device that will dissipate that over voltage condition and allow you to accelerate down. Below the full wave rectifier, you have your control power and power supply. So you have your little control power transformer. It's got a lot of different voltages to create those the different voltages you need for like gating and stuff like that. Below that, you have your acceleration and deceleration stall prevention. And this is really a picture of probably an old H1 drive, an old analog drive, and you'd actually adjust these pots. Nowadays, everything's microprocessor controlled, so you don't have all these pots. But this is kind of a nice little overview. So you get a current feedback that goes into that accel decel, prevents the stall, and then you get your volts per frequency control onto the right of that, and then it drives that sinusoidal waveform pulse width modulation control, which gives you your base drive amplifiers. If you have an over voltage, under voltage, or over current detection, the output of that would stop the gate pulses, right? You'd have a faulted condition. If everything's fine, then the base drive amplifiers will amplify that signal to fire the transistors, which would ultimately drive the AC motor. So that's what a variable frequency drive looks like, an old analog type drive. Here's all three phases, right? And again, UV is, remember it goes UVW, right? ABC. So this is U to V is A to B. V to W is B to C. And W to U is C to A. So it's all three phases, and they're actually shifted at different times. So you can see U and U to V is phase A, right? A to B, and it's going high here, and then you can see there's all these imbalances, right? Because you're going, you know, if you were to look at the center of that that bus, you'd actually go positive, full positive, and then you reverse it, you go full negative. So these are big swings in the voltage. And what that does is it causes that imbalance. But it's filtered out. Like if you were to look at the current on the output of this rectifier, you'd find out that it's pretty filtered out. The voltage is not, but the current is. And the reason it's filtered out is because the motor acts like a big inductor and opposes any change in current. So you see it on this picture right here. You have an oscillograph. You've got your pulse width modulation voltages, and then you actually see your current. So your current is actually smoothed out because of the motor's inductive effect. It's actually like a big inductor. Here's an AC sine wave broken out even further. So you can see on the positive side you have your peak voltage. If somebody says it's peak to peak, that's usually the square root of 2 times the RMS value. Your RMS value is 0.707 times peak. So if this is 120 volt standard waveform coming out of your receptacle there, your peak voltage would be 169 volts. Your RMS voltage would be 120 volts. And your average voltage would be, I can't remember off the top of my head, but you can calculate it. You just take that peak, that 169 times 0.637, and you'll know the average voltage. And the duration of one cycle is 0.0167 seconds, or you'd shift the decimal place over 3 times, and it'd be 16.74. I think it's 16.46 or something milliseconds. So we'll just round it to 16.7 milliseconds. And that's you need to understand these different values, because as you do rectification, you'll charge to the peak value, right? And you need to know that. As we look at a diode, this is a diode. You have a P-N junction. The P junction is your anode. The N junction is your cathode. And the direction of current flow, if the anode is more positive than the cathode, your direction of flow would be through that anode to the cathode. These are the diode rectifier volt ampere characteristics. Your forward current, which is primarily your that's where you usually want to be when you're forward biased, you'll have a very small voltage drop across that diode. If it's a small 1N4001 diode, you're probably looking at about 0.7 volt drop. I think for most schools they use 0.7 volt drop. For a large power diode, I mean like a 200 amp power diode, you'd probably see more like a 0.35 volt drop across it. So when you go into forward current mode and you're pulling 200 amps through that diode, you'll see the voltage drop across it is only like 0.35 volts. When you go into a reverse current condition where you're reverse biased, if you're forward biased, you'll go into the forward current condition and you'll have a small voltage drop. But when you're reverse biased, you will have a large voltage drop across that, and it's called the peak inverse voltage. That peak inverse voltage eventually had this curve. It doesn't show it, but if you kept going down that reversing bias voltage, it would fall off and go really hard negative, and it has a certain value which is called the peak inverse voltage. Rule of thumb that I've always used is solve for your current that you know you're going to have flowing through that device and double it. So when you size that component, let's say if you know it's 50 amps, you put in a 100 amp device, right? And then figure out what the peak inverse voltage is going to be, and then multiply it times 4. Then you can't be wrong, right? You can't go wrong. You'll never fail at that device, and you won't have to worry about snubbers or MOVs going around it as well. Just a little rule of thumb I learned through the years. The direction of the current flow, again, is flowing in the right-hand side. It goes from the positive, goes through the anode, and then passes through the cathode and continues to go. If you remove voltage, the current flow stops. Unlike an SCR, once you energize it, you can't stop it unless you remove that current flow. Even if you remove the gate signal, it's still going to flow as long as there's a load and some current flowing through it. But on a rectifier, it just stops. There's nothing that you can control. It's just there. So here we have a half wave rectifier. We have one diode in series with an AC waveform and a load. So you can see that when it goes positive, you can see the positive pulse across the load on the bottom of it. When it goes negative, there's nothing. There's no output. So then when it goes positive again, if there was another cycle of this waveform, then you'd see the pulse. And so you saw this when we were looking at those different capacitors. Remember how the capacitors would smooth that output away? So if we were to put a capacitor across that load, it actually would have a smoothing effect. The next bridge is that full wave bridge rectifier. And if you look at that full wave bridge rectifier, you see an AC waveform right there. So the positive, it flows to the positive top right-hand side of that diode. And it also, let's see, the current flow would be through the positive and then back around. Let's see, AC goes this way, and the negative portion of it would go the other direction. So you'd see the complete current flow. So basically what you do is every time the sine wave goes positive, you get a pulse. And every time it goes negative, you also get a positive pulse. So you actually see double the pulses as a half-wave rectifier. You only see the positive pulse get through, but the negative, you actually see both positive and negative pulses get through. And then, so then you have the next rectifier you would see is a three-phase bridge rectifier. I said 460 volt. That should say that's a typo right there. That 460 should be 460 volt AC, three-phase AC input. And then that rectifier right there is a three-phase Gantz bridge, and the output is a 650 volt DC output, and that's usually why they have 700 volt DC or 750 volt DC drive, big traction motors they used to use on those top drives. So that's what a three-phase bridge would look like on the front end of a rectifier or the front end of a VFD. SCRs, we talked about them. You've got your anode at the top and the cathode at the bottom, and then you've got your gate. So your current flow would flow just like a diode, but it's actually a PN-PN junction. So your P in the middle is your gate, right? And then the P at the top is your anode, and the N at the bottom is your cathode. And to gate that device, you would apply a positive voltage on the gate, and you would connect your reference or your common to the cathode of that device, and you can fire it and turn it on. Here's another same thing, right? I don't think it shows you anything different. It's a silicon-controlled rectifier, thyristor is the old name for them, and it's just a PN-PN junction. Here's your volts per biased voltage here for an SCR. So you can see that when you go into reverse voltage, or reverse biased, you have reverse current. It doesn't allow you to fire that device, and eventually it would fall off the edge as well, and you'd have to deal with your peak inverse voltage. So when you size SCRs, you use the same rules, right? Figure out what your current's going to be flowing through it, double it, and then figure out what your peak inverse voltage maximum for this particular circuit is, and multiply it times 4, and then you won't have a problem. You can see there's a little gate region here where when you go into 4 voltage conditions, there's a little hoop there, and then it falls off, and then it goes off to positive. So you have a higher voltage drop across this device. Switching AC thyristors or SCRs. The beauty about these SCRs is you can look at that AC waveform. They didn't draw the little gate right there, but you can look at the AC waveform and you can determine when it goes zero crossing. When you go zero crossing, you can decide when you want to fire it. So the top waveform shows the AC waveform, and then the hashed part would be your output. And the bottom part is the gate pulse, right, where you would actually gate it. So if you gated it right there, just went positive and negative real quick, a little turn on. You can do picket fence type firing and different types of firing, but if you just kick it on, it'll actually allow 3/4 of that waveform to flow through, and then it'll naturally commutate off, right, because it goes negative. And then if you do it again and you fire it, you can actually see that you'd get part of it. And that's why you would you can use this as a variable DC voltage output, and certainly you can do this on 3-phase as well. This is a different type of control. It's on the positive SCRs you have diodes. On the bottom you have thyristors. Not a bad little design. It has some drawbacks. The drawback is it can't go to 0. So it can only go to about 30% of the DC voltage. it can't always go. It can't go to 0 volts. So the motor would actually be turning even at the lowest firing angle available. So basically, what you do is you just increase and decrease your firing angle on those thyristors, and you can go from about 30 to 100% on that output DC voltage. So all the way up to, if that was 480 volt AC input, you could go up to 650 volt DC output, and then the minimum again is 30% of that 650 volt DC output. Here you have switching DC with thyristors. Again, we have a device here where you have your battery, your positive negative, or your rectifier output, and you can fire across that load. And so basically what they're showing you here is that little switch right there could short out that device. For some reason, let's say if you had an inverter where you don't have the natural sine wave, you see that's a DC voltage. The only way you're going to get that SCR to turn off is to short it out. And they call that forced commutation, right? Forced commutation. And so what they do is they have a switch that closes on it, and that way it forces it off. So here, if you look at this, so diagram A is just the DC output goes to a thyristor. If you gated it, it would never turn off because there's no way to remove that DC voltage. B is a thyristor with a switch that would show you that, you know what, even if you did have that DC voltage on that input side of that, and you remove the gate and you shut that switch, you would in effect turn that device off. So you close it real quick and then open it, and the SCR would actually turn off. And then C is a capacitor in that circuit, and that is what they call a commutation capacitor, right? So commutation capacitors usually fail if they're not sized properly. I know when I did a large job for one of the companies I worked for, we made a large rotary UPS unit, and the salesman, who's really nice guy, nice, real smart guy, really motivated, he told us, no, we're not going to use any capacitors because they always fail. So our goal was to design that rectifier without any capacitors, and the way we did that is we drove a synchronous motor, and we overexcited the synchronous motor, which gave the capacitance, or gave the capacitance to force that SCR off in the inverter condition. So that's how that would work. But if you see this device here, if you charged up that capacitor and then you fired B, you could actually reverse the voltage on that A SCR and force it to turn off. So you could actually play that way and actually do forced commutation. Here we have a true variable frequency drive, which would be an IGBT output. This is primarily, most of them are like this. I can't think of one that's not. On a smaller drive, anywhere from 1 all the way up to 200, 300 horsepower certainly would be like this. You'd have L1, L2, L3 is your incoming AC voltage. It is rectified with a standard diode front end. You have an inductor there, that DC link right there. That is for smoothing. You don't always need that, but if you have it, you can do like constant current applications. C is your voltage across the capacitor. You charge your capacitor, and then the transistor, or the IGBTs, are on the output, the circles, and that actually gives you your AC waveform output. So again, on the incoming side, you have a standard AC waveform. On the DC bus side, you'd have this ripple, right? But then you would have the current would be smoothed, and the capacitance would be so large that it would actually smooth that DC output, so that you wouldn't have that ripple. You'd have a smoother voltage. And then the transistors would fire in such a sequence that you could actually create a 3-phase waveform, which would in turn drive that AC motor. So again, you want to drive it slowly increasing the frequency and slowly increasing the voltage, so that you maintain that volts per hertz characteristic and you don't overheat your motor. Okay, so here we see an average DC output, and basically what you see is the gate pulses. If you have an early gating pulse, then you would see a higher DC average output voltage. If you have a late gating pulse, so it's later in that AC positive waveform, then you would have a lower DC output voltage. So what they're saying is you can vary the firing angle on the SCRs, and you can change the DC output voltage. So that's kind of critical, right? So if you were to take the integration of that sine wave and cut off or subtract the part that you're not allowing to get through, you could actually solve for that the RMS value of that DC voltage for that value. And the same goes for the late gating pulses. So you can what you do is you look at the zero crossing of that AC waveform, and you can determine when you're going to fire into it. The GTO. This actually is a gate turnoff transistor. I think Toshiba might have called it the giant transistor. I think there's somewhere that says that. Anyway, you got your anode, and you got your cathode, and you've got your gate, but you see how it has a little slash through it? It looks like an SCR, but it's a little slash through it, means that it can be turned on and off like an SCR. I mean like a IGBT, but for large power applications. So it's again a PNP-N, just like an SCR, but you have that gate that can be turned on and off. So an NPN transistor, the way we learned this in the Navy, is it's not pointing in. So you know it's NPN. You've got your collector at the top, you've got your base at the left, and you got your emitter on the bottom. So it's an NPN junction. So your collector is an N junction, your base is a positive junction, and your emitter is a negative junction. So if you took and did a positive voltage with respect to the emitter, you would actually turn that transistor on. When you turned it on, you would allow power to flow through that emitter to the collector. A PNP is a positive pointer in pointer, so it's pointing in, right? So pointing in pointer is the way we would do it in the Navy. So it's a collector base emitter junction. It's a PNP junction. The collector is a positive, the P junction, the B is a negative, and the E is a positive. So it's just a reverse polarity. So if you were to go from the B to the E and you applied a negative voltage to that, then you would actually turn that PNP junction on. If you take two transistors and you put them in series, where you have an NPN and an NPN, see how they're not pointing in, then the collector of the top one and the collector of the bottom one are your collector inputs, and your emitter of the first one feeds the base of the other one, and then the emitter is the second one. The reason you would do a Darlington bipolar transistor is to increase your current rating. So these are for like high power situations, and you can get more power out of them. It also provides, if I recall, a higher impedance. Power device switching times and circuit card requirements. An IGBT is super fast, right? It's the fastest of all of them. This is in microseconds, right? So it's super fast. You're looking at a 0.1 to 0.8 time or voltage to fire it, right? A bipolar transistor is a 1 to 1.5 microseconds, and the turn-on voltage is given as well. So the fastest is the IGBT, probably that's why everybody uses it now, and the slowest would be the SCR or the GTO, gate turn-off transistor, and it's 3 to 10. However, there's certain applications where you just can't use the IGBT, right, for high power, high voltage applications. So they still use the GTO in certain applications. This is the GTR configuration. Again, that's the giant transistor configurations for a Toshiba. You can see off to the left you have UVW, which is ABC, right? And these are Darlington pairs. You see how they look like Darlington pairs? Each one looks like a little Darlington pair. And so you have module A, B, and C, or you can have individual modules as well. And then your output would be a positive and negative bridge. So these are isolated modules, and the trick is you want to take this heat sink and you want to bolt it to a flat metal aluminum heat sink, and you want to make sure you put that conductive paste between them so that it properly conducts heat. If you don't, that Darlington pair would actually, or that GTR would actually fail prematurely. And this is what one of these devices looks like. It's encased or hermetically sealed in an epoxy resin. The bottom of it is an aluminum plate. It's the actual heat sink of that device. You can see your electrode and your case and the chips inside of it, and it's filled with a goo. We used to call it gorilla snot because when it blew up, it always spewed this stuff out everywhere. But that's a really cool design right there. So here you have the effects of a snubber capacitor on a turn-off characteristics of a power transistor. Remember, the RC network is a snubber network. Here they put they have the load at the top, and then they have this little snubber network between the collector and the emitter. And so what you're trying to do is you're trying to prevent that transistor from failing from different situations. And you want to help turn it off as well. It'll actually help turn it off. So you've got that diode on the top as well, so your output would be positive. Of course, this could be reversed, right? And this could be the AC output as well. So here you've got the top is the I base, right? So the power going into it at I base. And then you've got your actual waveform. So if you have no snubber, it would be fairly high. If you have small c, you can see the gradual slope of as it goes from on to off. And then you've got normal c. It's a nice easy slope. Plenty of time to turn that device off. And then large c, the voltage from the collector to emitter is kind of slowly rises. So you don't want to put too large of a c because you don't want to inhibit your ability to turn this device on and off, right? Make sure it goes as fast as it can. But again, what I usually do is I don't use snubbers, but I also oversize things so high that they never get into situations. But that's really for SCRs and things of that nature. Here's an IGBT, a typical IGBT configuration. So you have your collector and your emitter and your base, and they typically put a diode around this. Usually they come in groups of modules. You can get the full 6 SCR or IGBTs in one module, or you can get them in little pairs, or you can get them in single circuits as well. So you can see you got your C1 at the top, and you got your E2 at the bottom, and you've got your common E1/C2, which would be an AC output waveform. You'd connect your positive bus to the C1, your negative bus to E2, and then you'd have your gates, gate for B1 and gate for B2. Base 1 and base 2. And here's your equivalent symbol for the equivalent circuit and symbol for an IGBT. So you can see you actually have a MOSFET on the front end of that. I don't know if you remember what a MOSFET is, but if you took the professional engineering exam for power engineers before the last couple of years, you would have had to calculate all these data. I don't think they require you to calculate this anymore. I guess it doesn't really matter. You don't use it very often unless you actually design these units. But that is the equivalent circuit of an IGBT, and then the symbol is obviously a isolated gate from the actual base of the transistor or the body between the collector and the emitter. And that's a clear indication that that is an IGBT. If the gate or the base is connected directly to that solid bar between the collector and the emitter, then you know it's a transistor. But IGBTs are really what drove variable frequency drives, and you can thank Toshiba for that primarily because they really pushed this slide on that one. We talked a little bit about this constant torque applications. Here we have our first we have that line that ramps up, right? That's your volts per hertz as it's ramping up. So at 50 horsepower, you would be running at 50% speed. And then you could put it on constant torque, and you could actually run at 100%. So you could actually run this thing from 0% speed all the way up to 100% base speed, and it would maintain the full torque the entire time. If you go over 100% base speed, that torque falls off fast, right, up to 150% of this base speed. So that kind of gives you an idea of the constant torque application. Variable torque application. Here you have your torque curve goes up, and then you've got your flow. So again, 50 and 50. You got 50 horsepower. It's 50% of the speed, 30 hertz. And then you've got your overall value right there. Your your variable torque rises all the way to the top. So as you increase your volts per hertz, you actually have these torque and flow characteristics. The idea here is that you could run this at about 70% of its value, and you should see some affinity gain, and you would say, here's an HVAC application. You have a conventional motor starter. We talked about those. You've got a circuit breaker, a contactor, and an overload driving a motor. Whenever the contactor closes, the motor runs, and to adjust the air, you would actually adjust those outlet dampers. Obviously, there's a large amount of restriction there to the airflow, so you have losses. So the idea is to replace the conventional motor starter with a variable frequency drive, and because it is an air inlet fan, you wouldn't need those outlet dampers, and you could actually increase and decrease the speed of the motor and achieve your variable outlet a bit. Again, on the variable frequency drives, what we're fixing to cover is your system description and operation. What is a variable frequency drive? What's an AC motor, a controller, an operator interface, the drive operations. Most of this we've touched on. The benefits, the energy savings, the control performance. VFD types and ratings. There's generic topologies, control platforms, load, torque, and power characteristics, available power ratings, devices by machine and detailed topologies, application considerations, AC line harmonics, long lead effects, motor bearing currents, dynamic braking, and regenerative drives. And that would actually complete the course. So we're at 4.5 hours, so we'll keep going. Here you have a basic block diagram like we showed before. We have an AC-DC rectifier. The AC is converted to DC. The filter is the capacitor, could be a line DC reactor as well. Then you have your inverter, which converts the DC to AC to an output filter. You can have an output filter would be a choke, and then it goes to the motor. So that's a basic block diagram. We talked a lot about these different devices. Commonly used solid-state switching devices for power converters. We have diodes, SCRs for rectifying devices. For the inverters, we use the GTOs, the bipolar junction transistors, and the IGBTs. And the inverters also include the SCRs. If you have a large current source inverter, you'd probably want to use an SCR as long as the application doesn't require fast switching. So again, primarily you'll see IGBTs out there on the market. Variable frequency drive, a VFD, is an adjustable frequency drive. It's a variable speed drive. There's different names for them: AC drives, micro drives, or inverter drives. It's a type of adjustable speed drive used in electromechanical drive systems to control AC motor speed, torque by varying motor input frequency and voltage. And like I said, you want to vary that input frequency and voltage in a linear fashion. VFDs are used in applications ranging from small appliances to large mine mill drives and compressors. However, about a third of the world's electrical energy is consumed by electrical motors, and fixed speed centrifugal pumps, fans, and compressor applications in VFDs. Global market penetration for all applications is still relatively small. So there's not a lot of VFDs out there, and a lot of people just use standard old-fashioned centrifugal pumps direct across the line. The highlights essentially or especially significant energy efficient improvement opportunities for retrofitting the new VFD installations. So if you get an opportunity to change out a centrifugal pump or a fan, you could actually see some energy efficiency improvements. A lot of these energy efficient improvements that they offer, or they say, oh, you're going to get X number of dollars back, aren't always true. So you got to be real careful about that, because there's other things that factor in here. Over the last 4 decades, power electronics technology has reduced VFD cost and size and improved the performance through advances in semiconductor switching devices, namely the IGBT drive topologies, simulation and control techniques, and control hardware and software. So because of the last 4 decades, VFDs have slowly gotten better and better and better, and a lot of people are starting to use them. VFDs are available in a number of different low and medium voltage AC to AC and DC to AC topologies. So again, you have your sine wave. You got your variable frequency controller. You've got some operator interface that you can actually control it with. You get a variable frequency power output, and you drive your AC motor, which in turn drives the mechanical power. The AC motor, the AC electric motor used in the VFD system, is usually a three-phase induction motor. Some types of single-phase motors can be used, but three-phase motors are usually preferred. Various types of synchronous motors offer advantages in some situations, but three-phase induction motors are suitable for most purposes and are generally the most economical choice. And again, a synchronous motor with a VFD application would be for a high speed application where you would be rotating 6,000 RPMs on a two-speed machine. And the reason you can do that, again, is that you can control the excitation current and increase it to ensure that the motor stays in sync with the VFD's output current. AC motors that are designed for fixed speed operation are often used. Elevated voltage stresses imposed on induction motors that are supplied by VFDs. These elevated voltages obviously come from that DC link and the way they turn it on and off, right? Another thing is the length of the line between the inverter or the VFD and the motor. If you have a long lead, like 300, 400 feet or something, or 1,000 feet, what you'll get is a traveling wave effect. What happens is that positive DC bus or that voltage goes high, and then it travels down there, and when it gets to the motor, it reflects back, and as it reflects back, it doubles. It has a doubling effect, and this will go on and on and on, and they call it a ringing type effect, and then it'll destroy something. So what you want to do is you want to keep your VFD and your motor as close as possibly you can. So obviously MG1 has stepped up and said, hey, look, these motors have to be designed for definite purpose inverter fed duty. So now that's changed. Earlier, I don't know, 20 years ago or so, they didn't have these inverter fed duty motors. So and a lot of people didn't realize that they had to order it that way, and they would destroy these induction motors and kind of gave VFDs a bad name. Typical 6-pulse adjustable speed drive configuration. We've talked about this, but this is kind of unique because here you have a SCR on the front end, right? So your rectifier is controlled with an SCR. You've got a DC link, and then you have a SCR output on the inverter side of it. So this would be more of a current inverter drive, not a voltage inverter drive, or variable voltage would be a current inverter drive, so a current source, right? A variable voltage drive would be what we're used to seeing. We see SCRs, capacitors, and then SCRs driving the motors. And you can see the output voltage is just a square wave, and the output current is looking pretty rough as well. Going back to that current source inverter drive that we saw, where you have the SCR, the inductor with no capacitor, and then the SCR again, you still have a rough looking output voltage. They actually reversed, right? If you look back on the other one, it was different than that. So here you have your output voltage is a little ripple there, and your output current squared off. Your pulse width modulated drive, we've seen this, the diode, the capacitor, and the IGBT, and you've got that pulse width modulated waveform. The output voltage looks rough, but the output current's fairly smooth, and again, it's smooth because the motor's inductive, there's basically windings out there that are inductive, so it smooths out the current. Controlling the VFD, the variable frequency drive controller, is a solid state power electronic conversion system consisting of 3 distinct subsystems. The rectifier bridge, or a converter, sometimes they call that the converter. You've got the direct current DC link, or you could also have the capacitor across there. And then you've got your inverter, which is the DC to AC portion of it, and then you drive your actual motor. Voltage source inverters, or VSI drives, are by far the most common types of drives. That is a true statement. Most drives are AC to AC drives in that they convert AC line input to AC inverter output. However, in some applications, such as common DC bus or solar applications, drives are configured as a DC to AC drive. The most basic rectifier converter for the VSI, the voltage source inverter drive, is configured as a 3-phase, 6-pulse, full-wave bridge, diode bridge. In a VSI drive, the DC link consists of a capacitor which smooths out the converter's DC output ripple and provides a stiff input to the inverter. This filtered DC voltage is converted to a quasi-sinusoidal AC voltage output using the inverter's active switching elements, which we've seen. 6-pulse rectifier front end. Diodes or thyristors are usually grouped in 3-phase bridge rectifiers. Each 3-phase bridge is a 6-pulse converter. So when you say 6-pulse, you can count the devices and you'll see 6 of them. That's a 6-pulse bridge. If you had 12 of them, that'd be a 12-pulse bridge. If you had 18 of them, that would be an 18-pulse bridge, and so far, and then you go up to 24-pulse. A 6-pulse converter has a distinct harmonic current signature, which is very poor. A 6-pulse converter has at least 30% harmonic current distortion, which is extremely high. But as long as the drive is relatively small in relationship to the utility supplying it, it doesn't really matter, and we'll find that later. Here you have your schematic again of a general diagram for energy storage device to increase the ride-through capability of an ASD. So if utility for some reason dips and you want to have some type of a ride-through capability, this is the design you'd use. You have your rectifier, you've got your AC input source, you've got your DC link. You see how your DC link breaks off and it heads into this energy storage module, right? And a recharging type device. And then you've got your capacitor, you've got your PMG IGBTs, a pulse width modulating inverters, the IGBTs, and then you've got your induction motor. So the idea is if the input voltage starts to drop or reduce or blips out or brown out or whatever, the capacitor is going to hold it just for a second. But if you go to this energy storage module, what happens is you've got like a little buck system here. So what it'll do is that IGBT will fire, right? And when it fires, it will short out that inductor, right? And remember, on the inductor has a large magnetic field if it has a lot of current flowing through it. And then the minute you open that IGBT, that magnetic field collapses. And when it collapses, the voltage reverses. So before it goes positive, negative, and then it goes negative, positive, and then it forward biases that diode, which charges up that capacitor and maintains that DC voltage. So as the DC voltage is falling, you can, this is like a chopper, or it's a type of chopper circuit where they bump up the voltage and maintain that DC link for some period until you have lost your energy storage module's power. So it's a capability where you can do some ride through. Inherently, a VFD does have some ride-through capability because of that large capacitor on the DC link. A 6-pulse waveform seen by utility. Here the current is voltage, or current is blue, and the voltage is in red. And what they've done is they've flipped them. Ordinarily they would look closer like they were on top of each other, but for illustrative purposes, they've flipped one of them. So the current is inverted in this case. But you can see that blue current is pretty rough, right? And the voltage is pretty rough. So it's actually got some different harmonics in it. And I'll explain how that waveform is made and how the harmonics can be broken out to decipher how that waveform is made. So here, if you had a harmonic spectrum analyzer, you could measure the harmonics and look at the 6-pulse diode converter, and you would find out the fundamental frequency, obviously, is the 60 hertz. Here you have a 5th harmonic, looks like a 5th harmonic there, and you've got a 7th harmonic, and then you've got a 11th harmonic, 13th harmonic, 17th harmonic, and so on forth. Usually they take these all the way up to the 55th harmonic. So if this is a 60 hertz machine, then the fundamental one is 60 hertz. The 5th harmonic would be 5 times 60, which would be 300 hertz. And remember, I was telling you that when you have these 6-pulse diode bridges, you have these high harmonic frequencies. And so if you put a reactor or a choke in the AC line, the choke would actually, or the inductor would actually see that as 2 pi F. As F increases, the capacitive, the inductive reactance increases, and so blocks these high frequencies, these high harmonic frequencies from getting back to the utility. So you can reduce that total harmonic distortion at the top from 32% to some lower number. We'll discuss that well later. VSI drives provide high power factor and low harmonic distortion than phase controlled current rectifiers. Obviously, if it's current controlled, it is going to maintain that current at all costs. It doesn't care about the voltage, and you have higher harmonics in that case, and as well as the load commutated inverter LCI drives. So the best one is the standard VSI voltage source inverter, which is your standard VFD. The drive controller can also be configured as a phase converter, having single-phase converter input and three-phase inverter output. I think we mentioned this before. You can take a three-phase drive and you can feed it single-phase input power, and then it'll give you three-phase output power and drive a three-phase motor. You do have to derate it and have to get with the manufacturer to find out how much you have to derate it depending on your input, your incoming power is single-phase power. Controller advances have exploited dramatic increases in the voltage and current ratings and switching frequency of solid-state power devices over the past 6 decades. Introduced in 1983, the insulated gate bipolar transistor has in the past 2 decades come to dominate VFDs as an inverter switching device. And it truly has. So in variable torque applications suitable for volts per hertz, they have these volts per hertz drive control, and we talked about that, where you have that linear relationship as the frequency increases, the voltage increases in a linear relationship. AC motor characteristics require that the voltage magnitude of the inverter's output to the motor be adjusted to match the required load torque in a linear volts per hertz relationship. Here we have an example. We have for 460 volts, 60 hertz motor, this linear volts per hertz relationship is 460 divided by 60, which equals 7.67 volts per hertz. While suitable in a wide-ranging application, volt per hertz control is suboptimal in high-performance applications involving low speed or demanding dynamic speed regulation, positioning and reversing load requirements. Some volts per hertz control drives can also operate in quadratic volts per hertz modes, or even be programmed to suit special multi-point volt per hertz paths. Two other drive control platforms, the vector control and the direct control, torque control, DTC, adjust the motor voltage magnitude, angle from reference, and frequency, such as to precisely control the motor's magnetic flux and mechanical torque. That vector control is exactly why, when they perfected vector control, they allowed the variable frequency drives to dominate the paper and steel industry, because they were able to control that motor so precise that they could match the control of a DC motor. So that's actually a key to when that was invented. Although space vector pulse width modulation, SVPWM, is becoming increasingly popular, the standard sinusoidal pulse width modulation is the most straightforward method used to vary drives, motor voltage or current and frequency. With SPWM control, quasi-sinusoidal variable pulse width outputs is constructed from intersections of a sawtooth carrier frequency signal with a modulated sinusoidal signal, which is variable in operating frequency as well as in voltage. The carrier frequency signal is an internal carrier frequency, and you can fire these different IGBTs at different frequencies. If you increase the carrier frequency, the drive becomes, and the motor also becomes very quiet. And they use that in a HVAC application. If you decrease the frequency to like 1 kilohertz, the carrier frequency to 1 kilohertz, then the noise and drive is a little bit more loud. However, it's more robust. Operation of the motors above rated nameplate speed. The base speed is possible, but it is limited to conditions that do not require more power than the nameplate rating of the motor. So if you kept increasing the speed of a 60 hertz motor, eventually it'll stall, and this is sometimes called field weakening, and for AC motors means operating at less than their volts per hertz and above rated nameplate speed. When I was an instructor, we used to play little games with these, and we'd see how high we could take a motor in an unloaded state. We'd sit there and just increase it until it would basically just stall, right? It couldn't keep up with that frequency. And that's the beauty of an AC synchronous machine, because an AC synchronous machine, it actually controls its field, right? And so you can increase the excitation current as you increase the speed. And that's why AC synchronous motors that are specially designed to withstand all high speeds fill that application. You can have a permanent magnet synchronous motors that have quite limited field weakening speed range due to the constant magnetic flux linkage. You can also use a wound rotor synchronous motors, and induction motors have much wider speed range. And again, the wound rotor induction motor or the wound rotor synchronous motors you can increase their excitation, and therefore you can, as the speed goes above the 100% rating, you can just keep increasing the excitation on current. Here we have a 100 horsepower 460 volt motor at 60 hertz at 1775 RPMs, 4-pole induction machine, supplied with 460 volt at 75 hertz. So you have 6.134 volts per hertz. That's 460 divided by that 75 hertz. Would be limited to 60 divided by 75, which is your rated frequency is 60, and you're running it at 75 hertz. So you'd have an 80% torque at 125% speed. So you would not be able to get full 100% torque out of that motor at 75% hertz, or 125% speed. So you're rotating at 2218.75 RPMs would be 100% power. So that's kind of what happens. As you increase the speed, you actually reduce your ability to deliver torque. And obviously, if you kept increasing it, you would eventually stall. At higher speeds, the induction motor torque has to be limited further due to the lowering of the breakaway torque of the motor. And you remember what the breakaway torque was. We illustrated that. Thus, rated power can be typically produced only up to 130 to 150% of the nameplate rated speed. Wound rotor synchronous motors can be run at even higher speeds. In rolling mill drives, often 200 to 300% of the base speed is used. That's 2 times the fundamental speed. So if it's a 3,200 RPM machine, that's 6,400 RPMs that machine can rotate. Could even be as high as 3 times, so it's a significantly higher speed. But the mechanical strength of the rotor limits the maximum speed of the motor. So the manufacturer has to know that you're fixing to drive that wound rotor synchronous motor that high, otherwise that motor could just fall apart and destroy your machine. An embedded microprocessor governs the overall operation of the VFD controller. Basic programming of the microprocessor is provided as the user inaccessible firmware. So they can basically go up to this and change about every different parameter. Something I always tell people: if you walk up to a motor and some electricians have been messing with it, or somebody's been messing with it, and it doesn't work anymore, and it just doesn't run, and it just doesn't seem like it programmed. Maybe an engineer programmed it, and it just didn't perform like he thought it would. Just go up to that machine and just set it to its default values. Make sure you record everything that he wanted, but go ahead and just set it to default values and try it. Usually, I'd say 95% of the time, if you set everything back to default values, that VFD will run like a champ. So these are user programmable displays, variable and functional block diagrams. It's provided to control, protect, and monitor the VFD, motor-driven and the motor-driven equipment. So again, people get in there and start tinkering with it, and then it doesn't work like they thought it should. And so if you just set it back to default settings, you're off and running. The basic drive controller can be configured to selectively include such optional power components and accessories as follows. You can order it with a circuit breaker or design it with a circuit breaker. You can design it with fuses, isolation contactors, EMC filters, which is electromagnetic compatibility filters, line reactors, and passive filters. You pretty much want to get with the VFD manufacturer before you start doing this, because you want to make sure that they agree with what you're adding to it. You can connect the DC link. You can install a braking chopper. Remember that chopper circuit we saw? Or a braking resistor. So the chopping circuit or the buck boost circuit we saw could actually increase the DC voltage, whereas a chopping circuit would actually start braking it, and it would go into a braking resistor. You can connect downstream of the inverter output reactors on the AC wave or the AC lines, a sine wave filter, and a DVDT filter, which is a change in voltage with respect to time filter. Not a big fan of filters, not a big fan of any type of capacitor, inductor type filter. I prefer to increase the impedance of transformers and things like that or do phase multiplication to reduce my harmonics. Operator interface. The operator interface provides a means for an operator to start and stop the motor and to adjust operating speeds. Additional operator control functions might include reversing and switching between manual speed adjustment and automatic control from an external process control signal. If you wanted to, you could actually manually control it at the VFD, or you could allow it to switch over to automatic control and something other like a PLC might control it. The operator interface also often includes an alphanumeric display and or indicating lights and meters to provide information about the operation of the drive. An operator interface keypad and display unit is often provided on the front of the VFD controller. I didn't show a picture of it here, but you can actually order it where these VFDs are removable, and you can put them on the front of a panel, or you can put it on front of the VFD, or you can just not have one at all. A keypad display can often be cable connected and mounted on a short distance from the VFD, so you can put it on the door and put the drive in the back of it. Most are often provided with input and output I/O terminals for connecting push button switches and other operator interface devices or control signals. A serial communication port is also often available to allow the VFD to be configured or adjusted, monitored, and controlled using a computer. So here is that old analog drive, the power section of it, and again, this was downloaded off Toshiba's website. It's an old H1 drive, I think. Anyway, again, you have your input power. It comes in L1, L2, L3, or RST. You got your MOVs, and you can see those MOVs are connected into a delta configuration. So the line-to-line voltage, the MOV rating has to be rated for that line-to-line voltage and some, right, or it'll explode. Goes to that ZCT. What is ZCT? That's a zero sequence current transformer. And so basically what it's looking for is if everything is perfectly balanced, there's no imbalance in the current, then the output of that ZCT should be 0. And then you can see they also tap off for the AC voltage. So if for some reason there's a imbalance in that rectifier or in that drive, this drive will shut down and say you have a zero sequence CT issue. Then you've got your full bridge rectifier there, and you can see you've got R21 and R21A, and MS1 is actually controlled by the gate driver and control board. So the first thing that happens is when this thing is initially powered up, you don't want to run that rectifier directly into a capacitor. You want to limit the current through R1 and R2 or R1A, and then once you've let it sit there for, I don't know, 5 seconds or so, you can MS1 will close, which will fully charge C1. So it's just a way of limiting the inrush current of that capacitor. C2 is on the other side of the fuse. So P is the positive DC bus, N is the negative bus, and then you've got 3 isolated IGBT modules, IGBT 1, 2, and 3, and they're just standard IGBT modules with your inductive kickback diode there, or your regenerative diode. And then you've got your gate signals. See, they're twisted pair, and basically what you want to do is anytime you hook up an SCR's gate or an IGBT's gate, you want to twist it so many times, and usually it's like 6 times per inch or something like that. I've seen it slightly less, but usually 6 times per inch. You're guaranteed not to pick up noise and get any crosstalk. So you want to do that so you don't avoid some misfiring. On the output of this drive, they have a Hall effect current CT, and they're looking at phase A and phase B. They're not looking at all phases, and they can monitor the output current and shut that drive down in overcurrent condition. And that's really the power layout. I could go into more of it. I think we've pretty much touched everything there, and the how it operates and stuff like that. So we'll just move into operation. There's 4 different areas that a drive can operate. A drive application can be categorized as single quadrant, 2 quadrant, or 4 quadrant. The chart's 4 quadrants are defined as below. Quadrant 1 is the top right-hand side. That's a driving or motoring. You have forward accelerating quadrant with positive speed and torque. So that would be 95% of the time you fall into that category. You could slip over into that quadrant 2, and quadrant 2 would be that generating or braking, forward braking, deceleration quadrant, and positive speed and negative torque. So here what happens is your mechanical load is still driving the motor so that it becomes a generator. And if it becomes a generator, then you have you're in quadrant 2, and you're start to charge up that DC bus, and you need to start braking it somehow, or dealing with it somehow. Quadrant 3 is below it, and that is when you're driving or motoring, but you're in reverse. You're a reverse acceleration quadrant with negative speed and torque. So before you were driving forward, and then now you're driving reverse. And then quadrant 4 is a reverse braking application where you're generating or braking, reverse braking, decelerating quadrant. So if you rapidly try to decelerate that load, and if it's too large, you'll actually go into a situation where you need to add a brake, or you need to regenerate that power back to utility somehow. Most applications involve single quadrant loads operating in quad 1, such as variable torque, centrifugal pumps or fans, and certain constant torque extruder loads. Probably, like I said, 98% of all operations are right in that driving operation. Certain applications involve 2 quadrant loads operating in quadrant 1 or 2, where the speed is positive but the torque changes polarity, as in the case of a fast decelerating load, faster than natural mechanical losses. So you try to decelerate this thing, such as a fan. So if it's got a large inertia and you try to decelerate it too quick, you can't decelerate it so quick. Therefore, it's going to drive that DC bus open or higher, and you need to start using an IGBT to break it into a resistor. You can fix this problem by just increasing your deceleration time, so you allow the load to come down at its natural frequency or natural speed. Some sources define 2 quadrant drives as loads operating in quadrant 1 and 3, where the speed and torque is same, positive or negative, polarity in both directions. Certain high performance applications involve 4 quadrant loads, quadrants 1 to 4, where the speed and torque can be in any direction, such as in hoist, elevators, and hilly conveyors. Regeneration can only occur in the drive's DC link bus when the inverter voltage is smaller in magnitude than the motor back EMF, and inverter voltage and back EMF are the same polarity. So if that condition occurs, then you can regenerate that back in utility. In starting a motor, a VFD initially applies a low frequency and voltage, thus avoiding high inrush currents associated with direct online starting. One of the best things about a VFD is you don't have that high inrush starting. After the start of the VFD, the applied frequency and voltage are increased at a controlled rate or ramped up to accelerate the load, and we've talked about that. This starting method typically allows a motor to develop 150% of its rated torque, while the VFD is drawing less than 50% of its rated current from the same mains in a low speed range. The VFD can be adjusted to produce a steady 150% starting torque from standstill right up to full speed. So you can actually try to hold that shaft, and you'll never be able to hold it the minute you turn it all the way to its 150% of its speed. That's kind of key, because if you put this on standard control or not a constant torque, you can actually hold that shaft for a while. However, motor cooling deteriorates and can result in overheating as speed decreases, such that prolonged low-speed motor operation with significant torque is not usually possible without separately motorized fan ventilation. So we talked about that when this motor is running at 50% speed for extended periods of time, and it is running at full torque or 150% torque, the fan is not spinning fast enough on that totally enclosed fan-cooled motor. Therefore, it will overheat, so you probably would have to have a separately motorized fan ventilation system. With the VFD, the stopping sequence is just like the opposite of the starting sequence. The frequency and voltage applied to the motor are ramped down at a controlled rate. When the frequency reaches 0, the motor is shut off. A small amount of braking torque is available to help decelerate the load a little faster than it would stop if the motor were simply switching off and allowed to coast. Additional braking torque can be obtained by adding a braking circuit where you'd add a resistor controlled by a transistor or an IGBT to dissipate the braking energy. With a 4-quadrant rectifier active front end, an active front end is an IGBT on the rectifier instead of a solid diodes. If you have an active front end, you can actually control the power factor on that front end as well, or what the utility sees. The VFD is able to break the load by applying a reverse torque and injecting the energy back to the AC line. So here you have a regenerative type load where you have IGBTs on the front end, the rectifier portion of it, and IGBTs on the AC portion of it. And depending on the load and where you're at in the load, you can actually reverse the power and take the massive load on a hoist system or a drilling rig and then just inject it back into utility. Many fixed energy savings. So many fixed speed motors load applications that are supplied direct from AC line power can save energy when they are operated on a variable speed by means of a VFD. Such energy cost savings are essentially pronounced in variable torque centrifugal fan and pump applications, where the load's torque and power vary with the square and cube respectively of the speed. So here we have this change gives a large power reduction compared to fixed speed operation for a relatively small reduction in speed. For example, at 63% speed, a motor load consumes only 25% of its full speed power. And this is in accordance with the affinity laws that define the relationship between various centrifugal load variables. Here's a simplified fixed speed pump motor system with control valves. So here you have a across the line starter on the left hand side. You got your 3-phase power, starts the motor, and the pump is running at one fixed speed. To adjust the flow of that, you would actually have these flow control valves, and then you'd also have a minimum flow bypass valve so that you didn't run into a situation where if you restrict the output too much, your pump could cavitate, right? So, well, actually, if you open it up wide open, it could cavitate. So you'd want to always have some minimum flow bypass valve so you don't get into a cavitation situation. This is not a pump class, and I'm not qualified to teach a pump class, so I'm going to stop right there. Typical ASD, adjustable speed drive controller pump system. You have your 3-phase AC power. It is got a flow sensor that looks at it as part of the feedback system. You vary your voltage and frequency to the motor, and you can speed and slow down that pump. So that would be a typical application. And here's your affinity laws for centrifugal equipment. These describe the behavior of centrifugal loads. You can notice the flow varies directly with speed and head pressure as the square of the speed, while the power varies as the cube of the speed. Reducing the speed to 60% reduces the flow to 60% and the power input to 21.6% of nominal or normal, which can provide substantial energy savings. So the idea is if you reduce that flow to 60% and you'll reduce your power input to 21%. So that's your big savings. That's the heart of the affinity laws, but it doesn't always work there. In practice, this degree of power reduction does not occur because the system's static head and losses require the motor to operate at a speed greater than 60% to provide 60% flow. So reality of it is you might have to operate your speed closer to 75% to get your 60% flow. But in the United States, an estimated 60 to 65% of electrical energy is used to supply motors, 75% of which are variable torque, fan, pump, and compressor loads. So 18% of the energy used in the 40 million motors in the U.S. could be saved by energy efficient improvement technologies such as VFDs. And you've got to know that that was a salesman that wrote that one, because obviously that's the big push for VFDs. But just be aware that you might not get as much return on your investment as you thought you were going to get, due to the fact that you might have to run it a little faster. It's not a linear relationship there, but only about 3% of the total installed base of AC motors are provided with AC drives. However, it is estimated that drive technology is adopted in as many as 30 to 40% of all newly installed motors. So as the new projects are coming in play, a lot of them are getting the VFDs to start getting their return on investment. So eventually the old method will phase out. An energy consumption breakdown of the global population of AC motor installation is shown in this table. So here you have small motors, 10 watts to 750 watts, or typically single phase, less than 240 volts. Percent total motor energy is about 9%. There's roughly 2 billion of them in stock out there in the field. General purpose medium size, 750 watts to 375 kilowatts. These are 3-phase, 200 volts to 1,000 volts. Roughly 68% of the motors, total motor energy is 68%. And there's over 230 million out there in the field. So if you just went after the general purpose medium sized motors, 750 watts to 375 kilowatts, you could save a ton of money for the industry. Obviously, there'd have to be some analysis that goes into it, but you certainly don't want to just not use it. On the large, you have 375 kilowatts to 100 megawatts. This is 3-phase, 1 kV to 20 kV, 23% of total motor energy. Roughly 600,000 or 0.6 million are out there in the industry. There is a software package you can go. It's a free online thing that you can go on Toshiba and download. It's an energy savings estimator. So here we have the motor efficiency is 95%. It's a 20 horsepower motor. The drive costs $3,000. That popped in automatically. And then you can say, I want hours of operation. There are 24 hours a day, and there's no utility incentive. So it's just a one-time savings. So you plug all this in, and it came up with a system energy usage. So energy saved is 107,000 kilowatt hours at total equipment cost of $3,000. So you're saving an estimated carbon footprint of 48.48 tons. Your ASD system is saving 10.69 tons. So your total CO2 savings is, or the ASD system is actually adding to it, I guess. And so your CO2 savings is 37.79 tons. And you would save an energy cost $10,725 a year. That's a big number. So your estimated payback time would be 0.28 years. That's really fast. That's impressive. It assumes that you're paying a fair amount for your electricity. Certainly you might not be paying that much if you're in the industry or like a refinery or something like that. So here's another breakdown. Your operating hours are 8,760 hours. And it gives you your total operating cost, your current system, energy saved, your payback. It's just another deal. So you got year one, equipment cost is $3,000. Your energy saved is $10,725. So you've got a savings of $7,725. Year two is a total savings of $10,725. So each year you just keep saving. The first year, in 0.28 years, you paid off this whole deal. So after 5 years, you have a $53,000 or a $50,000 savings. So you can give that to your boss, and if it's for a HVAC fan type application, he might go for it. Control performance. AC drives are used to bring about process and quality improvements in industry and commercial applications. So you can control acceleration, you can control flow, you can do monitoring, you can do pressure control, speed control, temperature control, tension, and torque control. So very impressive. Fixed speed mode subject the motor to high starting torques and to current surges that are up to 8 times the full load current. So AC drives instead gradually ramp the motor up to operating speed to lessen the mechanical and electrical stresses, reducing maintenance and repair costs, and extending the life of the motor and the driven equipment. So if you just use straight across the line starting, you can see surge currents up to 8 times of the full load current, which you can actually break the shafts or cause all kinds of trouble. Certainly this would extend the life of your motor if you used an AC drive and slowly ramped it up. Variable speed drives can also run a motor in specialized patterns to further minimize mechanical and electrical stresses. We talked a little bit about the S-curve pattern can be applied to a conveyor application for smoother deceleration and acceleration control, which reduces the backlash that can occur when a conveyor is accelerated or decelerated. When you set up these drives, you can actually go to the acceleration and deceleration patterns, and that's how you would accept an S-curve pattern. Performance factors tending to favor use of DC over AC drives include such requirements as continuous operating at lower speeds, 4-quadrant operation with regeneration, frequent acceleration and deceleration routines, and the need for the motor to be protected for hazardous areas. So if you had a motor that needed to be in a hazardous area, you'd probably want to use an AC drive for that as well. So, table compares the AC and DC drives. So you get your DC. Look at the speed regulation. Typical speed regulation is 0.01%. A standard VFD, AC VFD with volts per hertz control is 1% speed regulation. An AC VFD with vector control, and that is open loop, is 0.5%. If you close the loop and you put a tachometer on there or an encoder, then you could achieve that 0.01%. And when they did vector control with closed loop, they started competing with those DC motors and with that speed regulation. So that was a big issue there. And so this kind of gives you an overall comparison between them. Obviously on the DC motors you've got the brushes, so you've got high maintenance. You have low maintenance on all the AC VFDs. Minimum speed at 100% torque. The DC at standstill, right? 8% on the VFD with an AC VFD with volts per hertz control. And you can kind of go through this on your own. Voltage source inverter VSI drive topologies. We've talked about this. In a VSI drive, the DC output of the diode bridge converter stores energy in the capacitor bus to supply stiff voltage input to the inverter. The vast majority of the drives are VSI type with pulse width modulation voltage output. VFD types and ratings, current source inverter, CSI, drive topologies. In a current source inverter, the DC output of the SCR bridge converter stores energy in the series reactor connecting to a supply stiff current input to the inverter. Current source inverter drives can be operated with either pulse width modulation or the 6-step waveform output. So we're going through different topologies here. We've never talked about the 6-step inverter drive topologies. Now largely they are obsolete. 6-step drives can be either VSI or CSI, current source inverters types, and are also referred to as variable voltage drives, pulse amplifier modulation drives, or square wave drives, or DC chopper inverter drives. In a 6-step drive, the DC output of the SCR bridge converter is smoothed via the capacitor bus and series reactor connections to supply via a Darlington pair or IGBT inverter, quasi-sinusoidal 6-step voltage or current input to the induction motor. And here, this gives you a 6-step, what it looks like. So you have VFD types and ratings, 6-step drive waveforms per VSI phase leg. In I, you see across the inverter bridge. 2 is line to line, and 3 is your line to neutral. So you can see a 6-pulse step. There's also cyclo converters or matrix converter MC topologies. the MC is matrix converter. Cycloconverters and MCs are AC to AC converters that have no intermediate DC link for energy storage. A cycloconverter operates as a three-phase current source via three anti-parallel connected SCR bridges in 6-pulse configurations. Each cycloconverter phase acting selectively to convert fixed line frequency AC voltages to an alternating voltage at a variable load frequency. MC drives are IGBT based. Here's a cycloconverter right here. So you can see this is actually, it would look like an 18 pulse drive, right? Because you got 6, 6, and 6, it's 18 pulse drive. And it's for a high voltage application. A double fed slip recovery topology. You don't really see these too often. Usually in wind turbines they have them. A doubly fed slip recovery system feeds rectifier slip power to a smoothing reactor to supply power to the AC supply network, being an inverter. The speed of the motor being controlled by adjusting the DC current. So here you'd have a doubly fed recovery system. You have your wind turbines, your gearbox, your generator there, and your converter, right? So the converter would actually support that generator under different conditions and backfeed that power to the grid. Most drives use one or more of the following control platforms. We've seen this: pulse width modulation, volts per hertz scalar control, pulse width field oriented control, or FOC, or vector control, and then direct torque control, DTC. In a typical volts per hertz control block diagram, you'd see this, and we saw this. You have your speed reference input, you've got some type of a ramp block, you've got a volts per hertz reference sharing, then you drive the transistor switching logic and or the pulse width modulating logic. You look at the current feedback, and then you control that IGBT. Variable frequency drives are also categorized by the following load, torque, and power characteristics. Variable torque, such as centrifugal fans, pumps, and blower applications; constant torque are conveyors, displacement pump applications; and then constant power, such as machine tools and traction. And we've seen all of this before. So available power ratings. VFDs are available with voltage and current ratings covering from a wide range of single-phase to multi-phase AC motors. Low voltage drives are designed to operate at output voltage equal or less than 690 volts. Where do we see 690 volts? Canada primarily. While motor applications, low voltage drives are available and ratings of up to order of 5 to 6 megawatts. Economic considerations typically favor medium voltage drives with much lower power ratings. Different medium voltage drive topologies are configured in accordance with the voltage and current combination ratings used in different drive controllers, switching devices, such that any given voltage rating is greater than or equal to one of the following standard nominal motor voltage ratings. Generally 2.3 kV to 4.16 kV is 60 Hertz, or 3.3 to 6.6 kV is 50 Hertz, with one thyristor manufacturer rated up to 12 kV switching. So if you go above the 12 kV switching, they use an SCR in that application. In some applications, a step-up transformer is placed between the low voltage drive and the medium voltage motor. Medium voltage drives are typically rated for motor applications greater than between 375 kilowatt or 500 horsepower to 1,000 horsepower. Medium voltage drives have historically required considerable more application design efforts than required for low voltage drive applications. The power rating of medium voltage drives can reach 100 megawatt. A range of different drive topologies being involved for different ratings, performance, power quality, and reliability requirements. Drive voltage 460 to 575 up to 650 horsepower. 460 to 575 with input and output transformers, 600 horsepower to 2,500 horsepower. 2.4 kV incoming voltage, 650 to 5,000 horsepower. 4160 volts, that's medium voltage. Anything above 1,000 is medium voltage, up to 35,000. So these are all medium voltage. 4160 is 650 to 20,000 horsepower. 6.9 kV is 10,000 to 30,000 horsepower. That's a big machine. 13.8 kV is 25,000 to 50,000 plus horsepower. So these drives and horsepowers can get very, very large quick. So here's a basic drives or by machine. So if you have an induction, you can have a cage rotor or a wound rotor motor or a doubly fed wound rotor motor. The cage rotor is your current source or voltage source, 6-step or pulse width modulation, a cyclic converter or matrix. The wound rotor motor is electromechanical, and the doubly fed motor is a slip energy recovery for the wind turbines. Synchronous motors. In synchronous motors, you can run them current source. You can also use pulse width modulation, which would be axial disc or radial interior. And obviously, you can go very high speed with synchronous motors. They also have a VRM, which is which is used for switch reluctance motors or stepper motors. Vector control scheme block diagram, and obviously we saw this on the DC when the comparison between the DC and the AC drives, and when they came up with the vector control with the encoder, they were able to monitor speeds at 0.01%, which is really key here. This input speed reference, see that little circle with a little X in it? That's what they call a summing junction. So you have your speed reference coming in, and then it's compared to your encoder speed, the actual pulse tack value. The output of that goes to your speed regulator, which goes to another summing junction. That summing junction looks at motor model, the current into it, and the motor model and calculated torque output. So you get your speed regulator, and your torque output goes to your torque regulator, which affects your transistor switching logic. Your volts per hertz reference shaping goes to a summing junction, and looks there's an output from the motor model that gives you your calculated flux output. Those two are summed together, which gives you a volts per hertz flux regulator, which also goes into the transistor switching logic and PMW logic. You have your current feedback, and you also have an output to your motor model to give you instant feedback, which drives those IGBTs or transistors. And you can see that you need all three phases for your current feedback there, which drives the induction motor. Attached to the back of the induction motor is that pulse tack, which gives your encoder to speed converter, and then goes into a summing junction, which gives you your speed feedback to your motor model, as well as your speed reference to your reference speed summing junction, so it completes the loop. Power modules for VFDs. There's different types of power modules. I'm just going to kind of look at some of the odd ones, if you will. Some of the thyristor bridges, because you don't really see these too often. A bridge or a VFD with an IGBT module is not really that fancy. I mean, it is. It's cutting edge and everything, but it's something you won't really look at too much because it's hiding in there. But a thyristor is a switching device. Heat sinks are used to dissipate that heat generated in the device. You need the snubber resistor capacitors to protect the device against over voltages. Sharing resistors for equalizing the voltage across series connected thyristors. And then pulse transformer to supply gate pulses to thyristors and to provide isolation between control and power circuits. When you exceed certain voltages, you have to start stacking SCR modules, and when you put all these SCRs in series, you're able to run these at high voltages in the range of 1.2 kilovolt modules. The same theory works for IGBTs. Toshiba is able to stack these in series and obtain a higher voltage rating. So the construction of a 1.2 kV module, you have two thyristors are used in series. You have that snubber again for protecting the thyristor against overvoltage. Reactor limits the rate of rise of on-state current, and then this particular module is an HPTF module, gives firing pulses to thyristors and also indicates the healthiness of thyristor. So here you have a power modules for your VFD. We've talked about this. You've got your energy source, your rectifier, you've got your intermediate DC bus, your inverter, you've got some control and monitoring capability, driving the motor, which is connected to the mechanical load. We've talked about this power module for variable frequency drive. It's a LCI fed synchronous motor. So here you have a SCR on the front end and an SCR on the back end. So your rectifiers are SCRs. You've got a choke, so it's a current source rectifier, and the inverter is also SCR. So Q1, Q3, Q5, Q4, Q6, Q2. And so you can stack these SCRs and control high voltages and high power machines. That's what an SCR looks like. You can either have the studs on the left, or you can have the hockey pucks on the right. The trick about these hockey pucks is they have to be clamped under a certain pressure. If they're not clamped, then they won't function correctly. They won't conduct. And they also have to have that paste. All of these have to have that special heat conductive paste. If you don't put it on there, you'll burn that SCR up. Here's what we call a hockey puck, right? It looks like a little hockey puck, but you can see that it's a SCR, and the gates are off to the left-hand side of that tab, and it has a gate, a cathode, and an anode. We talked about modules, the actual construction of a SCR. Here they elaborate on the 3-terminal SCR. You've got your P1 junction, your N1 junction, your P2 junction, and your N2 junction. The top of that's a little bit off. That P2 should be over the blue and the N2 should be over the purple. And then you've got your gate signal coming in. And we talked about the SCR volt characteristics. This one actually shows that peak inverse voltage. We didn't see that before. So when you start going reverse biased, it can avalanche on you. And so if you hit that peak inverse voltage, you can actually destroy the SCR. So you want to stay below that and make sure that you oversize that device so that it can handle that. And then you slide over to the right. You have no current flow until gate voltage is applied. So you have that funny looking curve there until it's forward biased, and then the current flows after gate voltage is applied. So you can see that waveform right there, the volt amp characteristics. So here we'll talk about this forward blocking or off state. J1, J3 are forward, and J2 is reverse biased. So you have forward biased and reverse biased. 2 and 3 forward conduction on state. J1, J2, and J3 are all forward biased. Reverse biased, you have J1 and J3 junctions are reverse biased, and J2 is forward biased. And then if you fall into a 4 and 5, you have breakdown, right? So you want to be careful to stay out of your breakdown. Here's an SCR forward bias, this half waveform. So it gives you characteristics of the SCR during a half wave rectification. So here you have your conduction angle, and then you've got your firing angle right there. So you look at the zero crossing of that waveform and you fire on the firing angle, and then it conducts the rest of the way. So your SCR blocks until rated voltage is applied at the point of gate, and the SCR blocks the negative half cycle and must have a PIV rating above this peak. So you have to look at the peak value of that AC waveform, and you need to make sure, the way I do it, is 4 times that peak inverse rating. And then you're not into trouble, and then 2 times the actual current that it'll ever see. So here you've got figure 3 is SCR phase control. You got 30 degrees firing angle, and it gives you your average voltage. If you have a 90 degrees firing angle, your average voltage drops. So you can see you're only using half of each wave. A shaded area represents the voltage applied to the load. The earlier the SCR is fired, the higher the output voltage will be. We have power modules for your VFDs. If you have a single phase rectifier, you have 0.5 times IM, your RMS current, and your SCR full cycle average current is 0.318 times IM. And then these are just different firing angles. So if you were to utilize the full waveform, you would see that, right? But if you cut into it, if your firing angle is 120 degrees or 90 degrees or 60 degrees or 30 degrees, you obviously decrease your overall AC output, right? Your current. This is what a full bridge, 3-phase bridge would look like. It's called the Gantz bridge. Here's a Y-connected transformer connected to a full wave bridge, and it gives you your output for that VFD. So the neutral, you'll actually see positive V plus neutral, V to neutral voltage on the high side and negative on the other side, volt to neutral. So it's your V8 is actually double that value. So and they give you the different waveforms right there. So VPN, you've got your 3 phases, and so if you wanted to calculate that, you can run through that. So it's 3 times square root of 3 divided by 2 pi times VPN. I mentioned that these SCR pucks have to be clamped, right? So they have actually a compression pad on them. And when you install them, you put the paste on both sides, and then you have to torque it down, and you have a little torque gauge to tell you if you've torqued it down properly. Once you've torqued it down properly, you can test it. So if you wanted to test this on a bench, you need to clamp that SCR in a vise or something and then test it. Make sure you isolate your vise from the cathode and the anode so you can actually pass some current through it. Power modules for VFDs, if you have them, you want to use that RC network. So here you have a diode and you have an RC network. And here's 3 connected series thyristors, and the reason they would connect 3 of them in series is to increase their voltage, right? So if you wanted to go up into the 1,000 volt range, you start stacking SCRs, right? And start putting those diodes, the snubber networks and the resistive networks to ensure that you have balanced load across them, or voltage across them. Here's a thyristor stack, and you can see the large aluminum heat sinks, and they're sandwiched together, and then it's all compressed, all completely together, so you can kind of get a good picture of that. Here's all the components. It's 2 SCRs, 3 heat sinks, and some bus bar and that clamping device, and you can see the gates, the red and white gates off of that. This is actually a firing board, kind of an old one, but you know, a lot of this stuff didn't change for SCRs. It really hadn't migrated. This particular module is a 2.3 kV module. 3 thyristors are used in series, whereas the 1.2 kV module, there was only 2. So everything else is about the same. That's what it looks like right there. So you have a module for a 2.3 kV system right there. These green boards are your snubber boards. You can kind of see that. And then your heat sinks are in there, and you'd blow air across these devices so they would cool down. If you didn't blow air across them, they'd fail real quick. And here's a thyristor stack, 2.3 kV. So you've got your 3 SCR stacked, and then they're clamped together and compressed, and then you would fire those. So here's another 3 for a VFD. And here's a small little current toroid, so you can measure the current through it. And here's your snubber networks. So you got your RC snubber networks for a large 2.3 kV module. And here's your resistors for that power module. And there's your gating board, another PC board. Excitation exciter modules are used. 6 thyristors in an AC control configuration, snubbers again, and then that's what an excitation thyristor module would look like. This is with the lid off of it, so you can see it's got toroids in there and bus bars and fuses. You got the 3 fuses up front, and there's another module there. You can kind of get an idea what these things look like. I debated on should I go over op amps in this course or not, but sometimes when you deal with these old SCR circuits or old VFD circuits, you do have to know what a differential amplifier is. So, and these are op amps, so you have V1 and V2, the input, and then you've got your output. So if the values are all equal, it's pretty simple, but you basically take RF, the feedback resistor, the top one that goes from the negative to the output, divided by RI, which is the input resistor, times volts in. So if all the resistors are the same, then the difference amplifier is pretty easy to solve. The integrator, which is exactly what you think it is, it's an integration operation. You got your RI input resistor, and you've got your C capacitor on the output of it. And basically, if you have a square wave going into this, you would see a triangle wave coming out of it. If you had a triangle wave coming into it, you'd see a square wave coming out of it. This is your differentiator amplifier. So here you have a resistor and a capacitor in series with your resistor feedback. So you're actually able to, if I went back and looked at each one of them, the first one would be your gain, right? Your proportional gain. The second one would be your integral gain, and this one is your differential gain or your derivative. So these three components would make up a PID control loop, right? So here you have your reference input to an amplifier, and then you've got your object under control, and then your feedback there. So if you have your reference voltage steps up, then the feedback voltage would rise up slowly, and then it would kind of hug that reference voltage. So that would be just all P, right? So, and then we talked about this differential amplifier. So you've got you can use a summing junction here. So remember we were looking at those circles with a triangle, the X's through them. This would be a summing junction. You'd have your reference speed reference input. You'd have your encoder output feedback as well, and then you'd get a common output. So your output would be the voltage output here. So you have input equals reference minus feedback. So this is the mathematical equivalent of a proportional gain. So remember, proportional gain is your P in a PID loop. So you can actually create a proportional gain summing junction using that op amp. Here we have a summing junction of 1-to-1 and an integrator. So this is a PI loop. So if you were trying to if you wanted to design a proportional integral control loop, this is how you would design it. You would build a summing amplifier with a 1-to-1 ratio, and then you would add the additional integrator there. So you put the capacitor and the feedback on that integrator, and you can see the output voltage ramps up, right? So the input voltage is just a simple little square wave, but the output voltage would actually ramp up. And so this would be a PI. So you can see if you have this overshoot, right? If you overshoot real far, and then you can add compensation on it as well, so you can actually control it. Here's your differentiation. So your PID. So you got your capacitor in series with that resistor, and then you got a resistor in the feedback. And so you're trying to your output voltage goes high and then falls off. So when the input voltage is a step function, it goes high, then it tapers off. If it drops from some value to 0, then it goes low and then tapers off. So that would be your actual D or derivative input to that PID. So here's a complete analog equivalent regulator function. So you have your feedback coming in, and then you have your reference to your differentiator. So you have your summing junction there. Then you've got your integrating portion of it, and then you got your proportional amp down at the bottom. You got too many R's in that proportional amp. So you got your IP, and then you've got your summing junction there. So here you have a complete PID analog control system. Certainly you can do this with microprocessors now, but I thought I'd point it out. It's kind of old school, but kind of nice to look at. We talked about the effects of capacitors, but didn't really talk about how they function. So really what you have is a negative plate. You've got some dielectric material, and then you've got a large positive plate. And that's how a capacitor is created. Capacitors are measured in farads. So you have Q divided by E. And the capacitive reactance, which we really didn't talk about, but it's 1 over omega times C, right? So remember the inductive reactance was omega times L. So the capacitive reactance is omega times C, omega being 2 pi times F. So what happens if you put some capacitive, like some capacitors out there, and you're trying to correct your power factor, and then you put in a harmonic source, like a large a variable frequency drive that has an abnormally high current and harmonics. So what would happen is, if the frequency increases here, that means that the bottom portion of this equation gets real small, right? Or it gets real large, right? So the frequency increases, the bottom number gets very large, which means the capacitive reaction actually decreases. So if the harmonics increase, the ability for the capacitor to oppose those currents decreases. And that's exactly why capacitors pop, or fuses pop on these capacitor banks, because when you have high harmonic loads, the frequency is actually higher in different multiples of that frequency, and it causes this capacitive reactance to reduce, which is measured in ohms. And using Ohm's law, you can clearly see that the current's going to rise through that capacitor to the point where it can't handle it, and it will pop. Here is the power flow in a capacitive circuit. So you've got your E and you've got your I, and you can see your I is lagging 90 degrees, or leading 90 degrees, and then you've got your power is actually in the shaded area, so it gives you your overall power. Here's that inductor again with a voltage. We talked about this as self-inductance, right? When we were talking about motors, we were talking about how the field goes through one way, and then the current, and then you get a magnetic field that's induced into the other one. So you have what's called self-inductance, right? So that's actually kind of a cool thing. And here we are on a inductive reactance, right? And that's just omega times L. And if the harmonics increase, the frequency increases, the inductive reactance increases. So the resistance to those high frequencies increases. So that's a good way of reducing your harmonics, right? Is by adding impedance to the system. Obviously, if you add impedance to the system, you're going to have some losses, but you could prevent some problems later, right? And here's your power flow in an inductive circuit. So again, you have your E is your voltage, and you have your I is your current. You have a 90 degrees shift if it was purely inductive, and you can see the power in those in that circuit. Okay, so now we move into harmonics. We all know what AC induction motors are all about. We know about motor efficiency and motor assessment, when to change them out. We've talked a little bit about motor controllers. We jumped into variable frequency drives and covered just about everything you can think of there, short of actually operating a variable frequency drive. Now we talk about the harmonics generated by the variable frequency drives. And then finally we'll talk about application considerations. Application considerations. It is very common practice for power companies or their customers to impose harmonic distortion limits on IEC and IEEE standards. So, for example, IEEE standard 519 limits at the customer's connection the point call for the maximum individual frequency voltage harmonic to be no more than 3% of the fundamental, and call for the voltage total harmonic distortion, THD, to be no more than 5% for a general AC power supply. This waveform right here is a 6-pulse front end on a variable frequency drive. The steady state distortion of this waveform, it's periodic and continuous in nature. So you know it's a harmonic if it's steady state distortion of the waveform and it's periodic and continuous in nature. If, on the other hand, it's a spike, well then that's not a harmonic, that's more of a transient disturbance. Harmonic sources come from nonlinear loads. Single-phase loads such as fluorescent lights and personal computers create nonlinear loads. That's why you want to oversize your neutral. For three-phase loads, you have arc furnaces and AC-DC converters create nonlinear loads. Basic harmonic principles. Harmonics are persistent distortions in a wave shape. They represent integer multiples of the fundamental frequency. So remember we talked about the fundamental frequency is 60 hertz, and so you have in here a third harmonic or a fifth harmonic, and then so on and so forth. And then all these waves are added together so that the end result is the one on the left, right? You can do a harmonic spectrum analysis and find out exactly what those waves are. You'll find out what their frequency is, and you'll also find out the amplitude of that frequency. A periodic signal of frequency f can be represented in the form of a composite sum. So, like I said, you take h1t and you add it to h3t, and you combine those together, you get yt, which is your output, which is your composite sum. So, of a sinusoidal term at frequency f, the fundamental is h1, which could be 60 hertz if that's you're in the U.S. Could be 50 if you're overseas. Of a sinusoidal term of which frequencies are integral multiples, fundamental h1, the harmonic is hn, right? So it depends on the harmonic value. Of possible continuous components, you could also have a DC component in there as well. So here we have the order of the harmonic is the value of the integer which determines its frequency. For example, a harmonic of order 5 would be 5 times the fundamental frequency. If it happens to be 50 hertz, then your frequency of the 5th harmonic would be 250 hertz. It's hard to believe that you'd have all these different frequencies in a waveform, but that's exactly what happens when you have harmonics. If you had 60 hertz, that would be 5 times 60, or 300 hertz. So again, you have a harmonic spectrum as a percent of the fundamental. You've got H1 as your fundamental. You've got a little bit of H2. You usually don't see a even harmonic unless you have some type of an imbalance. You've got your 3rd harmonic, 5th harmonic, 7th, 9th, and 11th. And again, this is a little colored graph, so it summarizes the harmonics are nothing less than the components of the distorted waveform, and their use allows us to analyze any periodic non-sinusoidal waveform through different sinusoidal waveform components. The figure below shows a graphic representation of this concept. The red is the non-sinusoidal waveform, the result of all these different harmonics. The green is a perfect sine wave. It's your 1st harmonic. It's your fundamental. Your 3rd harmonic is shown in the blue, so it's at 180 hertz. Your 5th harmonic here is shown in the yellow, and it's if it's 60 hertz, it would be 300 hertz. So if you sum the green, the blue, and the yellow together, you would get that red output. So that's how that works. 2 sinusoidal sources connected in series. If you have U1 equals 60 volts at 50 hertz, U2 max equals 20 volts at 50 hertz, and so if you combine them together, you would actually get this waveform. So here again, you've got a bunch of different waveforms. You've got your basic harmonic, which is your maroon. You've got your 3rd harmonic is yellow. 5th harmonic is green. 7th harmonic, 9th harmonic, 11th harmonic, and then your final waveform is a total harmonic. Looks really bad, which is that dark blue. But it gives you an idea that you can add these all up. Harmonic and power systems. Harmonic in any voltage or current whose frequencies are integral multiples of f. The fundamental, for example, a set of sine waves whose frequency of 50, 150, 250, 450 hertz is said to possess the following components. It's said to possess the fundamental frequency of 50 hertz, the lowest frequency. The 3rd harmonic, which is 3 times 50, which is 150 hertz. The 5th harmonic, which is 5 times 50, is 250 hertz. The 9th harmonic, which is 9 times 50, is 450 hertz. The distortion of the voltage or current can be traced to the harmonics it contains. This distortion can be produced by a magnetic saturation in the core of transformers or by the switching of thyristors or IGBTs in electronic drives. Again, there's a fundamental plus your harmonic waveform. Sources of harmonics. Transformers. The 3rd harmonic currents are present in the magnetization current, a small portion of the transformer full load current. If the transformer is saturated due to overvoltage, the harmonic distortion level of the current increases substantially. So if you don't have any harmonic sources in your facility, but you see this abnormally large 3rd harmonic, you can double check to see if that transformer is saturated, right? If it's rated, if it has a serious overvoltage condition. Fluorescent lamps, these devices produce a predominantly 3rd order harmonic current on the order of 20% to 30% of the fundamental current. Electronic ballast have slightly different characteristics but exhibit similar levels of harmonics. And then of course pulse width modulated converters, your VFDs, these devices are Use an external controller for switching the input transistors, allowing the current waveform to be shaped more desirably. However, these converters are limited in power and typically used in applications less than a few hundred kilowatts. That's not always true. As we've seen, they've really taken off. Switching power supply modes typically found in the single-phase electronic devices such as computers and other business and consumer electronics. These devices use a switching regulator to precisely control the DC voltage. The input of these power supplies normally consists of full-wave bridge rectifiers and a DC filter capacitor, exactly what a VFD is, which produces an alternating pulse current waveform rich in third harmonics. Though they are not used in large power applications, the cumulative effect of many devices may create concerns, particularly in 480/230 volt Y systems or 480/277 volt Y systems. Wave shape of current absorbed by a nonlinear load. We talked about the Thyrac controlling as a light dimmer or a heating regulator. And so if you have a Thyrac going into a resistive load like that, with the alpha angle of pi divided by 2, you would have the following harmonics. You'd have a third harmonic of 54%, a fifth harmonic of 18%, a seventh harmonic of 18%, etc., etc., etc. If you have a switching power supply rectifier, so you have a full bridge rectifier on the primary side of that with a capacitor, and then you've got some type of a switching power supply on the output of that device, you can see that current jumps real high. You see that current is really out of whack. So you have a third harmonic of 75%, fifth harmonic of 45%, seventh harmonic of 15%, etc. In three-phase SCR type drives, you can see that waveform really chopped up. You don't have a third harmonic, but you have a high 5th, 7th, 11th, and 13th, 17th, and 19th harmonic. So if you have a 6-pulse front end, you don't have that third harmonic. Three-phase rectifier with a DC filtering reactor. So before you had the VSI, the voltage source inverter. Next you have a CSI, the current source inverter. So you have that reactor. So you can see the square wave is kind of different. It's not as worse as the other one. So by adding the DC filtering reactor, you can actually reduce your harmonics. So you have a 5th of 25, 7th of 7%, 11th of 9%, 13th of 4%. Your 17th harmonic is 5th and your 19th is 3rd. So if you added these up, you could actually calculate. You'd actually have to do, it's not a straight summation, but if you calculated them up, you could determine your total harmonic distortion. I think we'll cover that in a minute. Harmonic currents in three-phase systems. In the neutral conductor, harmonics can get more complicated in three-phase applications. Here, not only do we have to deal with the phase conductors, but also the neutral conductor, and especially in triplets, odd harmonics like his 3rd, 9th, and 15th harmonics and sequence harmonics. The triplet harmonics are the major cause of heat because they add together in the neutral conductor. So it's not uncommon to see a lot more current in the neutral than you see in the phases. The magnitude of the harmonic current produced in the triplets can approach twice the phase current. So if you've got a Y-connected system going to a building, you want to measure that neutral current, and if it's twice the phase current, you want to make sure that wire is sized for it. This causes the neutral conductor to overheat because neutral conductors were historically designed with the same ampacity as the phase conductors. But now that they've added all these different fluorescent lights and what have you, we have a high third harmonic. For example, a third harmonic of 75%, the current flowing in the neutral is 2.25 times the fundamental. The current in each phase is only the square root of 1 plus 0.75 squared, which equals 1.25 times the fundamental. That's a huge value. In an induction motor, a situation that produces abnormal amounts of heat in motors is the combination of positive and negative sequenced harmonics. So this is kind of interesting because this goes back to counter EMF and EMF and how counter EMF subtracts certain things, and EMF, so you have your EMF and you have your counter EMF and it reduces the current. Well, the positive sequence harmonics are the fundamentals 7th, 13th, 19th, etc. And they tend to apply an additional forward force to the direction of the motor, rotation. So if you have 7th, 13th, and 19th, they'll actually help the motor rotate. However, if you have the negative sequenced harmonics, which are 5th, 11th, and 17th, they present a force that opposes motor rotation and tries to make the motor rotate in the opposite direction. The force of these harmonics acting upon each other creates heat, which leads to premature failure. Harmonic voltage distortion causes increased eddy current losses in the motors, and in the same way as seen for transformers. So if you have a large drive that was installed and all of a sudden you're starting to have all these overheated motors, double check your harmonics, because you might have some abnormally high harmonics that are causing these induction motors to fail. Current, this is a diagram that shows you if you had just linear loads like incandescent lamps, then your neutral current would be extremely low. So the 120-degree phase shift between linear loads currents will result in their balanced proportions, instantaneously canceling in the neutral. With linear loads, the neutral can be the same size as the phase conductors because the neutral current cannot be larger than the largest phase current, even when the load is completely unbalanced. Where you get into trouble here is if the incandescent lamps are now changed to fluorescent lamps, and then all of a sudden, and that's exactly what happens. You got an old building, and it used to have linear incandescent lamps, and somebody went in there and retrofitted it with fluorescent lamps, or these compact fluorescent bulbs, and then all of a sudden you have this high third harmonic, and your neutrals are burning up. When the load is nonlinear, however, the current pulse on one phase will not have a pulse on either of the other phases for which to cancel. The pulses are additive, which often leads to heavier current on the neutral conductor than on any phase conductor. The frequency of the neutral conductor is primarily 150 hertz or 180 hertz for a 60 hertz system, which is the third harmonic. So you can see that they are additive. As they come together back into that neutral current, they actually increase significantly. So you can see up to 2 to 2.25 times the phase current. With nonlinear loads, the neutral current generally exceeds the largest phase current, even when the loads are in perfect RMS current balance. Harmful effects on receivers. Well, you have cables, overheating of cables, additional losses due to skin effects, increase in dielectric losses of insulation. In the motors, we have the increase in the core stator and the joule losses, pulsating torques causing efficiency reduction, abnormal vibration, rotor heating. So if you've got a high harmonic situation and you've got all these problems occurring, that's probably why. So you need to deal with those harmonics. Limit injecting harmonic currents. Install limitation inductor coils for speed drives. So if you install those chokes right in the DC link and also on the front end of the drive, you can actually reduce your harmonics. You can also install specific rectifiers called active front ends. And an active front end, we talked about that, where the front end of the rectifier is no longer a diode, but it's actually IGBTs. You can also install anti-harmonic induction coils. Install filters to trap harmonics, passive filters, active filters, or hybrid filters. And then, of course, you can oversize your equipment. We see oversized equipment when you see the K factor rating of transformers. So they're designed, if you have a K factor 13 transformer, that's designed to run a rectifier load, a 6-pulse large rectifier load. Active filters are kind of cool because what they do is they measure the harmonics and then they inject a opposite 180 degrees out of phase of that harmonic, same amplitude, so it actually cancels the harmonic. Passive harmonic filters I'm not a big fan of, but you can have them properly sized. Passive or trap filters employ passive elements, capacitors, inductors to trap or absorb harmonics. Passive filters are generally configured to remove only one or two specific harmonics, so you might want to size it for the third harmonic. Passive filters are generally regarded as unsuitable for the third harmonic, so you would shoot for the fifth and seventh harmonic. For this reason, they are best suited for applications in which third harmonics are not an issue. Power factor correction is required, and specific harmonics such as fifth and seventh are creating a problem. Passive filters are ideal for systems that have high percentage of 6-pulse drives and other linear loads. However, the filters may need to be retuned for changes in the power system. Filters can be designed for several nonlinear loads or for an individual load. So it's not always the best thing, and they're certainly hard to size, and sometimes they change as your power system changes. Principle of compensation of harmonic components by shunt type or an active harmonic conditioner. This is kind of cool. Like I said, the source current's coming in and it's nice and clean. Your load is distorted, heavily distorted, right? And then this compensation current actually looks at the load current and it reverses everything by 180 degrees and then feeds it back in, so it cancels it completely out. The device should be able to inject at any time a current where each harmonic current has the same amplitude as that of the current in the load and is in opposition of the phases, so it's 180 degrees out of phase with each harmonic. Then Kirchhoff's law at point guarantees that at point A guarantees that the current supplied by the source is purely sinusoidal, and these work like a champ. The only problem is if they ever fail, you've got those high harmonics again. Isolation transformers, I'm a big fan of them. I like things that are rugged and don't fail. An isolation transformer provides several advantages. First and foremost, it provides impedance to the drive, which reduces current distortion. Remember, I said that if you increase your inductive reactance, you increase your impedance, you can actually oppose the higher frequencies, right? The reactance to those higher frequencies, the inductive reactance increases. So it obviously resolves voltage mismatch between supply and the load. It's a secondary to grounded, it isolates ground faults and reduces common mode noises. So that's probably the best solution, I think, is to install a large, high impedance isolation transformer. We talked about this. We saw this typical harmonic spectrum for a 6-pulse diode drive, and again, it's the 5th, 7th, 11th, and 13th, 17th, and 19th harmonic primarily. Here's an actual harmonic resonance. So here we have on a 6-pulse machine, we have the 5th, 7th, 11th, 13th, the 17th, and 19th. We have a 12-pulse, 11th, 13th, 23rd, 25th, 35th, and 37th. And then we have an 18-pulse, has even higher harmonics, but the total harmonic distortion is significantly less. What we call a 6-pulse to a 12-pulse is called phase multiplication. What we do is we take two 6-pulse drives and we phase shift the AC input by 30 degrees, and so you see a 12-pulse drive. And you can also do the same thing. You can have 3 inputs to three 6-pulse drives, and you would achieve an 18-pulse drive. So you can see you have a fundamental of 100%, a 5th harmonic of 6.9%, 7th harmonic of 5.1%, and if you do the math, you'll find out your odd harmonics here are 29.6%, so your total harmonic distortion is 29.7%. So that's kind of cool. That's a harmonic analyzer looking at phase A voltage spectrum. Sources of harmonics, saturated devices such as transformers and nonlinear reactors. If they saturate, they can create harmonics. Arcing devices such as arc furnaces, welders, and fluorescent lights. And then obviously your power electronic equipment, adjustable drives, speed drives, DC motor drives, and electronic power supplies. Here again is an Excel spreadsheet that we created, and it gives you all the different harmonics, the amps, the amplitude of each harmonic, and it gives you the voltage and the ohms of each harmonic, and calculates your total demand distortion, which is used in a IEEE 519. DC motor drive current. So really what this is a 6-pulse bridge, and it's looking at the current spectrum. So you can see that the total harmonic distortion at the bottom is 35.9%. Weird is the even harmonics. Why are we seeing 5.9% even harmonics? Usually you don't see high even harmonics, and the reason that you're seeing this is because it's an imbalanced current. So or unbalanced voltage and current. So if you look at the voltage on the left here, you'll see phase A to B is 459 volts, B to C is 461 volts, and C to A is 456 volts. So you have an imbalance in your voltage. And you also have a large imbalance in your current. 339 amps in phase A, 347 amps in phase B, and 258 amps in phase C. So that's a large current imbalance. And that's why you end up with this high, even harmonic. Real abnormal to see that, but that's kind of an interesting printout. Current versus voltage harmonics. Harmonic currents flow through the system. Impedance results in the harmonic voltages at the load. I can tell you, as the user, if you're the user and you created that rectifier or installed that rectifier, you can only create harmonic current distortion, right? You're not going to affect the voltage distortion. The voltage distortion is a product or is a result of how stiff the utility system is. And that's where people kind of get confused. So as long as you have low current harmonics, then theoretically you should have low voltage harmonics, but you can't control them. IEEE 519 harmonics generated by nonlinear device characteristics. Most devices look at sources of harmonic currents. Voltage distortion is caused by system response characteristics. So the whole system causes the voltage distortion. 519 harmonic levels. The customer is responsible for limiting the harmonic currents injected into the power system. The utility is responsible for maintaining the quality of the voltage waveform. So if you looked at 519, you would see the voltage distortion limits. If it's 69 kV and below, it's 3% distortion. That's individual voltage distortion. Your total voltage distortion is 5%. Current distortion. So here we have something that's kind of different. What we do is we have to look at the short circuit current at PCC, the point of common coupling. You can see I short circuit, maximum short circuit current at point of common coupling. Then you look at your maximum demand load current and the fundamental frequency components at the point of common coupling. So the short circuit ratio is not a SCR like a silicon controlled rectifier. It's actually a ratio of the utility short circuit current at point of common coupling divided by the customer's average maximum demand load. So that being said, ISC is the short circuit current, IL is the load current, and so if you have a relationship where that number comes up to something like 1,000, that means that your total demand distortion of your drive can be up to as high as 20%. And you'd still be in compliance with 519. So that's kind of interesting, right? So if it's if that I short circuit divided by your I load is less than 20, then you need to be 5% TDD. And the only way you're going to get 5% is if you install like a 18 pulse drive or some type of a reactor on a 12 pulse drive. And we'll talk about that in a little bit. Mitigation techniques. To mitigate your harmonics, you can do phase multiplication, you can do line reactors, you can do phase shifting transformers, you can go K-factor transformers, you can derate transformers, and you can install filters. So the top graph at the right, you've got line reactors, so you've got line reactors installed in front of that rectifier diode, and you can also add a DC bus reactor, and we saw that that reduced some of the harmonics. On the graph below it, that common bus, you see two transformers. So you have YY and a delta Y. And so you have nonlinear loads on a YY and you have nonlinear loads on a delta Y. And because the delta Y is a shift of 30 degrees and a YY is a shift of 0 degrees, then the loads fed on the other bus have there's a difference between 30 degrees. So you would actually see at the common bus the effects of a 12 pulse drive. So because it's phase shifted by 30 degrees. And then if you do decide to put in a filter, you want to use a delta connected filter with a reactor. So here's pulse rectifier without inductors, 63% fifth harmonic, 54% seventh harmonic. Pulse rectifier with inductors You can drop it down to 30% fifth harmonic, 7%, 12%, or seventh harmonic is 12%, etc. You have a 12 pulse rectifier with a polycon transformer like a delta Y. You'd see fifth harmonic 11%, significantly drops down. Seventh harmonic is 5.8%. 11th harmonic would be 6.2%. 12 pulse with a double wound transformer. So here you even have further reduction. So you have a double wound transformer. Fifth harmonic is 3.6%, and 2.6% is on your seventh harmonic. You can even step up to a 24 pulse rectifier with two 3-winding transformers. So you have a delta Y and a delta Y system, right? Two 3-winding transformers. So each one is the equivalent of a 12 pulse rectifier. So combined, they're 24 pulse. So you'd see, fifth harmonic of 4%, seventh harmonic of 2.7%, and 11th of 1%. You can see the manufacturing cost rise significantly for a 24 pulse, 250% the cost of a 6 pulse rectifier. You can use an active IGBT rectifier, which is a great idea. It says manufacturing cost is 250%. Not significant if electrical braking is anyway needed. If you have a situation where you have to deal with electric braking, you want to regenerate that power back, you're going to have that active IGBT rectifier front end anyway, and so your harmonics are extremely low. You can actually locate your harmonics. You can actually use the following downstream to the load, and you can measure each one, and you can figure out where all those harmonics are. So it's not as complicated as you might think. If you had somebody go out there, they can measure all the connections to your utility source and determine who the culprit is. End user harmonic control. Prevention is key. Know your sources. Check for resonance. Filter near the sources, not away from the sources. Put power factor correction capacitors near the loads that need them. Check wiring adequate size given true RMS current. A lot of people don't measure true RMS current, and they actually use an averaging current meter, and that can be a real problem. So here's a problem. This is a free software package you can download from Mirus. Do we have harmonic problem? So here we built a model. We have a utility transformer of 100 MVA. It's got a short circuit at 100 MVA, 13.8 kV. Got a cable, some power factor correction capacitors. I think those are not even installed. We've got a user transformer of 2000 kVA with a 6% impedance at 480 volts. We've got some distribution panels. We've got a load, a motor load out there. It's 84.9 kilowatts. It's got a power factor of 0.8. We also have a 6 pulse drive. It's 600 horsepower, and it's fully loaded. It's running max. So the answer is, do we have a harmonic problem? And you run this software and you'll find out, yes, indeed, you do have a harmonic problem. You have 716.8 amps. Your current distortion is 53.7%. Your point of common coupling is number 2, shows a current distortion of 17.4% and a voltage distortion of 1.2%. The point of common coupling of number 1 is 17.4% current distortion and 5% total voltage distortion. So you always want to decide where your point of common coupling is. You don't want the point of common coupling to be at the drive, the front end of that breaker of that drive. Certainly you fail every time. Your voltage point of coupling number 2, they give you a waveform of it, and they give you your harmonic distortion. Your current distortion, you can see that at point of common coupling 2, and they give you your total harmonic distortion. So you can see this is a report that it gives you. It's 17.4%. It fails. IEEE 519 limit in percent is 12%, and max individual current harmonics is less than 11th harmonic is 16.2%, and so you fail on that one as well. So this application actually failed. So let's say we change it to a 12 pulse drive, and then we rerun this test. So here we've added a 12 pulse drive, and it just kind of models it funny. It shows it as 6 pulse drive, but it's really a 12 pulse, and it has 12 pulse operation. So we ran it again, and the results were, oh, we almost passed. Because we now increase the harmonic values, we don't have the lower harmonics anymore, because when you shift to a 12 pulse rectifier, it switches. So 11 to 16th harmonic, individual harmonics, we have 4.1%, and the IEEE 519 limit here is 3.5%, so we failed that one. Let's say we have a 12 pulse drive with a 5% AC reactor. So we add in front of that drive a 5% AC reactor, and then we run the numbers again. Now we pass. So you got to understand all the point of common coupling on these studies and run the different software to make sure you're not going to get yourself into a situation. You can also model your existing system. If you've got like a refinery or something, you want to call a consulting firm and let them model that entire system. We do that at my job, but it's kind of a complicated thing, and it involves a tremendous amount of effort and field collection data. If you add a power factor correcting cap, so we're going to add a cap, and we're going to have a cap with no tuning, and sometimes you want to be careful that you don't add a capacitor that's not tuned for that third harmonic. Otherwise, you can get yourself into some problems as well. Harmonic analysis: build a model of the system of interest, determine the harmonic source characteristics, run the simulation, examine the results, design the solution, then check the solutions. So you can apply a filter. If you do it, the best way to do it is to build a delta type configuration and to put a reactor in front of it. Harmonic control devices: inline reactors, chokes. You can use zigzag transformers. You can build passive filters. You can build active filters. You can design a harmonic filter. Inline chokes: these are nice reactors you can buy. Simply a series inductance presents a series impedance that is directly proportional to frequency, forces DC bus capacitor to charge more slowly because it opposes any change in current. Additional benefits: reduce DC bus voltages due to capacitor switching transients and reduce nuisance tripping. So adding an inline reactor on the front end of that drive will actually have a lot of positive effects, not only reducing the harmonics. Inline reactor chokes: sizing the inline reactor. Line reactors are typically described as 3% reactors, or 3% to 5% are common. Size is based on the VA rating of the drive. So you have your VA base squared divided by your VA base times your impedance, 0.05. So your inductance in Henry is based on X of L at the fundamental frequency. So my recommendation is for you to go to a manufacturer like MTE. You can Google MTE and they'll size that reactor for you, or they have pre-selected reactors that you can use. Passive filters: capacitors and inductors can be arranged to produce high or low impedance at certain frequencies. Resistors can be added to provide damping. Shunt passive filters provide a low impedance alternate path. Series passive filters increase the series impedance for certain frequencies. Again, things might change over time, so if your systems change significantly, you might want to go back and calculate those passive filters again. So here you have a shunt passive filter. Notch filter is the most popular. May employ delta or Y connected capacitors connected to the line or neutral through inductor. So here you have a passive filter. It's a series passive filter, provides a high impedance to the target harmonic, must carry full load current, not practical for multiple harmonics, useful in single phase applications. General approach with passive filters: start at the lowest harmonic of concern, tune filters slightly lower than the target harmonic, check for resonant points, creating high impedances. If system impedance changes, you have to reevaluate that filter design. Active filters use power electronics to inject the missing current in the nonlinear loads. Current waveforms results in minimum distortion of the source side. No resonant concerns. May also correct power factor and flicker, voltage flicker. Harmonic summary. So harmonics are persistent distortions in a waveform or wave shape. Power electronics are the prime source of harmonics. Power factor capacitors aggravate harmonic issues. Modeling and simulations can evaluate various solution alternatives. Okay, so we finally made it through. It's 6 hours, roughly 16 minutes. We have the application considerations now. So we've gone through AC induction motors, we've gone through motor efficiency and motor assessment, we've gone through motor controllers, we've talked about variable frequency drives, we've talked about the harmonics associated with variable frequency drives and nonlinear loads, and now finally we have application considerations. AC line harmonics. While harmonics in a pulse width modulation output can easily be filtered by carrier frequencies, related filter inductance to supply near sinusoidal currents to the motor load, the VFD's diode bridge rectifier converts AC line voltage to DC voltage output by superimposing nonlinear half-wave or half-phase current pulses, thus creating harmonic current distortion and hence voltage distortion of the AC line input. When the VFD loads are relatively small in comparison to the large stiff power system available from the electric power company, the effects of the VFD harmonic distortion of the AC grid can often be within acceptable limits. So the first power or application consideration is for you to know that there are AC line harmonics, right? And we went over that extensively just before this. So furthermore, in low voltage networks, harmonics caused by single phase equipment such as computers and TVs are partially canceled by the three-phase bridge harmonics because their fifth and seventh harmonics are in counter phase. However, when the proportion of VFD and other nonlinear loads compared to total load of a nonlinear load compared to the stiffness of the AC power supply, or both, is relatively large, if your VFDs are abnormally large, the load can have a negative impact on the AC power waveform available to other power company customers on the same grid. Two other harmonic mitigation techniques exploit use of passive or active filters connected to a common bus with at least one VFD branch load on the bus. Passive filters involve the design of one or more low-pass LC filtered traps, each trap being tuned as required to the harmonic frequency, and you'd go for the 5th, 7th, 11th, and 13th. And we've talked about that. When the power company's voltage becomes distorted due to harmonics, losses in other loads such as normal fixed speed AC motors are increased, and we saw that as well. This may lead to overheating and shortening the operating life of these motors. Also, substation transformers and compensation reactors are affected negatively, and in particular, capacitors can cause resonant conditions that can unacceptably magnify harmonic levels. In order to limit the voltage distortion, owners of VFD loads may be required to install filtering equipment to reduce harmonic distortion below the acceptable limits. Alternatively, the utilities may adopt a solution by installing filtering equipment of its own at substation affected by the large amount of VFD equipment being used. In high power installations, harmonic distortions can be reduced by supplying multi-pulse rectifier bridges, 12 pulse, 18 pulse, 24 pulse drives from transformers with multiple phase shifting windings. They call that phase multiplication. It is also possible to replace a standard diode bridge rectifier with a bidirectional IGBT switching device, bridge marrying the standard inverter, which uses IGBT switching device output to the motor. Such rectifiers are referred to by various designators, including active in-feed converter or active rectifier IGBT supply unit, or active phase front end, or 4-quadrant operations. And again, we know that an active front-end variable frequency drive will allow for quadrant operation. It is also possible to replace a standard bridge rectifier with a bidirectional IGBT switching device, bridge marrying the standard inverter, which uses IGBT switching devices output to the motor. Such rectifiers are the active rectifier, and they improve your power factor and reduce harmonics. With pulse width modulation control and suitable input reactors, AFE's AC line current waveform can be nearly sinusoidal. AFE inherently regenerates energy in 4-quadrant mode from the DC side to the AC grid. Thus, no braking resistor is needed, and the efficiency of the drive is improved if the drive is frequently required to brake the motor. Long lead effects. I think I kind of mentioned this once before. The carrier frequency pulsed output voltage of the PMD, the pulse width modulation VFD, causes rapid rise times in these pulses, the transmission line effect of which must be considered. Since the transmission line impedance of the cable and the motor are different, pulses tend to reflect back from the motor terminals to the cable. This can be a real problem. The resulting voltage can produce overvoltages equal to twice the DC voltage, or up to 3.1 times the rated line voltage for long cable runs, putting abnormally high stresses on the cable and motor windings, and eventually installation failure. So you want to maintain the motor distance from the VFD as short as you possibly can. Note that standards for three-phase motors rated 230 volts or less adequately protect against such long lead over voltages. On 460 and 475 volt systems and inverters with third generation 0.1 microsecond rise time IGBTs, the maximum recommended cable distance from the VFD and motor is about 50 meters or 150 feet. So certainly you don't want to exceed that. Long lead effects, solutions to overvoltages caused by long lead lengths include minimizing cable distances, that's the easiest thing, lowering your carrier frequency, but if you lower your carrier frequency, your motor might sound funny. It might make funny noises and squeal and stuff, or whistle or something. You can also install DVDT filters, which is opposes any change in voltage with respect to time. Using inverter duty rated motors that are rated 600 volts to withstand pulse trains with rise times less than or equal to 0.1 microseconds or 1600 volt peak magnitudes, and installing an LCR, a low pass sine wave filter. That's an inductive capacitive resistive low pass sine wave filter. I think that you should just order your motors with inverter duty rating, and you should decrease the length to less than 150 feet. Regarding lowering your carrier frequency, note that audible noises is noticeable, increasing for carrier frequencies less than about 6 kilohertz and is most notable at about 3 kilohertz. So you want to watch that. Also on long lead effects, note there also has a selection of optimum pulse width modulating carrier frequencies for AC drives involving balancing noise. You're trying to balance the noise, the heat, the motor insulation stress, the common mode voltage induced in the bearing current damage, and the smooth motor operation and other factors. Further harmonic attenuation can be obtained by using an LCR low pass sine wave filter or that DVDT filter. Bearing currents, something you don't always think about, but if you're having bearing problems, this might be educational for you. So motor bearing currents, pulse width modulation drives are inherently associated with high frequency common mode voltages and currents, which may cause troubles with motor bearings. When these high frequency voltages find a path to earth through a bearing, transfer of metal or electrical discharge machining, EDM sparking occurs between the bearing's ball and the bearing's race. Over time, EDM-based sparking causes erosion in the bearing race that can be seen as a fluttering pattern. Because the voltage output of the VFD is the result of a high-speed switching, the waveform more closely resembles a square wave instead of a sine wave. As a consequence, an imbalance is present between the three phases that are entering the motor leads, referred to as a common mode voltage. And we talked about this. This pulse width modulation, if it's a perfect sine wave, you don't have this problem. But if you have this pulse width modulation, you have this common mode voltage, and you'll have high bearing currents. What we're looking at here is we have the currents would flow around the motor frame through the bearings, and you can see the three-phase waveform, and the varying flux encircles the shaft. So here we have an example where the stator to rotor current coupling is red, so you can see that current flow. Then you see the rotor to shaft current is green, so it's flowing through the shaft right to the load. Then you got your stator winding to frame current, which is from the stator windings through the frame, through the bearing to the load. And then finally you have your stator winding to ground current, which is blue, which is a stator current to the actual ground. So you've got all these different bearing currents. bearing currents. As soon as the motor is started with a VFD, the common mode voltage imbalance searches for a path to ground, and a parasitic coupling of the rotor and the stator windings develop. Once the oil film in the dielectric breaks down, voltage levels increase on the motor shaft, and the lowest impedance path for the current impedance imbalance becomes the motor bearings themselves. Voltage begins to arc across the bearing at high frequencies, leading to electrical discharge of machining. In large motors, the stray capacitance of the winding provides paths for high-frequency currents that pass through the motor shaft ends, leading to circulating type of bearing current. Poor grounding of the motor stators can lead to shaft ground bearing current. Small motors with poorly grounding driven equipment are susceptible to high-frequency bearing currents. Prevention of the high-frequency bearing current damage uses three approaches. First, good cabling and grounding practices. You want to ground not only the outside enclosure of the machine, but you also want to ground the load. And interruption of bearing currents and filtering or damping of common mode currents. Good cabling and grounding practices conclude using a shield, a symmetrical geometrical power cable to supply the motor, installation of grounding the shaft grounding brushes as the conductive bearing grease. Bearing currents can be interrupted by installing insulated bearings and specially designed electrostatic shielded motor induction motors. Filtering and damping high-frequency bearings, or instead of using standard two-level inverter drives, use either three-level inverter drives or the matrix, the MC drive. Since inverter-fed motor cables' high-frequency current spike can interfere with other cabling in facilities, such inverter-fed motor cables should not only be shielded symmetrical geometry design, but should also be routed at least 50 centimeters away from signal cables. So you want to keep your power cables away from your signal cables. Motor frame size. Motor bearing currents have a direct relationship to the motor size. Specifically, over 450 horsepower have been found to have the greatest candidates for bearing currents due to the higher likelihood of magnetic asymmetry in the construction of the motor windings. While large motors will experience some amount of bearing currents, motors powered from VFDs introduce additional magnetic asymmetry from common mode voltage. Rough handling. Believe it or not, if somebody was to drop that large motor, they can actually increase the bearing currents as well. Motors that are at increased risk of shaft voltage if they were handled roughly during shipment. Oftentimes damage can occur in the factory, in transit, or when the motor is being lifted into a pedestal. Minor motor damage during shipment may not cause noticeable problems with motor performance. However, it increases the likelihood of magnetic asymmetry, leading to bearing current development. So what you want to do is you want to measure the shaft currents and the bearing currents that would flow through there and understand it. And once you've understood it, you can take it out to the field and make sure that it matches. This is the way you can actually measure it. You can, you add a grounding strap and a current probe, and you can put a carbon brush on that rotating shaft, and you can actually measure these rotating, the bearing currents. So after the ambient noise measurement has been completed, the carbon brush is placed directly to the spinning motor shaft. Several measurements should be recorded with an effort to ensure the entire waveform can be viewed on an oscilloscope. Careful observation of the waveform should reveal a sharp spike in voltage is present, which would be indicative of a shaft voltage discharge. Voltage is in excess of 0.5 millivolts peak to peak is oftentimes cause for further investigation. However, in VFDs, the nominal value will almost always be in excess of 0.5 millivolts. The examples discussed below indicate various examples of shaft voltage tests. So here you can see motor A, and it has an abnormally large peak to peak. It's if you look at the A, it's 74.8 volts. It's extremely high. So the oscilloscope screenshot shown and presents clear evidence of shaft voltage with a peak to peak value of 74.3 volts. This is well above IEEE 112 allowable value of 0.5 millivolts, as well as the manufacturer's allowable voltage of 1 volt to 2 volts for VFDs. So if you have a large 450 horsepower motor, you can measure that shaft current and you shouldn't see more than 1 to 2 volts peak to peak for VFDs motors driven by a VFD. A peak voltage of 74.3 volts imposed upon the shaft likely means that the bearings will not survive much longer unless remedied. When testing a motor, it is often useful to test the B motor. So if you've got two motors that are almost identical, you can check A and B, and then a screenshot shown in the B motor of the cross-the-line motor that was dropped during shipment. So here we have a cross-the-line motor, but it was dropped during shipment. So you have a 0.6 volt reading. Clearly, there's no evidence of shaft voltage or damage to the bearing in this waveform. Oftentimes, comparing two similar motors can help pinpoint if the problem lies in the motor itself with transient voltage power supplies or in faulty grounding systems. And that's a big key, right? If you don't ground that system properly, you can have all kinds of problems. Another application consideration is dynamic braking. Torque generated by the drive causes the induction motor to run at synchronous speed less the slip. If load inertia energy is greater than the energy delivered to the motor shaft, the motor speed decreases as negative torque is developed in the motor, and the motor acts as a generator, converting output shaft mechanical power back to the electrical energy. The power is returned to the drive's DC link element, the capacitor or reactor. The DC link connected electrical power switch or braking DC chopper, either built-in or external to the drive, transfers this energy to external resistors to dissipate the energy as heat. If you don't have a dynamic braking resistor in there, or if this is not installed, you can do a DC over voltage on the bus and it'll shut itself down. Cooling fans may be used to prevent resistor overheating. Dynamic braking wastes braking energy by transforming it to heat. By contrast, regenerative drives recover braking energy by injecting this energy on the AC line. The capital cost of regenerative drives is, however, relatively high, so it might not justify it. Here's a picture of a dynamic braking system. Here you have your 60 hertz input to the rectifier. You've got your DC link with your capacitor. You've got your inverter and then your motor. You've got that chopper and your resistor. So whenever in the far left here, you can see a better detail of it. So whenever the situation is that the DC link starts rising to a value that's too high, the chopper will come in and allow that DC voltage to be bled down through that dynamic resistor and reduce that voltage for you. The regenerative AC drives have the capacity to recover the braking energy of the load moving faster than the designated motor speed and overhauling load and return it to the power system. Current source cycloconverters or matrix drives inherently allow return of energy from the load to the line, while voltage source inverters require an additional converter to return that energy to the supply. Regenerative drives. Regeneration is only useful in VFDs where the value of the recovering energy is large compared to the extra cost of the regenerative system, and if the system requires frequent braking and starting. Regenerative VFDs are widely used where speed control of overhauling loads is required. Some examples: conveyor belt drives from manufacturing, which stop every few minutes. While stop parts are assembled correctly, once it is done, the belt moves on. A crane where the hoist motor stops and reverses frequently, and braking is required to slow the load during lowering. That's it. That's the entire course. It was 6 hours and roughly 35 minutes or 40 minutes or so. You'll also find on this DVD a copy of the variable frequency e-books. Basically, these are books that I found online that had no copyright restrictions on them. There's roughly 13,072 pages of documents in this e-book. It's a wonderful collection of data. Certainly give anybody credit where credit is due. So you'll certainly find some Alan Bradley technical guides in there, Siemens Power Engineering technical guide books in there, and some other people. Some guy was a PhD and he wrote a book, ebook on there. But again, I didn't try to hide anything or anything like that. If it didn't have a copyright on it, I went ahead and used it as the ebooks. I hope you enjoyed this class, and I hope it helps you to be able to apply VFD successfully. Thanks a lot for your time, and that's it.